So good morning, everyone. Welcome to this third edition of the Zak World of Façade conference series. My name is Ahmed. I'm part of the organizing team here at Zak. We'll start due to paucity of time. So I'd like to quickly introduce the Zak World of Façade conference series for those who are attending it for the first time. So we've been doing these events since 2012. This is our 10th edition in Australia and the third one in Brisbane. We did the first one in 2019, 24, and now in 26. And we are organizing this event in close to 50 countries around the globe now. This is our event lineup for 2026 lineup. So we go to various different countries around the globe. Countries which are new this year is Albania. Albania has the number of projects that are under construction in Albania puts many European countries to shame, especially new build projects and high-rise towers. We go back to Uzbekistan, we go back to Georgia, and these are kind of places where there's a lot of growth happening, there's a lot of construction activity happening, a lot of new build projects which are happening. Most of the other Western world, mainland Europe is about adaptive reuse, refurbishment, and it's a little different set of topics that are presented at those kind of events. Very carbon focused, embodied carbon, recycled materials, reuse of materials. We still have that a little bit here, but I think in most of Europe and America, I think the discussion is on those kind of topics. And of course, the Middle East is about giga projects. Southeast Asia is still cost is all built on cost and other factors. So it's a big mix of events which we curate around the globe, and all the topics are curated to that respective city, to that respective country or region. These events are courtesy our event partners. I'll quickly introduce all of them. We have 20 of them. All of them are exhibiting outside in the tabletop displays, which you would have seen. We've got a fantastic range of exhibiting brands this time around. So we'll start with Alspec. Alspec are an Australian door, window, curtain wall system company. They're also an extruder, and they're also launching glass products at this year's edition. CAS is from China. They have unitized panels with the sell and fabricate, and they are also distributors of Lopo. Lopo is one of the largest terracotta cladding manufacturers globally. Dulux, again, an Australian company, powder coating, as they say, and DGL, which is a sister company, which is their international brand for powder coating for aluminium profiles. Equitone by Etex, fiber cement cladding. They've got a very nice non-combustible product with different finishes. Fangda from China, again a big curtain wall producer, but they've got a lot of other cladding products also which they have displayed at the event here. Firefly have pacifier protection products for the curtain wall and cavity, for the curtain wall and cladding sectors. Frontek is from Spain. They are extruded porcelain or ceramic-based cladding. High UV is from China, so they're one of the world leaders in advanced polymer materials. So they've got films for dynamic glazing. Janssen is from Switzerland. So Janssen is the world leader in steel door, window, and curtain wall systems. It's not too popular in this part of the world, but steel is now coming back into fashion, mainly in Europe, in adaptive reuse and renovation projects. Knauf is a big German multinational. This is Knauf Aqua Panel. They've got cement board cladding and other products. Northwood, Australian company, they are into aluminium cladding products with different finishes. Lysaght, formerly Blue Scope, steel cladding, various solutions for the complete building envelope. Proclima from Germany, they are into weatherproofing solutions, which is breather membranes, vapor barriers, and they're also displaying the whole system. Sculpsform, again another Australian company, rain screen cladding systems and other value-added products for the facade segment. Siderise is from the UK, so they've also got passive fire protection products, cavity barriers, and fire protection products for rain screen cladding. Solar Lab is from Denmark, so they are into BIPV, building integrated photovoltaic solutions, and not the old ugly style, but the new decorative one. BIPV is picking up a lot in Australia. There are a lot of projects in Sydney and in Melbourne with completed examples, and these are the new age, the next generation of photovoltaic glass. Technoform, German manufacturer of thermal performance solutions. So they've got polyamide strips which are used to improve the thermal performance of aluminum profile, and warm edge spacer bars to improve the U value of your insulated glass units. Vector Foil Tech, Asia Pacific, is the global leaders in ETFE solutions, lightweight cladding and roof product. You'll be hearing from them in their presentation. Wallnova is from China. They've got perforated cladding solutions and a lot of other value-added products. Any metal fabricated products is what they have. Webforge Locker, which is part of Valmont. Valmont's a big company. They've got same perforated panels, screens, second screens for parking garages, shading, and other stuff. Next event is actually next week in Melbourne. So again, different set of topics, different set of speakers over there. And that's next week. We have two events in March. That's Barcelona. We do it at this beautiful Torre Glories building, which is, I think it has jalousie louvers. I think the world's tallest building with jalousie louvers. They have trouble cleaning them, but that's another story. But it's a fantastic building. Washington, D.C., again, our first event in the North American series. We started the Zak Awards for Excellence in Facade Design and Engineering in this region last year with Sydney. I think it went well, so the idea is to repeat the same in Melbourne this year. So this is what we do. We do everything related to doors, windows, facades, these conferences, these awards all across the globe. And today's speakers are talking about projects predominantly in this region, Queensland and the wider western coast of Australia. So eastern coast of Australia, I'm sorry. And I hope you enjoy today's storytelling from our speakers. That's it from me. I'd like to call upon today's event host and convener, Kavita Gonsalves. She is the head of sustainability for Asia Pacific at Populous. Populous are a global firm. They are known for their designs for some of the biggest stadiums around the globe. So she's going to be our event host for today and curating this until the end of the day. So thank you all, and we hope you enjoy today's event. Sorry, I forgot to add. Post-event, we have a networking reception in the exhibit area itself. So we've not had that at the previous editions, but we have it this time around. So please do stay back for a drink once the event ends. So thank you and enjoy today's event. Thanks.
Thank you, Ahmed. Good morning, Brisbane. So Brisbane, known as Mianjin, Magunjin, is the land of the Turrbal and Yagara people who have cared for this place for tens of thousands of years and continue to thrive here today. We recognize their sovereignty, resilience, and enduring culture, and acknowledge our responsibility as guests to contribute to a future of equity and respect. I also acknowledge each of you here today and all of those who have come before you, who have brought us to this moment. Welcome to the Zak World of Façades Australia 2026 here in Brisbane. My name is Kavita Gonsalves, and I am the head of sustainability for the Asia Pacific region at Populous. It is a pleasure to be here today with you all. At Populous, facades are the interface between people, place, and performance. They shape identity, mediate climate, enhance experience, and increasingly carry the responsibility for sustainability, resilience, and long-term value. As designers of major civic and sporting venues across the globe, we understand that facades are critical to environmental performance user comfort, and cultural expression, particularly as we look ahead to Brisbane 2032. So I'm quite excited to hear from all the speakers today and learn from them. Just a few quick housekeeping notes before we begin. If I could ask everyone to pop your phones into silent mode. We love connectivity, just not the ringtone remix that might pop up during a keynote. There won't be any Q&A during or immediately after the presentations. If something sparks your curiosity, and I hope it does, please grab the speakers during the breaks. They're brilliant, and a good cup of coffee always does the trick. We will also keep a gentle but firm eye on the clock today. We have a lot to get through. The countdown timer is visible on the prompter screen. I'll have the support of the organizing team to help manage timing so we can finish on schedule and everyone gets their full moment on stage. We have a full and exciting program ahead, exploring innovation, compliance, sustainability, and the future of facade engineering. So let's begin. To open our program, I welcome Naveen Dath, the director of Cody Parker. His topic is Reframing Subtropical Urbanism, the Facade as Civic Interface at Queen's Wharf, Brisbane. This topic will showcase a climate-responsive facade shaped by river-inspired forms, integrated public spaces, and subtropical performance, redefining Brisbane's skyline ahead of 2032. Please welcome him.
Gives you a good idea of what the entire project actually comprises. It's an animation that was done a long time ago. It's a useful start for people that haven't been to Queen's Wharf. While that's playing, quick show of hands, how many people have actually been to Queen's Wharf in this room? Oh, pretty cool. A lot more than expected, that's very good. Fun and games. The intention for Queen's Wharf has always been about creating something that is transformational for Brisbane. And obviously, Queen's Wharf opened its doors about 18 months ago, and what's fascinating to see is how this transformation is actually playing out. It's evolving how this part of the city has changed, and it's evolving how people engage with and use and experience that southern part of the Brisbane CBD. It's changed South Bank as well. It's obviously changed the skyline of Brisbane, particularly from South Bank, and it's transforming all the waterfront in the city as well. But we're not here today to talk about urban regeneration. We're here to talk about architecture. So what I'm going to try and do today is take a step back and look at the bigger picture. I'm going to try and give you some insights into the architectural design of this transformational project. We'll try and unpack some of the key design fundamentals and the design drivers of this project and how we've gone about putting this together. It's obviously been a very long journey, almost about 11 years. We started this journey in about 2013, 2014, and it's been about 11, 12 years delivery. Before I get started, though, I do want to also acknowledge the traditional custodians and the owners of the land on which we gathered today, the Turrbal and the Jagera people, and that's where the site is located as well, on the banks of the Mewa. And I'd like to pay respects to the elders past, present, and emerging. So when we started this project in 2013, 2014, that was the skyline of Brisbane. Fairly nondescript. Brisbane was a completely different place 15 years ago. Brisbane always had the potential, and there was aspiration for Brisbane to become an international city, a global city, a new world city. But we were still tagged with being an old country town, so we're still trying to shed that perception of being a large country town. Fast forward to 2025, 15 years later, we've got Queen's Wharf delivered on that skyline. It's obviously clearly it has transformed the skyline of Brisbane, that's for sure. It's transformed that waterfront area of Brisbane as well, particularly when you compare it to what used to exist or not exist before Queen's Wharf. And that's not just a daytime thing alone, it's also a nighttime thing. It really comes alive at night where the facade actually takes over and creates this captivating backdrop for how you experience South Bank, particularly at events times as well. What makes this job really challenging is a combination of three things really for us as designers and architects and developers as well. First and foremost, the location, as I said, is extremely prominent on the banks and northern banks of the Brisbane River. It's a skyline-defining location. There is a very strong historical context to this site as well. I'll talk about this towards the end of this presentation as well in a little more detail, but this is the site where Brisbane as a city originated. The Moreton Bay Penal Colony and the Brisbane City. This is where it actually originated as well. So there's a very strong historical connect to the site as well. And this precinct, this section of the site, is also the historical precinct, the heritage precinct of Brisbane, if you like. And that's where you've got heritage buildings that exist that talk to the birthplace, the birthing stories of Brisbane. But what makes it even more complicated is this layer of vertical integrated public realm throughout the development. You probably heard, and hopefully some of you have experienced, the 12 football fields of public open space that's throughout the master plan. But a lot of that public open space is actually vertically integrated throughout the architecture, throughout the height of the development, culminating in the sky deck 30 stories above ground. And that poses a significant challenge to the architecture of the project, to the design of the project, to everything that we've done. And that's not just about planning alone, but it goes down to even simple details like the materiality and the finishes and how soffites and ceilings are actually fixed back to the main structure as well. So although it is ultimately an entertainment-focused, mixed-use destination, a developer-oriented project, it still has a very, very strong civic layering to it, which makes it very complicated. And it's important to acknowledge that because those three things put together are basically the fundamentals of most of the decision-making that has happened throughout the history of the project. The vision for Queen's Wharf from the start, from 2013, 2014, when we originated the first sketches for these projects, has always been about creating something globally significant, something that would propel Brisbane onto the world stage, something that would help Brisbane take its place as a new world city, and hopefully attract the Olympics, which we are doing now. But it also had to be, at the same time, authentically in and of and about Brisbane. And this was quite fundamental to everything, because it's quite fundamental to tourism as well, because the fundamental of tourism is that you attract locals first, and the tourists will follow. So creating something for the people of Brisbane that is in and of Brisbane, that celebrates everything that Brisbane has to offer, has been fundamental to that vision. To understand that, how do we go about doing that? First and foremost, we need to understand the context of Brisbane, the place. So Brisbane is the third largest city in Australia. It is the fastest growing capital city in Australia. Wasn't the case 15 years ago, but it certainly has been in the last 4 to 5 years post-COVID, that's for sure. We have a population of about 2.5 million currently, which is expected to grow by 20% in the next 6 years to about 3.04 million, which is quite phenomenal if you look at cities themselves. We enjoy a subtropical climate, about 280 days of sunshine every year, which is I've done these presentations in many other cities before, and audiences actually gasp when they hear 280 days of sunshine every year, which is quite phenomenal, especially if you're looking at Europe or even southern parts of Australia and so on. But as any growing emerging city, we are still coming to grips with our identity as a city. What does the city stand for? The Council of Tall Buildings and Urban Habitats called us the emerging high-rise hub in Australia, which is fantastic because we've got a lot of high-rise coming up at the moment as we speak. We're beginning to finally embrace the Brisbane River, and you see lots of development happening now around the Brisbane River as well. A couple of days ago, I was reading a news article which called us the lifestyle capital of Australia, and I kind of like that because that moniker has been around for a while, and it is quite true because, as I said, we enjoy this fantastic subtropical climate, which results in a fantastic, relaxed, informal lifestyle. We enjoy being outdoors. We enjoy natural breezes blowing over our body, and we have the climate to be able to be outdoors. We are an emerging leader in what is coined as subtropical urbanism, and this has only happened in the last sort of 8 to 10 years. If you drill down into the site itself, and I was talking about the significance of the site, the entire master plan extends from the Victoria Bridge all the way to the Gardens Point Bridge on the other side. So roughly about 1 kilometre stretch of the waterfront. The core integrated resort, the new build architecture that you see, that occupies the center of that site, and that is about 2.5 city blocks worth of development. And it nestles itself in the heritage quarter, the historic precinct of Brisbane. So there are about 8 different heritage buildings around the site that the new architecture, the new build, has to actually interface with. And that poses a big challenge in itself. So the narrative that we developed right at the very start, it's a way of us being able to rationalize and justify some of the built form and allow it to stand out against the backdrop of the Brisbane CBD, which, as you know, is pretty orthogonal. They are river-inspired forms, they are deliberately organic forms, and the narrative was always about trying to reference the morphology of the landforms and the gorges and the cliffs that used to exist, that continue to exist, even well before colonization. The towers themselves, they're seen as these sort of sheer cliff faces with crevices and cracks where greenery actually grows through into those cracks and crevices on top of tabletops and so on. And that's the general metaphor that we've constantly adapted and reviewed our design decisions against. So how do we go about creating this globally significant, achieving this vision of global significance and authentic Brisbane? Three key design fundamentals, 3 key design drivers that we've adopted all the way through, that we've held on to all the way through. One is about subtropical response, subtropical architecture. The second one is about heritage interface and how do you respond to that immediate heritage, the fantastic heritage context and the history that we have. And lastly, it's about benchmarking sustainability. And I'll unpack all of these in the following slides. So what does subtropical architecture mean? As I said before, we enjoy a really informal, relaxed lifestyle here in Brisbane with 280 days of sunshine. But most of the architects in the room will know what that means in terms of architecture. What you try and do architecturally is you deliberately blur the line between inside and outside, create these sort of indoor-outdoor spaces, balconies, verandas, covered terraces, shaded areas, and so on, where you allow spaces where people can, which provide shade and shelter from the sun and the rain, but at the same time allow these natural breezes to flow through. Because that's important, because the level of humidity that we have in Brisbane, you need to have those natural breezes flowing over your body. So creating these sort of interstitial transitionary spaces is fundamental to subtropical design, subtropical architecture. And when you walk around Queenswharf, you'll realize that each and every public space in that development, all of those public spaces, whether you're up on the sky deck, which is really just a metaphor for an elevated sky veranda, or whether you're down by the riverside at the base of Brisbane Steps in Queenswharf Plaza, or in Willem Street in the Port Cochet area, or the laneways and the malls, they're all completely naturally ventilated. They're all these interstitial transitionary spaces that respond to the climate. As you're walking through, you get the shade and the shelter from the rain and the sun, but then you have these natural breezes constantly flowing through as well. So really an example of celebrating Brisbane's unique lifestyle. The atrium is a really significant part of this. It is the main arrival point for pedestrians along George Street, if you've been to Queen's Wharf. It is an indoor space, and yet it is an outdoor space. And that's the success of of blurring that line between inside and outside. So it actually connects the 7 different levels of the developments together. But at the same time, it provides this fantastic arrival point, which references Brisbane. The external facade of the aluminum batten facade actually wraps internally inwards as well. It's completely naturally ventilated, glass lures on the top, and the design of the battens with the color and the texture and the patterning of the battens once again responds and references the Brisbane vernacular timber buildings. One of the key signature moves in the atrium is these beautiful large green stalactites that are suspended from the roof. Now these vary from 4 meters long to about 7 meters long. There are about 9 of them, and they've all been very, very carefully positioned and considered from a point of view of safety and design. Did a lot of work with Multiplex and Urbis and Fighter Green in terms of making sure we got this right in terms of the location of it and reticulation of services to and fro, structure, and all of those things that you need to consider when you're delivering it. So on the right-hand side, you see an early drawing of some of the considerations for those green stalactites. And that is really a signature piece. Now, that is not restricted just to the atrium alone, because that expression of using visible living greenery as a visible expression of subtropicality is fundamental to subtropical design and architecture as well. Right now, this has become a lot more mainstream in Brisbane now. But then if you look back to when we started on this journey about 2014, 2015, when we were designing this, it was still a big leap of faith for developers and everyone else to come on the journey and say that, you know what, we're actually going to infuse greenery and living greenery into the architecture and integrate that into the facades. But we've actually used over 20,000 native subtropical plants throughout the development. All of these plants were actually grown in a nursery in the Sunshine Coast a year and a half before they were actually delivered to site, so they were allowed to acclimatize themselves in the nurseries, and then they were delivered to site. And it's great to see that most of these areas, the greenery, even where it's actually facing west, because that was one of the big challenges that you're not going to have greenery facing west. But despite all that, it's still thriving and living, and that's really, really very successful. One of the innovations that we have in terms of subtropical design, subtropical living, is in the residential tower. We have a residential tower with about 650 apartments, 60 stories tall. The early wind studies indicated that traditional balconies below level 30 would really be untenable for use, so not a real meaningful, usable subtropical living space. So what we came up with was this idea of a winter garden above the sky deck level, above level 30. So what the winter garden does is it just allows us to capture this interstitial space between the external facade and an internal bifold door. The external facade, you can see those 2 large rectangular windows there, and that's a motorized lift and tilt window. So at the press of the button, those lift and tilt windows are motorized. They open up, allow fresh air to come in. They're connected to the weather monitoring system, so in case of inclement weather, they automatically shut. But then what that allows is it allows complete flexibility and livability for residents. You can use that entire space as a fully indoor-outdoor space, or you can close the bifold doors in between, and then it becomes a more traditional balcony. or you can close it all and you know, if the weather is inclement, then you can completely close it all and you've got a sealed envelope. So that was quite a good innovation, which was received pretty well in the market as well. So that was subtropical design. Let's move on to the next design fundamental, which was about the heritage interface. As I said before, we immediately, the core integrated resort in its immediate adjacency has about 6 heritage buildings. And what's challenging about these heritage buildings is that they're all of different sizes, different scales, different functionalities, different uses, different architectural styles, different materiality, you know, ranging from rendered brick to exposed brick to stone, and built at different times as well. So quite a variety of these heritage buildings. And one of our fundamental challenges was, you know, how do you create a singular response that is able to deal with all of these varying different conditions all the way through? And one of the strategies we came up with was creating this 2-story stone plinth, if you like. You know, most heritage buildings have a stone plinth at the base, a very traditional way of construction. So we thought metaphorically, once again, you've got all of this 40 to 60-story tower sitting on top. They probably need to ground on a stone plinth. So we came up with this idea of a 2-story stone plinth which wraps all the way around the lower podium. So singular unifying material that interfaces in a variety of different ways with the existing heritage context. And the stone that we used was deliberately a neutral beige stone. So it picked up on the warmth of the sandstone and the Brisbane tuff, but it's still fairly neutral, which allowed the heritage buildings to actually maintain their prominence. 3 different textures, finishes of stone within that. So it in itself had its own rusticated plinth base, which was made of split stone. It's a granite stone, by the way. It's a beige granite, it's not a sandstone. So it had a split face base, and then it was predominantly a honed finish with a dressed finish, bands of dressed stone, which reference some of the datum lines from the heritage buildings adjacent. So next time you go for a walk around Queen's Wharf, feel free to have a look at that, because I think it's fairly successful in the way it actually interfaces with all the heritage buildings. The upper podium, 4 levels of it, that's quite challenging as well, and that's challenging purely from the point of view of its sheer size and scale. As I said, 2.5 city blocks worth of development, and what we've wanted to create is a singular, once again, unifying identity, and that's been done by this aluminium battened facade, which wraps all the way around. And the aluminium battened facade itself is in detail, is quite simple. It has a very simple 1 meter primary rhythm of mullions, of fins, which provides sun shading. And then there's a secondary layering between that 1 meter, which kind of offsets, which creates a bit of movement and interest. And once again, all of this goes back to very subtly referencing the traditional Brisbane vernacular of timber architecture. The upper podium is actually quite important in that heritage response also, and that is really very evident in that corner of George Street and Margaret Street, where you see the photo on your right, you see Harris Terrace in the foreground. And one of the key heritage response principles that we've adopted is this of respectful contrast. What that means really is that acknowledging that there's new built form behind the heritage building, and that new built form is new. It is of its time. So we're not trying to mimic the heritage building in any shape or form. But it is respectful of the heritage building. It provides contrast, but it provides it in a respectful manner. So you see how the upper podium provides a really recessed backdrop, which allows that heritage building in the corner to actually maintain its prominence on the streetscape. And that has been paramount from a decision-making process all the way through. The towers have a very, very subtle layering of that heritage response as well. One of the questions I keep getting asked usually is, why is the color bronze for the towers? And this is why, right? The hotel towers in the front, the bronze color actually responds to the color of that heritage precinct at the base. It creates a unified precinct, if you like, and creates a marker for that unified precinct. So it picks up on the warmth of the sandstone and the Brisbane tuff, and then picks it up in the color of the glass, especially when the sun's setting in the afternoon. And then there's also another subtle referencing in terms of the positioning of the mullions and the sun shading elements. And there's a deliberate idea to use those that staggered kind of bonding to reference the stretcher bond that you would normally see in masonry at the base of the precinct. So subtle referencing to the historic context. One thing that we were clear pretty early on, 2014, 2015, at the start of the project, was that given the significance of the site, given the significance of the civic nature and the civic layering of the site, we wanted this to be a benchmark for sustainability for future projects to follow, right? Obviously, those benchmarks have moved on quite a lot. We're talking about 10 to 12 years ago now, right? But those benchmarks have definitely moved on. But at this point in time, it was quite a significant decision for the developers to take as well. So Queen's Wharf is the first Brisbane development to achieve 6-star Green Star communities rating across the entire precinct. All the new buildings, the new towers that you see, they all achieved 6-star Green Star design and as-built ratings. And all the heritage buildings, once they're all repurposed, will achieve 4.5-star design and as-built ratings as well. What does that mean from a facade perspective? The facade itself, because the glazing is obviously quite an important piece of the puzzle. 16,500 glass panels, 450,000 tons of aluminium. About 20 linear kilometers of aluminium fins used all around the podium. There were 3 different contractors that were involved in putting together all the facade and the glaze. 4 different contractors, actually, if you include the stone guys as well. But just in terms of curtain wall and glazing, there were 3 different contractors: Uanda, SRG, and G. James. G. James did all the podium works, and Uanda and SRG did the towers. So that was quite challenging, and this was all through the COVID period as well. So you see some photographs of the mock-ups. And because of this COVID, we didn't get to travel to China to see the mock-ups. The mock-ups were all done in Rockley in a backyard to go and have a look at. So that was quite an interesting process. But the glass, the performance of the glass and the selection of the glass was quite a challenge, because from a sustainability perspective, it needed to have a high thermal performance, a shading coefficient of 0.19 or lower. But at the same time, it had to transmit a lot of visible light in as well because of the depth of the towers and so on. So the VLT had to be 35% or greater. So there was a lot of research done in trying to get the right kind of glass with the colors involved as well in meeting those particular criteria. Another interesting aspect of the glazed facade is on the arc building on the insides, the concave facade of the arc building that you see in the photograph on the bottom. The facade there is deliberately faceted and splayed and broken up, and you've got these slab edges which project out as well. Because we've all seen those stories of the concave building in London where you've got heat actually reflecting and frying a car on the street. We obviously wanted to avoid that happening here. So we've deliberately broken up that facade, and it's not just about visual interest, but it's also about responding to that particular criteria as well. Good. So what have we achieved so far? Lots of numbers up there. Those are the tangibles that you see. I mean, 900,000 visitors per month. I mean, that's one of the fundamentals of what we were trying to achieve right from the start, and that's phenomenal, because if you look at South Bank on the opposite side, that is the premier lifestyle destination of Brisbane, and it attracts about 11.1 million visitors annually. But to get 900,000 visitors per month through Queen's Wharf as a development has been phenomenal. But also focus on what Queen's Wharf has achieved that is not really tangible, that is not measurable for the city. Queen's Wharf was one of the prime poster childs for Brisbane when it was touted for the Olympics, for example. And as I said before, it has changed the skyline of Brisbane. It's changed the experience of people along Brisbane as well, for the better, I would think. So it's a real example of transforming the city from ground up. I'm pretty close to finishing, but before I finish, I just wanted to give you a very quick, so bear with me, I'm just going to give you a very quick history lesson, only because it's important to acknowledge the historical significance of the site as well. It is the birth of a modern city after all. So that photograph that you see is from the 1820s. that shows the penal colony in the 1820s. Like many cities around Australia, Brisbane started its life as a penal colony. Some of the worst offenders from Sydney were being deported to the new colony, the Moreton Bay Penal Colony, 1824. The only point of arrival into the colony at that point was built in 1828, a set of timber wharfs. And those timber wharfs used to be called King's Wharfs in those days. And they used to be located right opposite the commissariat that you see there, that's highlighted there. The commissariat is one of two remaining convict-era buildings in Brisbane. There are only two left, and the commissariat is one of them. And the commissariat is where they would unload the grain and the ammunition and the guns and everything else and store it in there. And I'd like you to keep an eye on the commissariat, because 200 years later, you can still see the commissariat there. Obviously, it's dwarfed by the Riverside Expressway. It's hidden by the Riverside Expressway in front of it. And you've obviously got Queen's Wharf sitting right next to it. Queen's Wharf is, it's almost as a marker of that heritage precinct, of that beginnings of Brisbane. In a way, poetically, it kind of connects the past of Brisbane to the future of Brisbane as we hurtle down to 2032 to embrace our Olympic legacy. And at night time, it really comes alive, as I said. It's changed the perception of South Bank, of the city, of what people experience all along South Bank as well. And it's really propelling Brisbane towards becoming a global city. Thank you.
Thank you, Naveen, for that. It was really exciting to see how the facade translates the story of the project across three concepts, which is subtropical architecture, heritage interface, and sustainability. I now welcome our next speaker to the stage, Simon Barnes, Principal Building Envelope Practice Leader, APAC of Arup. His topic is delivering Olympic-ready stadium facades, the value of specialist integration and industry collaboration. He will explore how integrated structural, environmental, and fire engineering delivers high-performance stadium facades, drawing on global projects which include Optus Stadium, Santiago Bernabeu, and a Populous project, Kitech Sports Park. Welcome, Simon.
Thank you very much. I hope you can all hear me okay. It's a nice, snappy title for a talk, delivering stadium facades, the value of specialist integration. It's a very sort of Arup type of topic, but I think it's a topic that actually every consultant and every designer would feel really strongly about, and that is that we integrate the inputs of every consultant on any facade job, but in particular, projects like stadia. Quick introduction of myself and what I currently do. So APAC is Asia Pacific region for Arup. We have 130 facade consultants across the region in 17 different locations, and we work alongside 700 roughly technical specialists. So what do I mean by a technical specialist? I mean acoustic consultants, fire consultants, materials consultants, wind consultants, all of these highly specialized disciplines who contribute significantly to facade design across different projects, and often in really different ways. And so I'll get into what I'm going to talk about. So first of all, I'm just going to set the scene really as far as stadia are concerned. Stadia have been around for quite a long time, probably more than 2,000 years. And yet they have changed quite a lot in that period, and now require, due to a variety of reasons for different usage, specialist technical input. And that's very important in terms of synthesizing what the facade solution is. And then I'm going to talk, hopefully a bit more length than the first bit, about two key projects. One of them is Kitech Sports Park, and in particular the main arena there, which is a 50,000 person venue, and also the Santiago Bernabéu refurbishment, which is the one of the biggest soccer stadia in the world. It's an 80,000 seat arena, and that was a refurbishment. So, first off, stadia, have they really changed very much? Well, I suppose if you're going to a venue to watch any kind of event, whether it's gladiator combat or soccer, or even if it's a musical concert or whatever it may be, you need to be able to see the performance surface, so the playing surface or the stage or whatever. So obviously that creates raked seating, and if you surround that surface with raked seating, you're going to end up with a bowl, which is a key component of any stadium. If you have raked seating, you need to be able to get to it. So you can see in the Colosseum there on the left, there are lobbies which you need to be able to access your seats, and it's the same thing on the right-hand side. So on the right-hand side is Optus Stadium, which is roughly 10 years old. Then those lobbies that enable us to get to our seats, they need some level of enclosure typically. So there's a facade which wraps the whole thing. And then if we're in the bowl, if we're watching the event, generally we'd like a little bit of environmental protection, either from the rain or direct sun or the wind or whatever it may be, and that's the roof. So the Colosseum had a roof, but it wasn't made of high-strength steel because that obviously hadn't been invented then. So why, if all these elements are still the same, do we need specialist input? Let's see. So I think one of the main reasons is that rather than watching gladiatorial combat, we have moved on a little bit since then, and we do all sorts of different things in stadia. So of course we recognize sporting events of all sorts of different codes happen in stadia, but we also have increasingly large music events, etc., which generate quite a lot of noise and have a whole set of really different requirements. And this is where that sort of technical need starts to kick in. So the two images in the middle are both at the same location. That one's Rod Laver, so doing the tennis at the bottom, and then a gig up at the top. And the same is Marvel Stadium on the right-hand side, which you can see how it's adapted to a soccer use, where we're sitting behind the goal, but we're quite a long way from it. And then an Oasis concert last year. So what sort of technical specialists would assist with stadium design? Well, if a bowl is enclosed by a movable roof, then it becomes a very large enclosed space, and it's also got an awful lot of people in it. Under those circumstances, we need to consider fire, and we need to consider smoke management. That's really, really important. So clearly, the requirement for fire specialists is very important. And how does it affect the facade? Well, it affects the facade because you've got to get the smoke out through the facade. So that's kind of fundamental. Wind, you'll see here, this is Optus Stadium in Perth. It has a partially open enclosure, and that's very common for the sort of circulation areas behind the bowl. And they're often naturally ventilated. They need to provide a variety of levels of protection in terms of comfort and the environment there. And therefore wind is really important. But wind is also important from the perspective of the bowl itself and the protection offered by the roof and so forth. So wind is an important contributor. Acoustics, I'm going to talk a lot more about acoustics, particularly in relation to Kai Tak in a minute. But obviously, if you have music venues in a stadium and you have residences near a stadium, you need to address the issue of acoustic protection, and that can at times be quite extreme. Lighting from broadcasting purposes, lighting the playing surface, lighting the outside of the stadium, recognizing the fact that it's a very large object. A thing that you fit 80,000 people in isn't very small. And if you clad it in the wrong material that happens to be very reflective, that can be an issue. So reflections, daylight, all the rest of it. Then, of course, light to the pitch, daylight to the pitch, making sure that the grass can grow. Security, materials, and many, many others. So clearly, technical specialist inputs are really important to successful facade design for stadia. So let's get into the examples. This is Kaitak Sports Park. It's a project that we did with Populous, fantastic project. And I'm going to talk predominantly, well, exclusively actually about the stadium, but the whole development is a lot more than that. There are a number of different venues and playing surfaces and so on in there. And it's located in Kowloon, Hong Kong. On the left is Victoria Harbour. There's a huge window from inside the bowl. You can see views out to the distance from inside the stadium. It has a retractable roof because it hosts multiple venues. And it's surrounded by, like most places in Hong Kong, a vast number of dwellings, lots and lots of high-rise dwellings. Now, the history in Hong Kong is that the previous main stadium was in Happy Valley, and it was regarded as problematic from a noise perspective. So the brief for this project had some fairly extreme noise abatement requirements. So just some, I've already mentioned how many seats there are in the stadium, but yeah, it's big. So acoustic performance as a driver of facade design for Kaitak Stadium. So the briefed requirements for acoustics here, I've articulated them in terms of sound transmission class, which is a ASTM-defined number, but it just enables me to compare the different build-ups. So there's a fixed roof number, 61, retractable roof, 63. The envelope structure, that's the wall, that's where the facade's attached to, 78. And the glass facade is 40. Now, a typical internal wall in a dwelling is 35, so to put that into some level of context, that's a stadium facade that's got to achieve a very high level of sound attenuation. So how do you do it? Well, you can see that even at sort of very small scale, it creates some very, very big build-ups. Why does it create such big build-ups? Well, in stadia we have large spans, so large spans don't particularly like lots of mass. And typically with acoustics, we tend to introduce lots of mass in order to control noise. So concrete would be a perfect material to meet some of those noise control requirements. But of course, concrete's not a brilliant material for a stadium roof, and nor is it a brilliant material for a facade. So the solution was to maintain within strict weight limits the roof build-up and the performance, and the similar sort of strategy applied to the walls was to have a very big air gap, or multiple air gaps. So we have, at the top we have metal deck, we have anti-drumming material, we have mineral wool, we have plasterboard, we have a very big air gap, that's about 800 mil. And then we have further sound insulation and more plasterboard down at the bottom, and we also have some noise absorption. And of course, because we have moving panels to enclose the arena in the event of either extreme weather or a noisy sporting event, we have to seal that. So we have some pretty enormous gaskets you can see highlighted in yellow. That's where the two roofs meet, which is along the length of the pitch. Lots of challenges there, and you could not design that without having significant acoustic input. And of course, the whole thing needed to be tested for transmission, so we're talking about walls, roof, operable panels for sound absorption, rain impact noise, and actually after the thing was constructed, there was a series of site tests where, I'll call them microphones, but noise sound recording equipment was placed 300 meters from the perimeter of the site, and you could see how big that site was. But that's how much scrutiny was placed on the acoustic performance of this building. So that's one story about Kaitak, but of course, that's only part of the story about the facade, because the facade also contains a multitude of triangular panels and is doubly curved. How do you do that? 27,000 panels form the doubly curved facade of Kaitak Stadium. That's an awful lot of panels, but originally it was quite a few more. So this is the original sort of geometric set out which Populous put together. So it's a very kind of rational way to define the building envelope. It's, as I say, a doubly curved surface, but it's composed of vertical arcs that then are curved on plan. So what that creates is a series of different horizontal length panels up the height of the vertical arc. Makes sense, right? In order to meet this requirement and this requirement, there was a specific pattern created by the architect, which is composed of really two types of triangle. And that prevents the joints being in very specific and monotonous directions. So you get this sort of diffuse nature of the joints. And that's a great strategy. It's very rational because it allows you to fold the panels in all sorts of directions, and it meets the surface geometry requirements really well. The trouble was that the height of the panels, so up the height of the arc, was quite small, and that created about 45,000 panels. So there had to be a rationalization of that through our engagement with industry, our engagement with fabricators. So the answer to that was simply to increase the height of the triangular panels so it was a more faceted solution up the vertical height of the arc. But it still achieves that sort of fairly uniform surface that seems contiguous. So with that level of rationalization, we were able to take the number of panels down to 27,000, still quite a lot. But we also had to develop a method of fixing that was capable of significant adjustment, and also that recognized the fact that this has to be a wall that meets a very, very high acoustic performance requirements. So here we have panel rationalization in order to aid procurement and construction, and we have the whole thing informed by technical specialist input, which in this case was acoustics. I'm going to move on to this project now, which is really interesting. This is in Madrid, Real Madrid Stadium. It's a refurbishment project. This is a visualization, and you can tell it's a visualization because it looks like almost a continuous piece of stainless steel wrapping the stadium, which of course can't be achieved. What I'm going to try and do in the next few minutes, about 10 minutes, is to condense a talk that was given by some of my colleagues from our Madrid office. It actually was a technical paper, which is fantastic, and I'd recommend you all have a read of it after this. It was authored by Adrian Ruiz, Matias Garcia Del Val, and Jordi Alcaine, who gave me a lot of the images and the collateral for this presentation. But what that paper does is explain much more articulately what I'm about to try and explain in about 5 or 10 minutes. And there's obviously a hell of a lot more work in it than I'm able to articulate in that time. I should also mention the architects. It was a joint venture architectural design by L35, GMP, Architekten, and Rebas. So, what's so interesting about this one? Well, as I mentioned before, it's an 80,000-seat soccer stadium. It's almost like it could be considered a cathedral for supporters of Real Madrid, and I'm not one of them. I support a different team altogether. Won't go into that. It has 13,000 unique stainless steel blades on it. So we were just talking about how to rationalize the building envelope to suit procurement for large-scale application on a stadium facade. And here we are with a project that's got 13,000 unique stainless steel blades in it. How on earth can that be possible? 50,000 square meters of it. Okay, so what are the interesting technical drivers around the facade here? Well, obviously, first off, we had to establish a rational set of facade components. This is stainless steel, and those of you who've been involved in the design of any building clad in stainless steel will know it's potentially quite a reflective material. So the assessment of reflected glare was really important in respect of this building. It's a semi-open enclosure, so the way that these things respond to wind is actually quite complex. It's not as easy to assess as a equally permeable building in a wind tunnel. So there was a wind tunnel test for this, but there was an awful lot more that went into that. So we've got wind, we've got reflected glare. And then I think if we talk about industry collaboration, we have scale. So we have scale and complexity. So we can't just go to tender and expect somebody to come back with 13,000 uniquely shaped stainless steel blades and say, yeah, I'll do it, no problem. I do it all the time. That's not going to happen. So we needed to collaborate with industry. That's a big scale manufacturing task. And then, of course, we have to manage quality. You remember the visualization which made the whole thing look like it was a gaming console. It's a building, and it's made of things that are rolled in mills and fabricated at different times by potentially different people. So first of all, trying to get to grips with the architectural concept. So the best way really to understand it was to think of the blades in terms of their parameters. So what we have is a series of horizontal blades that are changing their geometry constantly as they go around the building, such that every single one of them is different. But if we think of it in terms of parameters, or the properties of the blade, we can see that we can start defining that by thinking about the angle between the top and the bottom surface. We can also think about the length of each surface. All of these things vary. And we can think about the relative angle between both those surfaces and the structure that supports them, which is facade-specific steel structure at 7-meter centers. So we had to do that parametrically. There was no other way to define that, not practically. We then had to think about how the components go together. And obviously, there's still space for a bit of a hand sketch, which is very gratifying to me because that's my field of technical expertise. But what the hand sketch shows us is that we have a series of components which enable us to deal with that level of complexity. So we have a horizontal circular hollow section, which we'll call a spine. On the spine, we've got a collar. The collar allows us to rotate and fix a series of ribs. Each rib has its own unique geometry. And then attached to the ribs, we have stainless steel sheet. And that has to be attached invisibly, of course, because we have to support it at multiple points along its length because we're twisting it. So the stainless steel has welded studs on the back, but it also has structural sealant and a channel to attach it to the rib. And that whole thing creates a 7-meter long strong back panel. The strong back panel has 4 stainless steel components, sheet components attached to it, because obviously 7-meter long stainless steel sheet is not a freely available commodity. So just getting into the analysis briefly, and this is sort of probably 15 pages of the paper, and it's worth an awful lot more than the time I'm going to dedicate to it, but let me try and summarize it. The reflected glare component of it. So why is that important in the design and geometry of the blades? Well, 2 things really. One, obviously, is the orientation of the blade. At different orientations, that blade will catch incoming direct solar sun and reflect it back, mostly to neighboring buildings, because the top surface is sloped. If you have high angle sun, it comes out quite horizontal angle, much more than it does on a vertically clad building. And we know this because we experience this on lots of other buildings around the place, and some even in Australia. The second thing that is controlled by that analysis, or is informed by that analysis, is the surface finish. So stainless steel, we can polish it, we can brush it, and a brushed finish is beautiful and is often preferred for a whole number of reasons. But in the case of reflected glare, it's not particularly good because it's so flat. What we need is a bit of texture. So what this study informed and actually led to was the selection of an embossed finish on the surface of the stainless, because an embossed finish will break up the reflection and greatly reduce the surface luminance. So that's what these diagrams are on the left. The top one is brushed stainless, 760 candelas per meter squared. And the one on the bottom is the textured, the rolled pattern, and that's down to 217 candelas per meter squared, significantly less. So that process, that analysis, that specialist input informed the material selection and the geometry of the stainless steel. The tiny little images up the top, that's all about wind, that's wind pressure. So of course there was a wind tunnel test. I think I mentioned it earlier, and there's a picture of the model there, bottom left of those 4 little tiny images at the top corner. And that was, obviously models tend to be constructed at a fairly small scale, and the level of detail and variance in these blades is really quite tiny scale. And so there was additional CFD modeling undertaken to address particular wind directions and particular geometries of blade to validate really what the wind tunnel was telling us. And as it turned out, those CFD analyses showed that the wind tunnel, if anything, was just slightly conservative. And therefore it was reliable. We also looked at turbulence and we looked at comfort in relation to wind. So again, we're talking about the the lobbies into the bowl and the comfort of people in those locations being an important driver. Okay, so that's the digital process informing design with a lot of specialist input. If you move now into trying to make that a reality, that's a whole nother level of challenge, and that's why engagement with industry, with fabricators, with suppliers was so very important. Now, this is an image of the visual mock-up, or a visual mock-up, one of many, required for the project. And this was massively important because the range of finish, or the range of appearance in stainless steel, which comes from 3 separate fabricators and is produced in multiple batches, can be significant and needs to be thought about and needs to be understood by the client. So building something this size was actually really important for the project. I'm going to talk quite a lot to this slide because I deleted a few other slides to try and make this as short as possible. But these are just some of the other samples that were produced. So you can see this is 1.8 mil thick stainless steel with an embossed finish. Another piece on the top. So that's a typical strong back, and you can see it split into 2 lengths of stainless. The diagram in the middle, that's related to batches and manufacturers. So the different colors represent different batches of material and how they're dispersed across the elevation. So if we had simply allowed that to happen accidentally on the facade, we might find that we'd have a big block of dark somewhere and a big block of light somewhere, which couldn't be further from the visualization that we looked at the beginning. So obviously very, very important. And the other thing that was obviously, I would say, fundamentally important to this process was because there were 3 fabricators and because there was so much variety in the size of the rib, the shape of the stainless steel, we had to use the digital model as the source of truth for the fabricators. So there had to be a process of information exchange digitally between the design team, which involved lots of back and forth and clash detection and validation through structural checks and so forth of all the geometries before it was then exported to the fabricators, who would then translate it into whatever SolidWorks, whatever software they use to create their cutting patterns. Because every rib was different, every surface of stainless steel was different. So that's saying, okay, well, you don't really have to you don't really have to make things practical, you can do anything. But obviously it's a unique project. I wouldn't suggest that this is what we do for every building by any stretch of the imagination. But it shows what can be done. One last thing, Because you have 3 fabricators, and because you have such an enormous area, getting the quality right was also extremely important, and getting the quality consistent. And of course, measuring things that are warped and twisted surfaces is really difficult, especially if they're all different. I mean, you can't really use a template if every panel is different. And so we use 3D scanners. And we agreed a level of tolerance at specific vertices on each panel. And that enabled them to, once they got on the building, appear reasonably seamless. And I think the result is pretty amazing. But you can see the difference in tone dispersed across that elevation. I think it's an amazing project, but wouldn't necessarily recommend doing it for every project. Now, this is just really in summing up. You know, we talked about the importance of collaboration in this talk. So the importance of collaboration not only with technical specialist input, but also with industry. I think they're both as important as one another, particularly for large-scale projects. And clearly, technical excellence is part of that. You have to take a step back sometimes when you're designing something and think about the bigger picture. And the bigger picture, well, that's the curiosity part. And then the bit at the end, the digital innovation in delivery is, well, the things that you think are impossible can be possible if you embrace digital innovation. So hopefully that was of interest, but that concludes my talk. Thank you.
Thank you, Simon. Your last slide says it all, that for complex and large-scale projects, it really takes expertise, intelligence, and collaboration between different disciplines to prototyping to achieve design intent. I now invite our next speaker, Michael Lette of Lysaght and Fielders, to speak on the topic of elevating facades, freedom in design, confidence in compliance, efficiency in delivery. In his topic, he'll explore how design flexibility, NCC-compliant engineering, and efficient off-site manufacturing can come together to deliver bold, durable, and future-ready facade solutions. Over to you, Michael.
I'll try to make this a reasonably quick presentation so that we can get back on time. There's going to be a lot of photos and things like that, so we can sort of rush through them quite quickly, and hopefully everybody can read quite fast as well. So essentially, I'm going to sit there and do a presentation on design, compliance, and performance. For those that don't know BlueScope Building Products, we're part of the 4 downstream businesses within BlueScope Steel. You've got the steel markets, you've got the BlueScope Building Products, which Lysaght and Fielders are a part of. Then we get into flat steel products and pipe and tube. As I said, I'm not going to do a lot of reading, but the construction landscape is rapidly evolving, and we're going to focus on 3 key areas of focus, and those being labour, which is obviously something that's quite expensive in Australia, design and compliance. Okay, our approach, where we assist. So we're looking to sit there and help with timing and efficiency. So a lot of our panels now are all made by robotic machines. Some of our panels take roughly 40 seconds to produce. You've got design freedom, limited design freedom. I've had to sit there and put a lot of design freedom from a lot of designers occasionally that have gone too far. And then we've got obviously compliance, and we'll do a section on where we sit with the compliance a little bit later. For those that are wondering what colour this is Umbriel, and it's a soffit for one of the case studies that we're about to run through. Okay, so why early engagement? Consistency, less structure, prefabrication, and obviously to reduce delays. As you know, most projects don't tend to start on time, just like today's event. And it's basically something that we have to sit there and try to come back to, right? So we've got to try to make, to grab time. And the big part of it is also collaboration. As Simon mentioned in the previous presentation, is a big part of what we do. So, where we sort of fit in. The projects that we were looking at were the Armadale upgrade line, which was essentially 5 stations from in WA that ran through, and then the Byford Railway. Western Sydney Airport, that a lot of people are familiar with, we used the horizon panels, and these were large Soffit panels. The shed in UTAS in Tasmania was the Aramax. The big sections there are basically a reduction of steel structure, and I'll go a little bit later. Okay, so where we sort of fit into things like this is a large, you know, we're well and truly on projects way before we even start. The robotics help to sit there and gives accuracy in panels. As you know, with a lot of facade panels, if you're hand folding and things like that, there's a lot of, it's, you know, what part of the day have you turned up, how good is it, you know, what you're feeling and things like that. Our robots, as you can see here, we did 2 large canopies on this particular station, which is Cannington, and that colour is Copernicus. We've got large, sort of 2.5 to 3 metre by 1 metre panels that were put up over the top of the railway. With the early collaboration, we also sat there and designed a lot of product where flashings were going to be introduced, but we took the flashings out and we actually made the panels and the flashings together. So we're actually blending the 2 designs. This is just a really quick image on that we can sit there and do a lot of, you know, lightings, vents, GPOs, signage, cameras, all of the accessories that you need on stations can be actually post-fitted into these panels. This is just a quick shot on just how simple and how clean Azure looks. Okay, so it's an open jointed system, it's a coloured screw system. You don't see the screws. If you look hard enough and you blow some of these images up, you can only see the screws directly in front of you. The rest of it blends in a 25mm joint. Okay, design freedom. This is the Armidale station, so we actually did a lot of brand new products on this and a lot of new features. So concept, design, fabrication, installation. Okay, and where we fit into it. So Azure on the Armidale line, we've got a very, very high tolerance now with robotics. As anyone's producing robotic panels right now, it's a very, very high tolerance. So our panels are manufactured, and this is what surprises a lot of the installers, is that you're getting panels that have a 0.5 mil out of tolerance, possible 0.5 mil. So when you put these panels up, which is why we sort of call them very much a lift and fix scenario, if you can sit there and put the top hats in the right places, these will go up really, really quickly. We've got other products, as you can see, so you've got a kaleidoscope, so that's where your design and your freedom of design can come through, which is as if we can fold it on a piece of paper, you can fold it on a machine. Aramax, the big standout there is the 20-metre clear spans. You know, that's taking out a lot of structure. These are very, very large profiled panels, and they can also be perforated in aluminium, so you can get them in the steel, aluminium, and in stainless. These are some of the pictures from the Allure project in Perth. We're looking at some of the coffers that were down in the lower stations. This is in the Armidale up on top of the viaduct system, so we've done all the Sophites that you see there, which are in the umbrial colour. We've got the monument service booms that are running through, and then we've also done all your station rooms, and they were actually pods that were manufactured off-site and then brought into, so we just clad just the surrounds on those panels. This is just some more sections of where we had to marry 500mm panels through with 1 metre wide panels. This is where we had to introduce soft curves. So the idea here was that the architect had the masonry panels up the top, and they wanted to know, could we curve a steel panel? So as you see in front, we've got there's one and then there's another one. So these curves were all not 90 degrees, they were all slightly different, and they were all rolled in 1.2 steel. And then we put the braces on the back, and then we basically installed them so they came straight off out of a crate and straight on the wall, straight into place. We've also sat there with integrated lighting and lighting systems. So you can see where we've gone through panels and we've taken the strength out of the panels. So we've had to engineer the panels in such a way to sit there and support all the lighting systems. Again, this is just blending with other materials. And then we get into the compliance side of things. Okay, what we test at Minchinbury, we've got our own NADA certified, as you've probably read before. We test for structural strength. We test for cyclone testing with fasteners and connections. Obviously, it's a big part of keeping the panels on the wall. Fire compliance and performance, so we meet all your NCC and AS requirements. We also weatherproofing, so we do that with a lot of panels. And with the ZUR in question, we completed the AS 4284. We had fantastic performance and results in very, very high wind loads. And that was done through using our friends over there at ProClimate, which you're going to hear about a little bit later on. Okay, so we just
industrial research is very unique and very different. So our job is to solve real-world problems.
We are not only a world-class testing facility, but we also are a provider of innovative building solutions.
The capabilities of the team include business as usual support in regards to technology, engineering assessments, supporting manufacturing and quality. We also, of course, work on new products and product improvements, so it could be identifying a gap in the market or our product offering and addressing that.
The benefit of having this facility is to give the customer certainty that our product will work and touch and feel.
R&T facility at Minchinbury gives the architects confidence to push the barriers of their designs. Then we can run them through the testing facility.
We have a lot of different people in R&T. We've got the very experienced, older members of the team. They know just about everything that we've done before. They remember the things that we've tried, the things that did or didn't work. And we've got the structural engineers who are experts in their field. We have the compliance experts as well that really help us to deliver solutions that perform, all right, and comply to relevant building codes. And that's really, really important to every technical piece of work that we do.
Really excited about growing the use of colour-bond steel and really how people build in Australia. We've got a massive opportunity to change how people build and how people use steel. And I see that's really important and way we can use new tools and new technologies to grow the use of steel.
Okay. Why we tested at Armidale? Obviously, we needed the biggest part of Armidale and the stations was impact. And that's why the architects and the builders and the client chose steel. 1.2 steel, as you saw in that test before. That's 107 kg 4x4 piece of timber with a steel plate on it being shot straight into our panels. So, that was probably the big test for the architect. There's not too many people that can kick faster than that in Perth at the moment. So, the other thing too is being the robotics, and also because we did a lot of work up in the early days, was the very, very top of that elevator. All those panels were put in place before the elevator actually made it to site. Okay, so it was like the elevator was actually removed, and then when it was placed, it was just placed in perfectly. Okay, these are just some of the pictures of some of the stations. Some of the stations where we've gone further down through the stairwell, so we're obviously dealing with the public areas and things like that. Okay, the value of steel brings to every project. So, built for speed, a little bit like this presentation. We've got a little bit of design creativity, and we've got some flair, and we can sit there and make things happen. So it's really nice to go to designers or engineers and say, okay, they're looking for a particular design. I ask them to sketch it, and if I can sit there and literally produce it in paper, we can nearly produce it on a machine. Proven compliance, as we've shown there. Okay, so the big areas of where we've done a lot of Azure was in those public sort of crash slash, it's probably a better term to call it, engagement areas. But yeah, that's where the Azure really stands out, because it can be actually fixed and replaced as well. All these panels can be replaced at any time, at any place. And that's pretty much it. So we also do interiors as well, as you can see here too. So yeah, should it ever get there.
Thank you, Michael, for sharing the case studies across the 3 different panel systems. We have our next speaker now, who is Bernat Miñana, Managing Director of Frontek Australia. He will present case studies demonstrating porcelain cladding and unitized and complex geometrical applications. Please welcome Bernat.
Hi, everybody. Thanks for your time and attention, and apologies when I speak English, sounds like Spanglish, but I think we'll understand each other. So Frontek is the product I'm going to introduce. They are porcelain panels made in Spain by one company called Grupo Greco-Gres. We are a long tradition company, so we've been making ceramics since 1940. We started doing some very traditional ceramics like bricks, roof tiles, or traditional clinker tiles. And from there, we evolved into the porcelain panels that we do now. You have here a view of our factory. We pay a lot of attention on the environmental side of it. We have our own power plant. Everything nowadays is automatic. People, when they come to the factory, they ask where the stuff is. No more stuff. Everything is done by robots or machines. As I was mentioning, we try to be as environmentally friendly as we can. We have our EPDM for the ones of you that want to know the real values, the carbon footprint, and everything. The only thing that we will improve soon is changing the gas kiln into a hydrogen kiln. But as of now, the gas burning is the only part that is not so friendly. The question we hear most often in Australia regarding our panels, our cladding panels, is this terracotta or ceramic? That's a wrong question. That's like asking if this is water or moisture. Ceramic is a wide term. Porcelain is a quality of ceramic. So ceramics are produced by one industrial process called sintering, that what does is bonding particles with a combination of pressure and temperature. I'm sure many of you have heard oh, how much water absorption does your ceramic have? So the ceramic absorption, because of dirt and because of the absorption, and makes sense, but in the ceramic world is the evidence of how good is the sintering. So if the sintering is very poor, like you see here in the low, the water absorption is going to be very high because there's a lot of space in between the particles. If the sintering is very good, there will be close to no water absorption. So when we are talking about water absorption, it's not how porous or dirty it will get, it's how good is the ceramic. So when you ask about ceramic quality, ask water absorption. To be porcelain is to be under 0.5. If it's not under 0.5, it's not porcelain. Let's go to some projects. You can see a few projects here. Many of our projects are clad on site, but because this is a facade technical presentation, we're going to focus more on the projects that they are unitized and they are installed like a typical curtain wall. So this is Miranda, is a small hospital in New South Wales. We send the panels to the factory. They use our system to fix it into modules, also the ceramic baguettes, and then they will clad into the factory, hanged with a crane, like most of the unitized system projects that all of you will do. This is something similar. The difference here is that it's a vertical configuration. As you will see in many of the projects, there is no problem in fixing the panels horizontal, vertical, inclined. You will see a few of them, and the overall results tend to be very nice. This is a project in Melbourne. It's a unitized project. The architect wanted to have a feature with some angle in the facade. So even the modules are rectangular. As you can see, there is this kind of band with a subtle effect of combining different batches of sandstone or different beige stone cladding. This is Macquarie student accommodation. This is one of our most iconic projects in Australia to date. We were lucky enough that when we were doing a presentation in the architectural office, they were defining the materials, and they realized that because Frontek is produced in rectangular shapes, doesn't need to be clad in rectangular shapes. All this project is most in triangles and in 2 levels. So you are achieving the effect of a sandstone, but with much more flexibility to clad it to a light structure. You will not have so many problems of batches, colors, potential fractures in the stone slabs. And the final result is pretty good. Even looks very bulky and very heavy. Everything is light galvanized structures that they are fully mechanically restrained with stainless steel brackets. This project is Frankston Hospital in Victoria. It's a Batesmark Conrad Garget design project. SRG were the facade contractors. Here they made it even more complicated. You will see that you have some vertical cladding in the modules combined with some horizontal cladding in the modules, 3 different colors and patterns, and the final result is quite good. We're pretty happy of how it worked. This is Warren Mahoney, is the Needham Hospital in New Zealand. This project is very special for us because we are very proud of how we achieved the design intent of the architects, but what I want to introduce here that is maybe more relevant for you guys is like this project needs to withstand earthquakes. So this project has been designed for seismic performance. So the modules were a cooperation between some facade consultants in New Zealand and us, so that the porcelain panel can move within the frame. So this has been designed so that it can withstand a plus minus 50 mil interslab movement. So that for porcelain, that is a relatively brittle material, is quite a good achievement, and the design is quite good. This project is 33 Alfred Street. 33 Alfred Street was the first skyscraper in Sydney. In the original design, it was using a 30 mil by 30 mil glass mosaic. So when the architects, John Pilton Walker, they did the renovation, they wanted to use the same proportion, but in a 10 scale. What it was 30 by 30 mil, now is 300 by 300 mil. If you pay attention to the facade, you will see it's quite seamlessly installed. You see there's not a lot of space in between modules. When you clad in unitized, you need to have some expansion joints for movement. They made it pretty well distributed so that you cannot see the joints of the modules. So guys, I had 15 minutes, but I have gone so fast that I finished in 7. So thank you very much for your time and appreciate the opportunity.
Thank you, Bernat, for that. We are now going to have a few words from Todd Grice and Balesh Balashan on the Society of Facade Engineering.
Good morning. We won't keep you long between your coffees. So just as a quick plug for the Society for Facade Engineering. So for those who are unaware, it's originated in the UK in 2004. It's a combination of, or an initiation between the Royal Institute of British Architecture, CIBSE, and iStructE. And so for Queensland, Balash and I are committee members, and this is a bit of a call to arms, if we can, to get some more people involved. Come out and have a chat with us at the break. What the Society aims to do is to have both education, pathway to chartership, which we are working on in Australia as one of our committee groups in terms of talking to Engineers Australia. Currently, facade engineering is not recognised as a sub-discipline. Some professional development and access to resources, and leading the industry. So if you want to become a member, you can be either a student, an affiliate, or you can apply for your full membership and become a fellow at a later date. There's a process. If you want to have a chat about it, come and grab Balash and I. At the moment, for Queensland, for this year, we're looking at pulling together a couple of city walks, which we'll go around and people will talk about that. So if you want to be a presenter on that, please come and have a chat with us. Also, we are doing a combined CIBSE SFE technical presentation on air infiltration, And there's a couple of manufacturers who would like us to do some walkthroughs in their factories. So if you'd like to be involved, please register. Thank you. Yeah.
And also a couple of working groups, we are working on that one. Especially I want to mention New South Wales Design Practitioner Act. We are putting some feedbacks on Society of Facade Engineer, and also we are pitching the business case for the Engineers Australia to make us the facade engineering as the practice into that. So a couple of things we are working in this as a Society of Facade Engineers. So probably this is the recognition for the facade engineering into that Australian market and to make our field is the safe and to the public. Yep, thank you.
Thanks to all our session 1 speakers. We are now going to take a break. Please take this opportunity to visit all the sponsors and their booths. We'll reconvene at 11:20 a.m. Welcome back to session 2. Oh, that got loud. I'd like to welcome our first speaker for session 2. That's Todd Grice, Director of Blight Rayner. His topic is, why do facades keep leaking? In this session, he will draw on global forensic experience to examine why leaks persist despite tighter legislation. And he will share practical lessons from diagnosing, repairing, and extending the life of existing building envelopes. Please welcome Todd.
Morning. I'm Todd, if you haven't met me already, outside. I'm Director of Facades at Blight Tanner. This is me and Tom hanging off the top of 1 William Street a couple of years ago, so I try to get out of the office when I can, and that means that I've learned a thing or two about leaks and failure investigations on buildings. So at Blight Tanner, we offer services in all aspects of facade engineering: architectural design, contractor engineering, remedial and diagnostics. And this has been a conscious effort to establish a team this way. And it's been interesting growing the team over the last few years that we've achieved approximately 1/3 of our revenue in each one of those subsectors. And there are several reasons why this model creates such a resilient team, but one key benefit for both individuals learning and the group performance is creating meaningful feedback loops between each service offering. So put simply, between those 3 subsectors that I mentioned, what are we designing now, and how will it impact the contractor work in the short term and our future remedial investigations? What are the pinch points for contractors? Where do the costs sit, and what are the details that are high risk? And how do we get them right? And this impacts both how we should design things better from an architectural perspective, but also areas to watch in the future for future failures. And what are we seeing out there now in service failing? And how can we change the way that we design and build? So when it comes back to feedback loops, as a greater industry, it's a key area where I think we're getting it wrong. We're not feeding back this information to each other. And why is that? Probably because it's pretty costly to fix facade leaks, and that often means it goes legal. And so if it's legal, it's generally confidential. So we don't want to share that. It's also pretty embarrassing to put your hand up and say, I've stuffed up. And I think generally as an industry, we're pretty poor with sharing information around it. So this lack of learning is a contributing factor to the fact that water leaks are the leading cause of defects in Australia, both in apartments and commercial buildings, and they account for about 80 to 90% of building defects. And that costs building owners and insurance companies about $3 billion annually. So it's not a small problem. So my hope is that I can be a bit of a feedback loop for you today and share some insight into what I've learned over the years and why buildings keep leaking. And I thought it'd be appropriate to break this up into 3 different sectors. So the design portion of it, installation, and then service life and maintenance. And I've got a 4th one at the end, which is where it all went wrong. And that's a bit of fun. We'll have a look at that at the end. So design. There are some key risks in the design phase for future water infiltration issues. Number 1, I would say, is interpreting AS 2047 and 4284 test reports. And many of these are not interpreted correctly, or they're missing so much information to protect the manufacturer's IP that it doesn't make it onto the project. And there are key things that are missed. A second thing would be missing details, especially for complex geometry. Misuse of materials. And systems, poor durability selection. An example of that would be permanent formwork being used as an air barrier behind a rain screen cladding system. We've seen plenty of leaks from those systems. Budgets not matching the project. So for example, the design team not having enough time and budget to get the design right and document it correctly, but also the construction budget not matching. So you're then basically pushing it all onto the contractor to get it done for less. An example of that would be residential buildings. They often have the tightest cost constraints, but yet have multiple facade types in comparison to, say, a commercial building. Poor coordination and accountability, and rinse and repeat in documentation. Those are some areas that I think would get it wrong in the design phase. So if you distill this down, there is a significant issue, I think, with also the training of facade engineers and consultants. Australia has no formal qualification for facade engineers. In fact, it's not even recognised as a subsector under Engineers Australia. Most of us are sitting as structural engineers. And therefore, if you have no way of knowing if the engineer or consultant who's potentially putting your F3P1 report together, I don't know why we keep jumping forward, putting that together is capable and knowledgeable of doing so. So, now we can move on to this. This is a practical example. So, this is a punch window for a residential high-rise window replacement, where the substitution of a custom subsill has resulted in some widespread water ingress across the building. So you can see it's a pretty standard window system. You have a sub-framing arrangement, sub-head, sub-sill, sub-jam. You've got a fixed light on the left and an operable scroll hinge awning on the right. Apart from the modified subsill, all other components had been previously tested in an AS 2047 test and had passed at 600 pascals. So the modification to the subsill was largely the same, and it fell upon the original designer to take responsibility for that. So once it was installed and it started leaking and the original manufacturer had brought it out onto site, they said, well, that's not our subsill. Who changed that? And that fell back onto the person who did the F3P1. So we got involved in doing a peer review for this, and it was decided that we'd take an exact replica of what had been installed on site and do our own 2047 testing. And it failed in multiple locations. Some of these were installation errors, as they put it into the rig incorrectly in comparison to what had been done on site, but majority was driven by this subsill modification. And we found that basically at about the 3-minute mark at 600 pascals, we would get this. What the problem was is that there was insufficient drainage in the subsill and it was building up. And then all of the other components within that facade that were already on the borderline of failing just got pushed over. And the solution here was simple, just to install more frequent weep holes, and the problem disappeared and it passed. But what's interesting is that that cost for that project was $1 million to rectify. The test was about, and the consultants involved in doing that, was about 2.5% of that. And so you get this order of magnitude. So the key takeaway from this, pressure equalised drainage, there is no theoretical way of calculating that. Yes, there are vent to volume ratios, but the reality is you need to test. And if you're doing a project-specific modification, then you need to do a project-specific test. Installation. Some prime issues in here. Sequencing of trades. That's a massive problem. Lack of understanding and knowledge for those people who are actually putting those systems in. Cost and budget constraints, we talked about that before. Don't want to reveal all my secrets too early. Subcontractors going bust during the works, that's a real challenge, especially lately. And similar to facade engineers, qualifications of installers. You know, of course we've got glaziers and whatnot, but when you look at cladding installation, the closest trade to that was carpenters. So that becomes a really interesting one. So the case study for this is a 20-storey resi unitised curtain wall where on the right-hand side at the stack joint, the gutter splice wasn't installed. And so the whole curtain wall is starting to rack and that shears the 4-way joint at the back. And that's pretty much happened across all levels. So you've got massive amounts of water ingress from that. As that racking system occurs, on the other side of the building where it's up against a shear wall and you've got a jam arrangement, that just starts pulling away. So all of these are basically caused by, the gutter splice is there. You can see it. So we can see it within the gutter. It just hasn't been knocked across. So a prime example where these panels are coming from the factory and they've got everything they need to succeed except for when it's been installed. Some more examples of that, where movement and tolerance hasn't been taken into account. So the one on the left here is where the closing angle hasn't lined up with the stack joint. And so the compression of that next panel above has just popped that out. Same with the one on the right. So a key takeaway from that one. These panels came from a factory with everything they needed to succeed, but failed at the last hurdle by the installer who clearly didn't understand what it was that they were installing. Ooh. Maintenance and life. A primary issue with leaks originating in the life of an asset is a lack of understanding for preventative maintenance. Understanding when I need to do something and catching it early. Apologies that this keeps jumping. Also a lack of CapEx build-up. So we often get to the point where we need to do something, but we've got no money. And so that hinders and delays getting that work completed. A big one is the design is too difficult to maintain. We haven't thought about it enough right back at the beginning. Lost documentation. I think anyone who's worked in the remedial space knows that when they've arrived on site and they go, we don't have drawings, but we've got structural drawings, that should work for facade. Yeah, that is a minefield of trying to put back together and piece together what actually happened. And with that information and that keeping of that documentation, it's almost like a golden thread, right? It only takes one FM to not copy a USB stick across correctly or something along those lines, and it's snapped and that information is lost. And you have to start building this thing back up again. And that impacts both preventative maintenance and then understanding how you can rectify those things. Another thing is, of course, poor selection of materials and durability that we talked about. So, case study for this one is a heritage listed building in Brisbane. And beautiful, beautiful piece of architecture on the inside, and it's got these lovely ornate skylights at the top. There is 16 of them in total, and over 120 pieces of glass in total making these up. And of course, things are aging and deteriorating, and it's getting to the point where we're getting a lot of leaks the whole way through this particular church. And the primary cause of that is, of course, the fact that we've got a steel-framed roof that's corroding. The problem here is that when you want to treat this, you have to take out all 126 panels of glass, take the frame down, go and get it reconditioned, and redone again. So there's a whole heap of thinking in here around maintenance that wasn't otherwise there. Now, benefit of the doubt, things have changed a lot since this was originally done. The problem is that we're still seeing people wanting to use painted steel in difficult to access applications and bonding things to them that are going to be a nightmare in about 20 years' time when they all start corroding out. So key takeaway from this one is that we're still building without thinking about maintenance and surface life. Final one, this is where it all went wrong. I will jump onto this one because it's a bit more interesting. So this is a project with a stick curtain wall system to the front of it, and up on the top level we've got an exposed concrete slab, and that's made up of structural slab at the bottom, insulation, which is the blue, and then a topping slab, and then at the parapet we've got a blockwork wall. That parapet's then got a capping piece on it, and away we go. This was having systemic leaks the entire way down the facade. So when we got called in to have a look at this, it was, hey, our facade is failing. This stick system is leaking. And we all know that stick systems, after a while, can have a few leaks around a few critical locations. But what was interesting is when we started to dig further, There's no documentation on this, so that's number one, around the maintenance of things going pear-shaped, is there was absolutely no design documentation for the facade or for the waterproof membrane. We couldn't find where it was, so we had to start digging things out. What we discovered was that while there was a waterproof membrane on the top, and when we went back through satellite images, they had had a crack at doing this 5 times in the last 10 years. There's clearly been an issue, but the entire substrate down below that on the structural deck was entirely wet, and water was basically permeating through the topping slab, through the insulation, down onto the structural slab, making its way across to the parapet wall that we can see, and then draining out over the slab edge. But that makes sense for it leaking up the top, but why was it leaking on all of the other levels? And that's because someone had a great idea of putting a catch tray on the inside. And so this catch tray would catch everything coming off that slab and then dump it out through the mullion, through a copper pipe. And this was at every single location. Again, not understanding the system, that maybe we shouldn't be drilling through the back of a facade to dump water that's coming from the slab above. And eventually, what happened was the spandrel zone, all of that paint started peeling off the glass and falling into this catch tray, and it clogged the entire system. So then the water got dumped into the back of the mullion and went down every single level and just coming out, level 6, level 5, level 4. And so once they got back up to the top and simply rectified the waterproof membrane at the top, all of this went away. But it just shows you that without the right documentation, without an understanding of the system, and without thinking about durable materials and all the other bits and bobs, you can really stuff up a remedial solution. And so this has now all been rectified, but there's a lot of money that's been wasted here trying to rectify this in simply the wrong way. Just another shot of the impact that that's had further on down the building with this water ingress. So the common link to resolve a number of these issues is education, but also spending money at the right time and at the right location. And that money might result in more time for the design team, but it also might result in more flexibility for the builder to investigate different options for producing a durable design. I would encourage you all to create your own feedback loops and try and learn and share this information. We all become better because of that, and hopefully we will get a more durable solution when it comes to facades, and you'll make my life less difficult when it comes to the remedial portion of it. But thank you.
So my takeaway from that session was thinking about materials, detailing, testing the facade, and making sure you have your documentation for support and maintenance. Thanks a lot, Todd, for that. Our next speaker is Jesse Clarke, the Technical Innovation Manager with ProClima. His topic is It's All a Facade. He will explore the role of cladding in rain screen performance, the science behind pressure equalized facades, and why fully tested AS4284 systems are critical to delivering durable, weather-resilient buildings. Please welcome Jesse.
My mother always told me, it doesn't hurt to be extremely, ridiculously good looking. But it's what's on the inside that counts. So that's what we do at ProClima. We sell membranes that are on the inside of facade systems to make them weathertight, and that's our specialty, as you probably know. The risks of not getting this right has been established by the New Zealand experience, and in the New Zealand experience they stuffed up in 2 ways. They let water get into the structure, as Todd just pointed out, same thing happening in New Zealand, and internal moisture. So they didn't manage the condensation risk properly, and they ended up damaging the buildings. The building damage in 2019 was outlined in this book, Rottonomics, the story of New Zealand's leaky building disaster. $47 billion in 2019, and still counting. It's much higher than that now. Not to say that Australia doesn't have a leaky building disaster, we just haven't quantified it yet. This was an interesting email I received back in May last year. And this was from a construction lawyer who wanted to know, they had a stalled major project and they had water ingress. And they wanted to do a causal analysis on how this moisture got into the construction system. They were trying to work out whether it was condensation or whether it was water ingress. Ultimately, it doesn't really matter because the building code now has mold index, and mold is in the building code. If mold's in the building code and starts to form, that means you've got moisture. Whether it got in by water ingress or condensation, there's a potential legal risk there. So that brings us to the weather-resistive barriers, or the sarkin type material, as the building codes call it. And basically, we have to stop the water getting in, and we have to allow the construction systems to dry out should there be any moisture in those construction systems. So just quickly, what are the building code requirements? I'm pretty sure you all know this, but it has requirements around weatherproofing, but it also has these emerging requirements since 2019 around condensation and the prevention and entrapment of water vapour. And the building code requirements, I'm pretty sure you've all read this part, but must prevent the penetration of water that could cause unhealthy, dangerous conditions or loss of amenity or deterioration of building elements. And you've all read the 2025 updates and what's coming, which pretty much says the same thing. The water must be disposed of in a way that prevents unhealthy or unsafe conditions, loss of amenity, and undue damage. So basically, we're protecting the health and the safety of the people in the buildings by not allowing water to get in. So ProClima always prefers to verify the systems that we design and deliver to market, or that we distribute to market. And this is the process by which we fully test using the verification method AS-NZS 4284, using a membrane system with a cladding over the top. This is typically how it's done to test the full system and the weather tightness of that system, in which a compliance report is achieved, such as this one from Ian Bennies and Associates in Melbourne, which can then be used for verification purposes. So what's the role of the cladding in this whole thing? Cladding can't be underestimated, but the wind pressure is the main thing that causes cladding to potentially have issues with water leaks. And if we go back in history and we look at the AAMA from America in 1971 that talked about cladding and cladding joints, if you have wind on the outside of a building, you create a pressure differential, you create airflows through gaps and cracks in the cladding that can entrain water past the cladding. If we start to baffle those joints and crimp them and seal them up, we can try and mitigate that water getting through by reducing the amount of airflow through the cladding system. But ultimately, the AMA talked about having open jointed facades, and then behind the cladding system, put in an air barrier or a wind barrier that creates an airspace and a pressure equalised cavity. So that's the basic science behind the modern day rain screen pressure equalised cladding system, 55 years ago. So back to the New Zealand leaky building crisis, $47 billion of damage. In 1990, brands were looking at, well, how does this pressure operate across a residential wall? Because that's where the big problems were. They were looking at the cladding systems and saying, if you got wind on the external side of that cladding, if that's like a weatherboard system, the pressure will force its way through the gaps and cracks, and the pressure will end up back on the plasterboard layer on the inside of the construction system, because that is the most airtight layer in that construction system. What that means is that you've got very small pressure differential across the cladding and most of the pressure differential across the plasterboard lining. And if you go back to the plasterboard manufacturers and say, well, what does that mean? They put pressure limits on how much pressure should be loaded onto the plasterboard. When you start to talk about commercial high-rise facades, that can be a significant amount of pressure. So obviously, we should be putting another membrane in that system or another layer in that system behind the cladding to make that pressure equalisation work. If that membrane is not well sealed, you'll take some of the pressure off the plasterboard, but you'll still have a significant amount of pressure on that plasterboard. If we take all these learnings to the commercial facade space, we know that face sealed systems require required sealed joints all over the facade system. That means 100% of the pressure is taken over that cladding system. It needs to be hermetically sealed for that to be weathertight. When you have minor gaps or cracks that form over time, UV exposure, temperature, cycling, you can end up with the sealant joints cracking, the wind will force the water straight through those cracks and joints in the mastic seals. So going to commercial facade systems that actually work, you start to put more like the AMA solution, which has a membrane behind the cladding system, baffle the joints, allow the pressure to equalise across the cladding, so you're not fully sealing the cladding up, you're having opening joints at the bottom and top of the wall to make sure that pressure equalises. If the membrane's not properly sealed, back to the Brands research, you'll take some of the pressure on the membrane, but you'll still end up with a lot of pressure on the plasterboard lining on the inside of the structure. We know from our experience that when you're using flexible membranes in systems, they should be well sealed, taped and jointed so that the wind pressure is mainly taken on the membrane. It becomes the most well sealed layer in that construction system. But what it does mean is that the membrane is going to deflect under pressure. When you go under negative pressure on the leeward side of the building, it's going to deflect outwards. So over the lifetime of that building, it's pushing in and out over the life of that structure. Where we're driving to is having rigid board systems that have full adhesive membranes over the top, more open jointed cladding systems that allow the pressure to equalise, and the membrane and the board are going to be taking all the pressure. They're going to be taking almost 100% of the pressure within that system. A very small amount of pressure will be taken on the cladding. So this is then replicating the ideal solution the AAMA identified 55 years ago. The perfect wall was coined by Joe Staburek, a building scientist from the US, about 8 years ago. And the perfect wall is a system in which you put an exterior layer of rock wool over the outside of that rigid board system. This has multiple benefits, including stopping the thermal bridging through the system, but also condensation management, because it helps keep that board warm and it can help mitigate the risk of mold growth within that construction system. Taking that a step further, in 2014, the BSCI in Canada did some research, spray rack testing, so the kinetic energy of the raindrops hitting a very open jointed perspex facade to see how much rain would go through those joints, hit the stone wall, and where the water would drain out of that system. So they measured the drainage out of that system off the front of the cladding, the back of the cladding, off the front of the stone wall, or off the front of the rock wall to see where the water was draining from. What they found is the majority of water drains off the front of the cladding, back of the cladding, and the front of the rock wall. And this was under extreme weather conditions. So we're talking about 70 times more rain intensity than 94% of the driving rain events in Ontario, Canada. And Ontario, Canada is a very wet environment. So this brings me to the next discussion, which is rigid boards. Rigid boards can handle pressure to an extent. And when we load rigid boards into the system, we then put a full adhesive membrane over the top of these rigid boards. So this gives us a full weather-tight system. We've been doing a lot of research and a lot of testing on this system. And the ProClimate technology, all the sealing technology to seal up the joints and gaps and cracks is what really makes this system work. So diving into what the system is actually about, the facade system there, you see on top hats, actually relies on all the pressure being taken on the weather-resistive barrier, or the Sarkian type material if you're using building code language, and that needs to be a water barrier, it needs to be an air barrier to take the wind pressure, and it needs a level of vapor control, meaning vapor permeability. And the attachments need to be sealed on. That's a critical point where you might get water leakage through that system. This is now called the Frontek system, packaged as a full weather-tight system with all the ProClimate components. When we install this in the lab, the team makes sure that it's installed in a very robust manner, and we pay attention to all the details, because the details that we install in the lab become the details that we deliver to market. And paying attention to the way it's installed surface by surface, penetrations are fully sealed using ProClimate sealing technology. Special attention needs to be made at the windows. As we saw from Todd's presentation, windows are where things often leak, and how those windows are sealed in is important. We have a new product which is a movement joint material, primarily developed for New Zealand for seismic movement joints, but what we've found is there's a strong demand for this in Australia as well for all sorts of control joints. This is the seismic racking underway or testing at Ian Benny's and Associates. We're just testing the product here, but you can see the flex on the T-Flex product, 300% elongation, flammability index less than 5, and a vapor permeable product itself. So it meets the C2 D10 requirements around non-combustibility. We also looked at fireproofing and the fire performance using open state fire barriers, how they were attached to the assembly to make sure all the fixing points didn't leak, which is an important component of fire-safe facades. When we talk about rigid boards, we need to be very conscious of the fact that rigid boards can crack. They can crack during installation when they're screwed on, under overdriven screws can crack the boards up, and also when they're under building movement can crack, and also under wind pressure they can crack. And that's what you see here if you look carefully. There's a hairline crack in the back of that fibre cement board. So depending on the wind pressure and the stud spacing, then you can get these cracks occurring. This is why we need a full adhesive membrane over the top. We wanted to make sure that under negative pressure, strong negative pressure, the membranes wouldn't suck off the wall. So we did a lot of peel adhesion testing to the ASTM D330 test method. And we took that a step further. So at the test lab at Azuma in Sydney, we basically took the pressure up to -6 kPa to see what would happen when we had the adhesive membrane over the board. This is a huge success for us because the membrane didn't show any signs of delamination, and there was full failure of the board before the membrane showed any signs of coming off the substrate. So screw it, it doesn't even matter. The fixings are the critical point in the facade system. And we tested with all sorts of different fixing methods, including top hat sections with screws going through into the studs. But the real hero is the Tescon Natick, butyl sealing tape. And we've tested with various options for, well, facade mounting options, including the rails, including facade clip systems, Technoform, EOT, Hilti, Sculptform, Green Girt, Builder clips, Builder F clips with packers, Builder U clips with packers, Rondo, heavy duty metal angles with packers, and ultimately put this under test to make sure that it wouldn't all leak. And we did this without a cladding, up to 3.5 kPa serviceability limit, after we had racked the whole system, positive, negative 20 millimeters on the seismic movement joint. It's what's on the inside that counts, and it's the details that drive the outcome within the cavity, the drained and ventilated cavity. What we wanted to go to next was look at what happens when we put a full continuous layer of insulation, and we wanted to make sure that the fixings didn't compromise the weather tightness of the system. This system is called Vortex Melior, and Melior means better. When we fix the rock wool, we established the best way of fixing the rock wool is to use mushroom-type clip fasteners. And these mushroom clips provide a weather-tight outcome when fixing the rock wool over the system. They do this because the water drains off the front of the hydrophobic rock wool rain screen product. It doesn't penetrate through that, and you get the bulk of the water draining off the front of that insulation layer and producing a weather-tight fixing of that insulation. So this is the system under test, extreme conditions, no cladding, all 100% of the water hitting the rock wool, and we still passed that full-scale facade test. So in terms of bringing this to market, we have the certification, we have evidence of suitability, we've got the full-scale facade tests from the Ian Benny's test lab in Melbourne, and we've got weatherproofing assessment reports that can be available to all engineers, and you just need to request it from us, and these are the reports that establish the verification of the performance for weather tightness in the NCC. If you want to know more, come and have a chat to us. We're happy to have robust discussions and very technical discussions. Thank you.
Thanks, Jesse, for that deep dive into the ProClima weatherproofing products and their performance. Our next speaker is Angus Macleod, Technical Director at Vector Foil Tech. His topic is Southern Hemisphere's largest single-span timber aircraft hangar clad with ETFE. Over to you, Angus.
Thank you very much. Well, good morning, everyone. My name's Angus from Vector Frontek. I'm Technical Director there. I'm going to be talking a little bit about Air New Zealand's Hangar 4 at Auckland Airport, which we completed late last year. Before I do that, though, just a little bit about Vector Frontek. We started in Australia in 2003, and we've completed approximately 75 different projects around the area since then. Some of the projects around Asia that you can see: Singapore Sports Hub, the Beijing Aquatics Centre, Forsyth Bar Stadium in Dunedin, and Southern Cross Station down there in the bottom middle. So we've been all over Asia and Australia and New Zealand. Some context for you in terms of the airport. So we've got Auckland International Airport at the top there. They're in the process of moving the domestic terminal into the international at the moment. And then you've got 3 hangars at the bottom end of the airport, the east end actually, all built between the 40s and the 70s. And then Air New Zealand decided to build a new hangar, Hangar 4, right at the eastern end. The initial design concept, it's a hangar. But they want to have at least one wide-body aircraft, an A350 or something along those lines, and then a couple of smaller jets in there at the same time. They also wanted to be able to shut the doors, and they had a very innovative drop-down door system there, which we'll talk about a little bit later. Of course, no project is just built by one person. On the design team side of things, we had some excellent architects, Studio Pacific from Wellington. Holmes were the lead structural engineers. ACOM, Civil, Hydraulic, Mech, Elec and Lighting. eCube doing sustainability, TSA were the project managers, BBD were the QS, WSP doing environmental and wind, GHD doing civil. On the construction side, we had New Zealand Strong, a very, very capable head contractor, sort of tier 2 level. And they brought on several specialists, including XLAM, who were supported by Dunning Thornton engineers from Wellington as the timber engineers. And of course Vector Frontek, and we were supported by Arup as checking facade engineers. Interestingly enough, there was no formal facade engineer on the project. Arup were the only facade engineers, and they were in a checking role. Give you some idea of scale: 98 meters wide, 130 meters long, 36 meters high, timber trusses, 2 and a bit meters deep. Very slender. The end trusses you'll see in the following photos are actually steelwork, and that's mainly because of the doors, and they required excessive deflection limits, and so they just needed a little bit stiffer down those ends. A lot of work going into what would fit into this space. Now you can see in the background here, the initial design concept was a portal-framed arch solution, which they then, over time, translated into a much thinner timber truss 2-pin solution. At the start of the project, it was actually being documented in insulated PVC style cladding using a contractor from the United States who specialized in this type of material, or this type of structure. You can see some of their work in the bottom right-hand corner there, but they'd never worked outside of the US before, and certainly never in Australia and New Zealand, which once the head contractors came on board, they started to question some of the issues, such as, well, who's got the warranty, who's got the workmanship, etc., etc. So it was a big risk at that stage, and that's where they started coming to me. Give you some idea on the timeline. Work started in about 2017, working on the design. NZ Strong were appointed as the head contractor in late 2019. Obviously, COVID happened. I think we all have memories of that. Site works, because at its heart, a hangar like this is primarily a civils job. There's a lot of in-ground works, tarmacs, fire pits, all sorts of horrible things. So site works started quite early. Then they decided to get us involved, ETFE redesign. At the same time, they took the opportunity to enhance the design because of the AS 1170 wind code, increase in basic wind speed in New Zealand. I'll come back to that in a little bit. Fast forward a little bit, we completed the project in late last year, August, September sort of area. So why? Why would they use ETFE as a cladding material on an aircraft hangar? We're usually on commercial buildings, stadia, hospitals, high-end. Why do an industrial building out of this high-end cladding material? And there's a myriad of reasons, and some of them are listed here. I'm not proposing to go through all of them, it'll take too much time, but we'll talk a little bit about some of them on the next few slides. One of the big ones, though, was the wind pressure. Like I said, the wind speeds increased because of AS 1170 changes. Had to redo wind tunnel tests. The way that ETFE works, we're able to redistribute a lot of that load across the rest of the structure. Timber's obviously the hero piece in this. The cladding is not, unfortunately. I love working with timber. I think it's a wonderful material. But it's got to be detailed, right? And you can see the level of design and engineering that's starting to go into these types of structures. The consultant engineers' drawings, this is them. You can see we've got LVL top and bottom chords, CLT webs and purlins. You've got really long screws, up to 700 mil long screws being applied on site to connect the webs and the webs to the top and bottom chords. And then you have perpendicular screws to hold the whole thing together, especially in the CLT. Every truss, over 16,000 fixings with 13,000 of them being applied on site. ETFE upstands sitting on top of all that lot. You'll see some images shortly being applied on the ground. Some interesting factoids about the timber as well. The CLT, even though there's over 387 tons, that only represents an hour and 13 minutes of regrowth in New Zealand forestry. So it's a really sustainable material from that point of view. A massive carbon sink. The LVL components were actually sourced from Australia. XLAM have a factory down in Albury-Wodonga. So that was shipped back over to New Zealand. But over 7,000 different separate timber components and 300,000 timber fixings overall. You can start to see in the image on the bottom right there, that's one of our air supply units that keeps one of the facades inflated. But the amount of design that goes into services and reticulation on a job like this, it's, from a personal level, I found it very similar to working on a hospital project, the level of design that went into it. From an ETFE perspective, we spent a lot of time working with the design team on environmental controls and working with the airline to establish what the best operational parameters inside the building were. Lots of different combinations of different specifications of ETFE. We ended up with a white ETFE on the roof with a very heavy print to give us about 4% light transmission. Just enough to take the edge off and provide long-term energy usage benefits in terms of lighting. But not dark enough, not bright enough that when you're at ground level and looking up at the plane that you're getting the contrast issues. Then we were able to then make the south facade out of transparent ETFE, let light in, turn it into more of an inside style, being able to view the outside of the building. Rainwater drainage, obviously we have to concentrate on. We did a lot of work on optimizing the geometry and the configuration to make sure that water was going to adequately sluice off the roof. With such a big span and such a big arch, we're getting a big flat spot right in the middle of the roof, so we wanted to drive water away. But then of course you have the instance, what do you do with all that water? Now this video on the right, that was a 25 mil an hour rainstorm. And we've got water coming off that. Yeah, it's coming off fast. Trying to capture that water was a challenge. So we had to do a lot of work with the guttering and the siphonics to try and capture and control all that water coming off. Site water testing, I think it's very important. We do a lot of work with this AMA AAMA 501.2 site water test. We had people going around and testing every single joint, full QA, full photographs, and videos of every single joint, which Arup then had to go and check. But such big cushions, the cushions here are 4 meters wide by 60 meters long. We end up with very, very few joints per square meter. So really reducing the idea of, or the risk of leakage across the entire job. Timber also presents some very interesting problems in terms of what do you do with man-safe anchor points. The timber there can't handle a 22.5 kilonewton point load, so you've got to spread it around a wee bit. So we had to come up with some innovative ideas about how to take those point loads and get them into the timber safely, developing systems like this. Quick time lapse, sorry for the quality, but it gives you some idea of the speed of installation. We've got the nose cone structure down one end, which is a steel framed solution. Then the timber hangers, which are being rotated up from the ground level. So they're hinged at the base and then rotated into position. We've got a trafficable netting system for the installation, and then the ETFE goes in really swiftly afterwards. And clad. So that time-lapse period was between May 2024 and August 2025, with most of the ETFE action coming in that sort of last 3 months. The finished product. Internally, you can note the nice, even quality of light through the space. You can see some of the services hanging from the roof as well, and the door in the background. Again, here you can start to see things like the foam generators for the fire suppression, hanging from the roof there, the big bell-shaped looking things. Lots of services, winches. You've got big-ass fans up there for air circulation as well. This is the northern facade, active bank of louvers there to try and let some of the hot air out, an access path up and onto the main roof, as well as onto the roof of the nose cone. And then from a distance, you can also see that access ladder on the right-hand side there. Interesting structural movement joint between the steel structure and the timber as well. From the outside, we're not getting much reflectivity, just through the shape of the cushions. It tends to spread the light out a little bit. We've got overall reflectivity of around about 40% on this, but we're not getting any glare issues from it. You can also see the active lightning protection system that we installed on the roof, as well as the signage, which has the fixings coming through the ETFE extrusion. Nice and waterproof as well. And finally,
today is a really happy day for Air New Zealand. We've just officially opened our new aircraft hangar here at Auckland Airport. It's a phenomenal structure, and it can fit 3 aircraft, 1 wide-body jet and 2 narrow-body jet at the same time, and it sets us up for the future.
It's pretty exciting for us and the whole team, obviously with it being brand new. I think there's a lot of features in there that are going to make it easier for us to work more efficiently. We all walked in with our jackets on, expecting to be cold, which we are most of the time, and about 5 minutes later we all walked off and threw our jackets back outside because it was warm in here.
Look, this is a state-of-the-art facility for Air New Zealand, and it's an investment in our people, and our aircraft, and our customers. This structure will be here for decades, and I think it's going to become a bit of a sort of an icon on the landscape for Auckland. So really proud to have the hangar right there, visible to everybody as a welcome to this country.
and that's me. Thank you very much.
Thank you, Angus, for that. It was very interesting to see the combination of timber and ETFE for the purposes of airport hangar. I now welcome our next speaker, James Perry, director at Koichi Takada Architects. His topic is naturalizing facades. He will challenge us to rethink the facade as a living interface, one that responds to climate, enriches human experience, and creates a strong sense of place and identity. Please welcome James.
Good afternoon, everyone, and thank you for the opportunity to speak here. I'm James Perry, Director of Koichi Takada. I recently joined the team but I have a long history with Koichi, and I'm familiar with the case projects that I will be sharing. The three projects in focus each articulate a deeply considered response to nature, not simply as reference, but as an embedded design driver. More importantly, they reveal a strong connection to place where form and facade are direct expressions of their underlying concepts. In each instance, the architecture is shaped by an idea that informs massing, form, materiality, and articulation, resulting in buildings that are both contextually grounded and conceptually rigorous. Koichi Takada works across Australia and internationally with studios in Sydney, Brisbane, and we actually have a remote team in Europe too. While our projects span the globe, a consistent question drives our design approach. How can architecture become a mediator between nature, climate, and human experience? Traditionally, facades have been treated as building envelopes, protective skins that keep the weather out and performance in. But we're increasingly designing facades as adaptive interfaces, shading, ventilating, filtering light, encouraging biophilia, and shaping social behavior. This shift isn't just aesthetic, it changes market response, environmental performance, and occupant well-being. The three projects I'll be presenting are Trinity Point on Lake Macquarie on the left, yet to be completed and still early phases of development, Norfolk Burleigh Heads in the middle, and I'm sure everyone's familiar with Upper House in Brisbane, completed in 2023. I'll start with our first project at a waterfront precinct located in Morisset Park, Lake Macquarie, called Trinity Point. The site is only a 90-minute drive from Sydney and 60 minutes from Newcastle. It's been identified by New South Wales as a strategic growth area and by Lake Macquarie Council for the establishment of an important tourist outcome. With significant visual catchment, a shoreline of about 170 kilometres, and actually the largest coastal saltwater lake in Australia. It's located on the prominent shoreline of Morisset Park. The site offers a prime destination along the foreshore of Lake Macquarie, and located at the end of a natural peninsula bounded by the lake on three sides. So a really phenomenal site. The rolling hills of the Watagan Mountains are the inspiration for the proposed architectural character. The idea of where the mountains meet the lake. The design intent reflects the natural surrounding hills, creates an iconic landmark and mixed-use precinct that is directly inspired by its unique setting. The architectural response is based on the conceptual approach to create a form and geometry that is crafted to harness site conditions and climate, and then to assemble this collection of buildings to further optimize the positioning on the site with consideration of views, solar access, and increased vegetation. And of course, the impact of both height and scale. While carefully considering the creation of open space, public and private, within the site and the connection back to the shoreline. And to generate a collection of building that maximizes the opportunity of a new activated foreshore, but reinforces the connection with the natural landscape of the site. As you can see, the built form strategy is driven by massing, a scale, and an ecological integration. Instead of a single monolithic form, each building tapers as it rises, and the footprints curve to follow the topography. This tapering reduces perceived height, creating a gentler built form and ecological sensitivity. The green roofs soften the skyline, reduce heat gain, support habitats, and visually connect the broader ecology of the lake and surrounding landscape. Each apartment and suite is designed with generous balconies, reinforcing the indoor and outdoor continuity and connection to place, shading interior spaces, providing natural ventilation, and allowing residents to engage with nature and the lake. The project is designed to be highly sustainable and carbon neutral ready, and that idea where the mountain meets the lake. The second project I'll move on to is Gold Coast and Queensland with a project called Norfolk. It's located in Burleigh Heads. The north-facing beachfront is located at 46 Goodwin Terrace at the southern end of Burleigh Heads Beach. With expansive views along the coast and out to the ocean, framed by heritage-listed Norfolk pine trees, which were actually the inspiration for the project, but particularly the form and geometry of the pine cone, which is replicated in the organic shape and the similar to overlapping scales of the pine cone. A number of studies were actually to determine the most relevant and environmentally responsive arrangement of the balconies along the most exposed and visible north-facing facade. And the preferred configuration provided the most effective performance and dynamic facade and strongest reference to the design intent and concept. The slabs are curved, offset, tapered, creating self-shaded private balconies while softening direct and intense solar exposure without eliminating daylight and providing a buffer for high offshore winds. The facade to the north elevation is a series of fixed aluminium battens tapered towards a balcony, positioned to provide privacy protection without compromising views and natural daylight. Tapered slab edges project past the facade line and curve line of balconies, reflecting natural and ambient light, which reduces the reliance on artificial lighting during the day, while acting as sun shading during summer, but then allowing winter sun deep into the living spaces. And the living spaces are positioned, as you can see on the plan, the north is to the left-hand side of the screen, to offset on the three primary facades. And this really enables a full and open connection between the private and indoor and outdoor living spaces. With the threshold between the indoor and outdoor blurred, which you can see or not see quite clearly in this image, reinforcing the importance of the expression and configuration of the form and facade interface along this north elevation. Maximizing views, but maintaining privacy, and creating a unique and individual experience for each resident on each level. The building also has a unique benefit of being positioned adjacent to Rudd Park on the right-hand side of the building as you see it, to the east, and this further reinforces the opportunity to connect not only the building to the immediate natural surroundings, but also the residents within. The east elevation is a combination of fixed and operable screens, allowing residents flexibility to open the facade and capture the cool breeze, but equally to close it down for privacy and weather. The solid sandstone base and vertical recesses divide the building into three distinct masses, reducing the bulk and scale against the park. That east elevation is broken up into aluminium operable screens that are set on a diagonal geometry that helps stiffen with the screens as they slide and move, but also to provide a strong visual reference to the overall building form. And battens are spaced at a 30mm center to center to ensure privacy for residents, but the balance to get it right so that those residents actually maintain a visual connection to the park and ocean views. Screens are positioned on the outside of the balustrade, allowing residents to easily slide and adjust these screens according to their needs, which opens the balconies and living spaces while still maintaining the privacy and the views. And creating what is a highly active elevation and connection to the park, which this view looks at that east elevation with the park in the foreground and the ocean beyond. The last project I'll be presenting is Upper House, and I'm sure a project that everyone is very familiar with. It's located in South Brisbane on Hope Street, a high traffic and high pedestrian part of South Brisbane, but also in the heart of the South Bank Cultural Precinct where we are. This is a very different context. It's urban, vertical, and dense. It's a residential tower with a mix of above ground parking, residential levels, and shared rooftop amenity. Drawing inspiration from the Queensland Moreton Bay fig and the Daintree rainforest, we started to develop this idea of how this building could exist in this urban environment. The tower form and movement becomes an expression and articulation of this inspiration. Through the varying positions and geometry of the balconies as they progressively move up the tower, from the podium to the vertical sinuous facade to the sheltered roof garden, all connected as a single continuous urban tower for living. The podium encloses an above-ground car park, which is clad by a 5-story art wall by Australian artist Judy Watson, titled Bloodlines Weaving String and Water 2023. It acknowledges the Turrbal people as the traditional custodians of the land on which the project is built. The external artwork serves as dual role of hiding the functionality of the car park, but creating a cultural narrative through its patterned perforated metal and folded backlit artwork. The podium can almost be interpreted as the buttress root system of the fig, anchoring the building and creating an extensive canopy and shelter below. The facade becomes a deeply connected and public interface rather than a utilitarian one. Above this, the tower introduces what we call the dancing balconies, each connected by a series of paired extruded aluminium profiles or ribbons that span from balcony to balcony, maximizing repetition, reducing cost and wastage. The balconies adjust their position and geometry level by level to accommodate the ribbons as they move up the building. They shift along the facade, orienting towards view corridors while reducing direct overlook between neighbours. Their movement breaks down the massing, creates rhythm, and enhances privacy, a critical issue in this urban context. The timber colour ribbons are a significant feature for each apartment, a foreground for the city beyond. And these ribbons transition at the roof level into a timber pergola that houses shared amenities, outdoor living spaces, and a shelter in the sky. It's at this interface where the aluminium ribbons transition into the sustainable larch glulam pergola, made of slim load-bearing main ribs, featuring double and triple bent elements and timber purlins for shading. That all come together to enhance the experience of the timber canopy for occupants on the rooftop and as a foreground to the city skyline. Through the shop drawing and fabrication process, the larch timber was CNC cut with double and triple curvature to provide the required geometry that you see of the pergola. And to maximize the efficiency and repetition of the timber beam, dimensions and geometry to reduce cost, wastage, and minimize the impact on shipping and storage. All these considerations had a significant impact on the process and feasibility of using timber in this way. The timber is fitted with steel connections right from the factory to accommodate a smooth, easy lifting and assembly process as well as delivery to site. It took about 6 months to install the 48 cubic meters of timber, comprising of 672 triple curved timber beams and approximately 1.6 kilometers of large purlins. In addition to the timber pergolas, there are 2 9-meter tall unique structures that sit at the top of the tower on the 32nd floor. The nests, as they're called, are timber-rounded platforms forming a suspended pile on top of the pool area, surrounded by an intricate free-form mesh of ash tree timber, providing shelter and privacy. Each nest is composed of 92 ribs, split equally in half for top and bottom parts, connecting at the center disc using concealed pre-assembled hardware. The ribs have been steamed using an innovative process which included the design and construction of a dedicated steaming machine and a number of hydro-adjustable molds to be able to form the shape that each rib was designed for. The bench is demountable, while each individual piece has been manufactured using a robotic machine. The finish and final touch has been done by a specialist artisan working in their Italian workshops prior to shipment. The combination of the sophisticated design, production, assembly of the pergola and the nest create an environment that not only serves as a shelter for the residents, but also significantly enhances the biodiversity and reintroduces bird life back into our urban high-rise living. And this actually is a photograph from the top of the building. It's not one that... So it's amazing the transformation that it has had in that space. Finally, these three projects represent the outcomes of a rigorous conceptual process and connection to the natural world. We have generated built forms that go beyond relying on facades to solely provide comfort and performance. They craft active and adaptive interfaces that respond intuitively to their residents, regulating climate, filtering light, and framing outlook to enhance well-being and everyday quality of life. At the same time, each project remains contextually distinctive, contributing meaningfully to and enriching its surrounding environment. Thank you.
Thank you, James, for that. It was a reminder on how key architectural and design moves can create places of comfort, protection, joy, and pay homage to local culture. Our next speaker is Christy Irish, Queensland State Specification and Sales Manager for Ecotone, with over a decade of facade expertise. Christy will explore circularity in facade design, reducing embodied carbon through the 4R framework, and driving industry collaboration to deliver closed-loop, long life-cycle material solutions. Over to Christy.
Good afternoon, everyone. It's great to be here. Let me begin with one simple question. What happens to the materials we use when a building reaches the end of its life? Well, most of the time, they become waste. But what if we could change that? What if the materials we use today could live on again and again? That's the promise of circularity. Designing smarter, building responsibly, and ensuring our choices today don't become tomorrow's problems. Today, I'll show you how fibre cement panels, hold that thought, guys, known for its strength and durability, can support true circular construction through the 4R framework. Refuse what we don't need. Reuse what we already have. Reduce waste through design, and recycle to keep the materials in the loop. We'll look at 3 key case studies today: a hospital in the Netherlands, 2 projects in Germany, and some homegrown Australian innovation, proof that circularity isn't just theory, it's happening right now. By the end of this talk, I hope that you'll see that circularity goes far beyond recycling. It's about rethinking how we design, build, and collaborate so our buildings don't just stand, they sustain. Need a clicker, guys. Let's dive in. In just 50 years, the world's population has doubled from 3.7 to 7.5 billion. But our extraction of virgin materials has grown even faster, rising more than 3-fold from 27 to 92 billion tonnes. At this pace, the planet's generosity has its limits. If we continue on this trajectory, in a few decades, there won't be much left to give. What we're talking about isn't just an idea. It's a framework of doing more with less. It means using fewer resources, water, energy, materials, while creating products that last longer and waste less. And it's not something one group can do alone. Every stakeholder has a role in reshaping the system. This is the blueprint for a sustainable future, and it starts with us. Construction is facing a definable question. How do we keep building without exhausting our resources? The answer is circularity. Designing materials to stay in use, not become waste. The answer is circularity. The 4R framework that we use for fibre cement. 1, refuse. Avoid unnecessary new materials. The example here will be our Netherlands hospital. Instead of purchasing new panels, they used existing ones. 2, reuse. Extend the life of what already exists. Our second case study is the Hanover House, a recyclable house in Germany. 3, reduce. Minimise the use of virgin materials through smarter design. Another example in Germany, where we have a German logistics warehouse optimising its panel cutout. And lastly, 4, recycle. Close the loop by transforming old panels into new ones. The example we'll go through is Etex and Heidelberg crushing old CFC and absorbing this. True upcycling. Here is circularity in action. The idea is simple. Avoid using new materials, and existing ones can be upgraded or reused. And when change is needed, make sure everything can be dismantled without breaking panels or damaging the substructure. That's how we design for flexibility, longevity, and circularity. Do we have any Dutch speakers in the audience? This one's for you. Everybody else, I assure you, we have subtitles. Let's have a look at how they did it.
Het ziekenhuis van Nijsmellingen is voor Equitone een interessante testcase, omdat er 15.000 vierkante meter materiaal beschikbaar is voor hergebruik. Wij hebben daarom samen met de architect, met de aannemer, maar ook met het ziekenhuis zelf rond de tafel gezeten en we hebben een aantal eerste indicatoren nagecheckt waaruit bleek dat het wel degelijk realistisch is om hier een reuse case van te maken.
Samen met ziekenhuis Nijsmellingen zijn we begonnen aan de ontwikkeling van een nieuwe gevel. Het is een bestaand gebouw, het staat al wat langer en dat heeft ook weer een goede toekomst nodig. Bij het ontwerpen van een nieuwe gevel is het ook een belangrijk thema om te denken aan circulariteit. Dus zo zijn we bezig gegaan, kunnen we dan niet alle gevels van het hele ziekenhuis door de tijd heen vernieuwen, bestaande gevelplaten oogsten en combineren met nieuwe platen in de nieuwe gevels.
Waarom is Nijsmellingen nu zo'n interessante testcase voor Equitone circulariteit? Allereerst is er natuurlijk de schaal van het project. We hebben de ambitie om minstens 10.000 vierkante meter materiaal te redden van de afvalberg. Ten tweede is het iets wat heel lokaal kan gebeuren, geen grote transportafstanden. Ten derde kunnen we 80% tot 85% van het materiaal hergebruiken en dan een nieuw leven kan krijgen.
Ja, het project gevelrenovatie is eigenlijk ontstaan vanuit de ambitie die we hebben om in 2030 energiepositief te zijn. En dat is een ontwikkeling ook passend bij de strategie vanuit het ziekenhuis samenwerken aan duurzame zorg. We hebben daarbij gekeken op welke wijze we de gevel zouden kunnen renoveren. Maar uiteindelijk hebben we ervoor gekozen om de gevel zoveel mogelijk weer her te gebruiken.
Binnen de architectuur is elk project uniek. En binnen ETEX denken wij aan mogelijkheden in plaats van onmogelijkheden. Allereerst kwamen de tekeningen op tafel en was de intentie om het hele ziekenhuis met meer dan 10.000 vierkante meter bestaande gevelplating te vervangen door onze Equitone Pictura. Maar we kwamen er ook achter dat de bestaande cementplaat oorspronkelijk ook van ETEX, met meer dan 20 jaar oud, technisch nog in zeer goede conditie was en esthetisch ook nog heel mooi aansloot bij onze nieuwe Equitone Pictura plaat.
Bij het oogsten van de bestaande platen is gebleken dat de plaat omkaderd, afgekeerd aan de gevel hangt. Wat maakt dat de randen van de platen een beetje bevuild zijn. Dat heeft ons gebracht bij het aan de zijkanten afzagen van de laatste resthoekjes. Wat maakt dat de platen iets kleiner gaan worden. Want we gaan hem terugplaatsen in een geschroefd, meer wat geventileerd systeem.
Duurzaamheid en circulariteit wordt steeds belangrijker in bouwen. En dat is ook de ambitie van Convenor. Wij willen bijvoorbeeld in 2025 afvalvrij zijn. Zo sluit het mooi aan bij onze circulaire ambitie en kunnen we dit mooi in combinatie met mijn snellingen en de architecten realiseren.
Het project gevelvervanging past ook prachtig bij het project Madaster. Bij het Madaster opgericht door de bekende architect Thomas Rauw. Om eigenlijk te komen tot een soort materiaalpaspoort. Waarmee je jezelf ook dwingt om aan de voorkant goed na te denken welke materialen je gebruikt. En het gevelproject bij Nijsmellingen met de ETEX gevelbeplatingen is daar een prachtig voorbeeld van en past daar heel mooi bij.
This project became an inspiring test case for Equitone and a benchmark for circularity. It proved that even after more than 20 years, the Equitone panels were still performing exceptionally well, and that sustainability starts with mindset. The client's commitment to finding the most sustainable solution was critical. Without that attitude, they might have simply chosen new panels. In fact, the client's drive provided a harmonious synergy, a holy matrimony, if you will, between the client, the architect, the subcontractor, and supplier. Here we move on to example 2, the case study for reuse. This award-winning facade, known as the Recyclable House, was awarded a sustainability prize at the 2020 German Facade Awards. The jury was won over by its exemplary concept. The architect's concept embraced a bold principle: design by availability. Start with salvaged components, prioritise short transport distances, enable demountable construction, and eliminate residual waste. Reuse intensity. This facade, believe it or not, was clad with 90% reused building elements, sourced locally from the client's own demolition sites and refurbishment key projects. The key reused material here was for fibre cement panels originally used in 2007. Once green, they were recoated black for a fresh modern look. The fixing approach? Large format panels were visibly attached to a wooden substructure, forming a rear-ventilated facade. The system as well was chosen for its future demountability advantages. The result? A legible facade order with clear zoning, simple geometry, and a very striking mosaic of recycled materials, all contributing significantly to lowering CO2 footprint. This is circularity in action and a blueprint for the future. In 2011, Germany began closing several old military airports, but one base in particular stayed open. Its location between Frankfurt, Stuttgart, and Nuremberg made it strategically essential. Instead of shutting it down, the army upgraded it, transforming existing hangars to support NH-90 helicopters. Hall 1 in particular required a full revitalisation to safely store critical parts and equipment. This wasn't just a renovation, it was a reinvention, preparing the site for the future of military aviation. This hall is an example designed for a robust industrial building, yet it's wrapped in a striking architectural envelope, a fibre cement forming a camouflage net that flows seamlessly around the corners, highlighting volumetric form. The geometry here was carefully optimised using the largest available panel format, and offcuts on this project were reduced to an impressive 1.6 to 3%. This is design intelligence at work, where aesthetics, performance, and sustainability converge. Our fourth, recycling. SemLoop XL represents our next major leap, scaling up our enforced carbonation process to an industrial level. building on the success already proven in Poland. This innovation prevents 60,000 tonnes of fibre cement waste every year, a flagship of our strategy of 2030 and our commitment to closing the material loops to net zero. But here's a bigger idea. This breakthrough doesn't just recycle fibre cement. It redesigns its entire life cycle. It permanently stores CO2 and creates a fully closed loop system, setting a new benchmark for circular construction. How does the circular process work? 1, grab the waste collection from ETEC's production sites and the wider construction sector. 2, recycling and upgrading. Fibres are removed, the material is processed into recycled fibre cement, known as RFCP. 3, we have an enforced carbonation. The RFCP captures the CO2 directly from the like exhaust, transforming it into carbonated RFCP. And lastly, we get the low carbon cement. This carbonated powder becomes a highly secondary raw material, replacing clinker and feeding back into the new fibre cement products. And so, we arrive at this final point, the heart of innovation. I'm sharing this final video highlighting the features and the potential it unlocks, because sometimes the biggest leaps in circularity starts with the smallest details. By using uni-screws, we create facades that aren't fixed forever. They're adaptable. Panels can be dismantled, reused, and reinstalled with ease. And with that simple act, we unlock the true potential of circularity. Because sometimes the breakthrough isn't dramatic innovation, it's a small, intelligent detail that makes long-term sustainability practical. And there's another element just as important, the biodegradable component. It ensures that as we innovate, we stay on the right side of the problem, contributing to solutions, not adding to waste. This is how circularity becomes real, through thoughtful choices. In our pursuit of smarter, more sustainable construction, something remarkable happened. Equitone partnered with SFS in Sydney, Australia, to rethink one of the smallest components, the humble screw. Together, we developed a fixing system, not just to secure materials, but to support the future of circular design. The new screw system delivers a stress-free connection, engineered with the same patent technology that underpins the Equitone fixing system. And the result? A solution like no other, currently on the market. Simple, precise, and built for longevity and reuse. Today, I'm sharing the final video in this series and highlighting the potential, because sometimes it starts with the smallest. Key takeaways: circularity is not just recycling. It includes design for disassembly, material optimization, and innovative fixing systems. Thank you very much for your time. If you'd like to talk to me, I'll be right outside that door.
Thanks a lot, Christy, for that. It's really encouraging to see material suppliers engaging in circularity and considering constructability, thereby reducing embodied carbon for building construction. Our next speaker is Brian Hubbs, Principal and Specialist with RDH Building Science. His topic is Facade Risk Mitigation, a look to the future based on lessons from the past. I hand over to Brian.
Thank you. Thanks everyone for inviting me back to Brisbane to talk again. It's my pleasure to be here. I come from Canada, in Vancouver. I live in a rainforest, so some of the things I say probably aren't directly appropriate to Brisbane, but the core of everything probably is. I'm a founder, principal, senior specialist with RDH Building Science. We're a primarily North American firm that deals with facade engineering and building science and building forensics. My main role there is looking at forensics, so I get to see what other people have done that hasn't worked out, figure out what happened, and then apply that to my practice to help people de-risk their buildings. So I've seen a lot over the last 30-some years. Today I'm just going to share literally a random bunch of case studies related to fenestration. It's quick, it's like TikTok for building science and facade engineering, and I'll get you to lunch pretty quick. But if you're bored of what you're seeing, don't worry, in about 30 seconds I'm going to change what I'm talking about. What I thought I'd do first is just some fundamentals of fenestration. This is some stuff you kind of need to know to understand the rest of my talk, and also some really cool videos that I've taken over the years at these performance mock-ups, which Todd alluded to, and I'll talk a little bit more about that. So we talk about facades, and particularly how they move. So this idea of racking and vertical displacement. It's important to look at the system. So curtain wall, window wall and strip windows, site-built or stick-built, and large panelized systems are your four big systems. What we're seeing more and more are these large panelized systems. They go up fast. So they really, we deploy them a lot on our mass wood buildings when we build mass wood high-rises to get them closed in and watertight quick so they don't get wet during construction and then take years to dry out. We're also seeing them as a result of some pretty high bar energy targets. So when we have less joints and more insulation, we have better performing systems. So for performance and for speed, we're seeing a move to those. It's important to know how things move when you're designing those systems and when you're coming up with new systems or using them on your building. So let's just talk about interstory drift. Interstory drift happens due to wind and it happens due to earthquake. I'm not sure about Brisbane. I sit on a Pacific megathrust, so at 9.8 every 500 years, and we're 200 years overdue for it. So we have very high loads. You probably have less than this. But all buildings are going to do this. You have very high winds. I was down on the Gold Coast this weekend. Very high winds. So your buildings are going to do this due to wind and due to earthquake. When your building does that, the floors move back and forth relative to each other. We talk about two different kinds of movements. When we talk about interstory drift, elastic and inelastic. Elastic is the one that the building is going to see in its life, and you want it to be air and watertight and perform afterwards. The inelastic is the one where it might not see it in its life, but if it does see it, you want to be able to get out of the building without having parts of the building falling on you. So that's a different kind of earthquake, a different kind of interstory drift, but you don't want things falling out. We also need to take vertical movements. So big difference between the two basic systems. Curtain wall, unitized curtain wall is hung from the slab above generally, and it's outside the structure. Things like window wall, strip windows, they sit on the structure and go in between slabs, and part of it might go past, or you might put panels there. When you talk about different kinds of facade movements, you talk rack, rotate, and translate. Those are your three different. And typically systems are gonna have a primary way of moving and then a little bit of everything, but for the most part, racking is going to be stick-built curtain wall, that type of thing. Rotating will be unitized curtain wall, and translating will be things like window wall or big panels, because big panels are big and stiff and strong, and they can't rack, and they also can't rotate because they're too big. A 40-foot panel rotating is gonna make a lot of up and down at each corner. So this is why I included this section. These are performance mock-ups that we've been involved with, either on one of our projects or helping a manufacturer develop a new product, where I take pictures of that interstory drift, or I take a video and then I speed it up a couple thousand times, because we don't actually do this in real time. It's done very slowly with jacks. But you get a sense of how things move. So if you look at this one, let's go back, you can see what's happening there. Translation, but translation only works until you hit a corner, right? An interior corner, an exterior corner, a curve, then it builds up and you've got to rotate something. So this is a translating system with corners that are built to rotate, right? You can see them opening up. At the end, that's just chamber bending, but this is a large panel. This is a CLT large panel, we call them a mega panel project. We're helping a manufacturer come to market with this, so the cladding is just kind of throwaway, but you can see what's happening here. You're getting translating, they go up to 40 feet with these panels, and then you can see you have to design a very large, very flexible, very movement-intensive joint at the corners in order to take that corner racking, right? And you also have to worry about your fasteners, or just think about what your fasteners are doing when that's happening, your anchors to the building. So you got to design those to take that movement so they don't break or nothing falls off. So I think this is kind of neat. A lot of our own structural engineers were amazed at looking at this. They'd been kind of assuming what happens and designing. Now they can see what really happens, and a lot of them are surprised. They hadn't thought of some of these metrics. This is your classic unitized curtain wall. So this is rotating, pure rotation in this plane, and then the other plane you're seeing an in and out movement. And then we'll reverse that and do it the other way. But that's your classic unitized curtain wall rotation. They're kind of pinned at one corner and they rotate. Now what happens if you have a building like this, where you have constantly shifting balconies? What does it want to be, right? Does it want to be curtain wall? Well, these kind of sections here might want to be, where they run all the way up and down the building. So you could use unitized curtain wall for that. But what do you do here underneath the balcony? You're just going to hang it from the balcony? What are you going to do on the balcony? You're going to set the doors on the threshold so they're not moving up and down. So it's a lot of kind of decisions to make when you do a building like this. And what we try and do is kind of align the stack joint and use something bottom bearing. In this particular case, the manufacturer that got awarded this project was a curtain wall manufacturer. They used curtain wall for this. What they ended up doing was designing a strip that went around the building of curtain wall and then another piece that goes in. So kind of twice the work. I think they lost a lot of money on this job. So this is what we call Franken mock-up. This it racks, it rotates, and it translates, and you can kind of see what's happening here. So, there's just so much going on here, there's no way you could predict it. So the way that we do it is we test it, and then it fails, and we take it apart, and we fix all the things that are moving, and then we test it again, and it failed, and then we took it apart. And so it took 3 tries to get this all working because there's just too much to simulate. So keeping it simple is a good thing. Just pick one movement, make it designed that way, and don't try and do all 3 in one mock-up. It's not going to be super successful. When you finish this thing, nothing can fall off. When you do the large inner-story drift, right, the inelastic, nothing can fall off. So things like this can happen. Here's a big panel where we've bent the anchor, deformed cladding, broken glass, broken frames. That can happen as long as nothing falls out. For the smaller movement, the elastic, we're going to air test this, water test it, dynamic. We're going to structurally test it. It all has to pass straight up because that's what it's going to really see. All right, so I really just had that in there so you could see my videos. They're kind of interesting. I'm going to talk a little bit about IGUs and glass. IGUs and glass, we have different codes, but the beauty of Australia, New Zealand, Canada, and the US is we have many codes we can use, but we all uniformly allow ASTM 2190 as the durability standard for insulated glass units. And that's great because, IGMA, FIGA now have a certification program, so they actually can certify that manufacturers have done this testing. It's very difficult for a layman to look at the test report and see if they passed or failed or what they actually used. So this is something if you're an architect and you want you want product on your job that it meets the standards that you're looking for. This certification program is really good. It helps you ensure it's certified without having to learn a whole bunch about how these tests are done. And then labeling requirements. So you can go out and you can look at the glass and you can kind of look at the label and make sure it's done right. When we look at IGUs, there is a ton of different options that you can choose for all the different parts of a simple IGU. 2 pieces of glass with a hermetic seal. There's about 5 million combinations of things that you can choose. When you talk about that many combinations of things, it's likely that they all haven't been tested and that they're all going to work together. So it's super important that you choose a manufacturer that's been building for a long time in a location that you can trust, that's certified. And this is a certification document that has 3 options, 3 of those 5 million options listed that they're certified to. Just keep it simple and keep using that same thing over and over again. I've got a case where we had to replace about half of the IGUs on a building. And we've got a document that looks just like this, but it's not real, right? It's very easy to produce this these days with a color photocopier and a Word. So the most important thing is you go to your certification agency and actually look to see if they're certified for the products that you actually ordered. For the spacer bar, the glass, all the combination of things that you ordered, they need to be certified for, and it meets your code. So let's talk about case studies. Let's look at how those things can go wrong. First thing I just wanted to talk about was mass wood buildings. We're building a lot of mass wood buildings in Canada. We're learning a lot about how they perform and about some of the pitfalls which we never thought of, because build something new, you learn things. This is a building I looked at here where we're tying a very high performance fenestration system. Well, not we, the other consultant, the building designers tied it into a nail lamb beam above. And so we got called out because they're just having condensation and air leakage problems. This is just a shot of the thermographic scan. So you've got a very airtight, tested curtain wall system, and then boards with really no sealant in them. So air is just moving above your curtain wall system. So things like that you need to think about. One of the things I think I mentioned last time I was here, time of wetness really matters when you talk about wood. This is a project where the architect wanted to put wood in the spandrel box, in the shadow box. It's going to look really cool on day one, maybe not 10 years down the road. Shadow boxes usually have condensation in them, things like that. So here's where I've got a mock-up, which we produced in China, where I've taken a picture of the wood that he wanted to put in there and printed it with frit on the back side of the glass. So that looks pretty good, and that's what we're moving ahead with on that project, is not real wood, just a picture of the real wood, and a picture of the actual wood that the architect wanted to use. That's going to look good for a long time. The wood is not going to look good for a long time if you put it in an environment that's 100% humidity a good portion of the year. This is a program we have at RDH. We take everything we're given, pretty much, that's organic. We put it up on our roof, and we would just take pictures of it every month, right? This is a piece of hemlock. That's a medium durability wood that we have in Canada. This is a acetylated radiata pine, which is, radiata pine is your wood of choice for building. When you acetylate it, you make it much more weather resistant, which is good. But it's roughly equivalent to our medium resistant wood in terms of, that's what it looks like after 16 months. So you put that in a spandrel, in a shadow box, that's what it's going to look like in 16 months, pretty much. So we don't want to do that, even if it's preservative treatment. The preservative treatment works really well. It makes it much more durable. Doesn't make it immune. Here's a project here. I got called out by the curtain wall manufacturer. I do a lot of work for this company, and they were getting blamed for some leakage around their high-performance curtain wall. So I went out to take a look. I've got pictures really close because I don't want you to know what building this is. This is the outside here. You can see mass wood. It's checked. That's what happens to mass wood when you put it outside and let it get wet. You can see it's even been repaired, and it's checked again. That happens. Wood gets bigger when it gets wet and smaller when it dries out, and cracks occur and reoccur. That's okay. Notice on the inside, notice on the inside, there's no cracks or checks. That wood's been kept the same temperature and same humidity. It's not checking and cracking there. Notice that the inside and the outside are connected. So I'm thinking maybe the water leakage here is caused by the piece of wood that's between the high-performance curtain wall that has checks in it. So we start to do a little bit of water testing, and sure enough, water leaks out on the floor here, right at this corner, and I open it up and I cut the caulking underneath this. And I can see there's roof membrane there. I cut the caulking, water comes out, right? So water's getting in those checks, running down and sitting underneath that, and there's caulking on the inside stopping me from seeing it. It also stops it from drying out, right? And this is base building structural wood. It's holding the roof up. So we want to make sure that when we design with mass wood, we design with mass wood and put the mass wood on the inside. And then take that high performance curtain wall, join it to the other side with some type of good membrane, insulate outside, and if you want the look of wood, put a sacrificial piece of wood on the outside that's going to look good, that you can easily replace without having to do major structural work on your building. Mass wood can be an integral part of a fenestration system, right? We see lots of mass wood fenestration systems. We do a lot of interesting work with complex mass wood buildings with glass on them. Just keep it inside, right? It's nice. Keep it inside. This is a Rayco skylight system. It's got a silicone gasket here that separates the outside from the inside, keeps the wood dry, right? That's the right way to do a wood fenestration system. Good, everything's durable, nothing's absorptive, long-lasting materials outboard, wood on the inside, keep it dry, keep it at the same temperature. This is a little slide I show when I meet with architects to talk about their mass wood buildings. I call this a mass wood exposure nomograph. So this is out at UBC. It's in a fairly protected area between other buildings, so it doesn't get direct wind exposure, but UBC is a pretty protected area, or a pretty windy area. And you can see here, so on this side of the building here, you've got brand new looking wood. As we get closer to this edge above, you can see this is a normal day where you've got rain. When we look at the outside of these, we see some deterioration, particularly at the bottoms where it's getting sucked in the end grain. When we move over to the other side of the building, there's some of that mass wood that's completely exposed, and we can see how that looks. It's, this is a building that's about 8 years old. It's needing some work already, right? So this is how I show architects, this is about how much overhang you need per height if you want to make it continue to look like it did on day one on year 10. Open the window of my hotel room, I see this building, I just like, wow, right? But you might want to make your own Brisbane nomograph using that building. So, spontaneous glass breakage. Has everybody in this room heard of spontaneous glass breakage? Pretty much? Yeah. So I won't dwell on it too much. I've got a bunch of buildings right now where we're seeing spontaneous glass breakage. Glass breaks for no reason, falls down on the street. It's tempered glass on the exterior light, which isn't a great idea, but sometimes you need to do it for strength. Most of the buildings between 4 and 40 units have broken. One case, if an occupant was shower glass. Another case, it's fallen on the street below during a parade. So, mitigation measures. Some of the buildings, they're hoarding the public spaces below permanently. Other buildings have a daily person that inspects the facade for nickel sulfide breaks and then repairs them very quickly before the glass can fall out. And in one of the buildings, they're replacing all the glass. So it can be a pretty big issue, and it's pretty easy to mitigate this. For those of you who haven't investigated a nickel sulfide break, you look for that telltale break pattern, butterfly wings, at the center of your glass, so your break point, and then you kind of look at the side with a magnifying glass or a camera like I have, it's a microscope, and you'll see a little inclusion right at that, where the wings join. That's what a nickel sulfide inclusion looks like in some unbroken glass. We've got a method we're working on to find this stuff on site, in situ units. That's what it looks like when it's broken. These are things that aren't not nickel sulfide inclusions that people have identified as nickel sulfide inclusions. That's a refractory inclusion, that's a bubble. So some nickel sulfide myths. Under 8 breaks in 1,000 is okay, right? No, it's not. That's how we design glass for 8 breaks in 1,000, and then we apply safety factors to make sure it never breaks. Tempered low iron glass is similar in risk to tempered heat soak glass. That's also, in my experience, not true. I fell for that once. We had 4 breaks, 4 nickel sulfide inclusions in our tempered low iron glass on a pretty iconic structural glass project. Glass etched as heat soak tested has been, not always. That etching happens during the tempering process, not during the testing process. So they etch it as heat soak glass. Did it go through the heat soak test? Nobody knows. You have to make sure. When we talk about heat soak tempering, this is the way to solve it. So there's a little furnace. You put your glass in that furnace for 2 hours. You heat it up and you hold it for 2 hours at a certain temperature. Lights that are going to break. And then you don't have them on your building, and then they have to make new ones up. So this is an expensive process, but nobody can tell if that's been done. Although there is a method now for figuring out after it broke. The best thing to do is use a heat soak test pen. It's called a check marker pen. You put it on the glass, you heat soak test it, it permanently stains the glass with a UV mark, and then you can look to see if that's been actually done. It won't stain UV unless it's been heat soak tested. Specify this. You go to Germany, they're doing this anyways. You go to Asia, they won't be doing this unless you ask for it and check to make sure they're doing it. Case study here, solar oven. This is a project we got called out to. It's got curved glass. Standard IGUs with a low E coating. This is what happened. They had a fire. There's a lot of damage. The insurance companies tend to replace like with like. So we weren't involved yet. Insurance company paid for this to be fixed, and that's how they fixed it. We got called out when one of those bushes started smoking. So he said, Brian, why is that bush smoking? So we did a little solar study, and we thought, okay, that's actually going to create quite a bit of heat on certain days of the year when the sun's kind of low. We're looking at temperatures in the excess of 250 degrees Celsius. So I thought, my client wanted to know if there's anything we can do. Can we mitigate this somehow? I still want to be able to see out, but I don't want my landscape to catch on fire. So we set a little test rig up here with a black body. We're going to measure how hot it gets. We'll try something, and then we'll come back and see if that made a difference. As Daniel was setting this up, he smelled something burning. It was his pants. It burned a hole in his pants. As we were setting it up, it burnt our actual test rig, so you could see it caught on fire as we're setting up. We're measuring about 270 degrees Celsius there. After we put a diffusion film on, which is the best thing I could come up with to allow you to see through it, it was 250. So it's not going to be enough to not have a fire again. So they just ended up putting a fence around that area and just hardscaping everything with rocks. So careful with those inside curves. I'm not going to get through this, but I'm going to whip through a couple of case studies. IGU failures, right? I've seen IGUs fail probably every way possible, and then I find another one where it's a new thing. This is what it looks like when IGUs fail, right? You got condensation, oily films, low E corrosion, evidence that there was some frost there that's gone, some more low E corrosion, some chemical fog, those little fingerprints and roller marks. That's where you're starting to see the condensation happen first, and that's where it's occurring. So that unit's just getting ready to show you that it's failed. Basic things, basic math. It's a hermetic seal. It needs to be continuous. So this is a gap here in the primary seal. There's two seals, primary and secondary. There are some gaps in the secondary seal. There are some air pockets in the secondary seal, between the secondary and the primary seal. That's going to cause your spacer bar to migrate. And that's the failure that created. And this particular one was a project where we were already replacing units that had failed, and these were what we got. And I said, those are going to fail again. And we were able to get it fixed, but there was a couple that were in already, and they've already failed 5 years later. So we're back going to replace those. So those cause failure. I called it. This is a little machine we use called a frost point tester. You put it on there, you adjust the temperature, you measure what temperature you start to see fog or frost, and that tells you the dew point. From that, you can back calculate how full your desiccant is, how much longer this thing has to the point where it fails. You can do a lot of forensics based on this little, basically, thermos with a thermometer. This one here, anytime these days, everything is so automated and robotic. Anytime you take something off the line and you do something by hand, check it very carefully, right? This is a German fenestration system needs this toggle. They don't allow structural glazing in Germany, so this is a toggle adapter that slides into this. So these units have to come off the robotic line and someone has to install these. So this has been tested already in a pool of water. We're seeing bubbles come out. Here we're pressurizing the unit with some soap and we're cutting it open, and you can see here. It's just QA/QC, right? Right at the end of that toggle. There's a gap. This is low corrosion delamination caused by incompatible gaskets. This is an EPDM gasket. It's touching the silicone. Plasticizers are moving from it into the unit, and it's causing the low corrosion and the fogging. This is a setting block that wasn't proper. This is an incompatible setting block. It's caused this unit to fail. This is a PMU that we're working on that has an incompatibility. You see that yellow staining? That's telling you, it's screaming, the silicone's not compatible with the gasket that's in this system. Those kind of things you need to pay attention to. This is like a weak exposure in the performance mock-up. Okay, I'm going to end. PIB migration. I'm going to end on this. PIB migration, this is your primary seal moving. I don't know if you guys have seen this. It's not uncommon. It's caused by a lot of things, including plasticizer migration and contaminants. But if you look at ASTM 2190, you put it in a chamber and you cool it and you heat it and you cycle it and you spray it with water, you throw some UV at it. But the key is the max temp is 60 degrees Celsius, okay? You take a curtain wall system and you make a spandrel area and you make it a shadow box, you can get temperatures upwards of 180 degrees Celsius in that air temperatures. And you can get hermetic seal temperatures in the 80s. So when you increase the temperature of something, it degrades faster. The chemistry rule is every 10 degrees higher you go, you double the speed of whatever reaction is happening, be it thermal degradation or incompatibility. So if you're 30 degrees higher, it's an order of magnitude. So something that may have gone 45 years, you may start to see those same problems in 4.5 years. So just because it meets the standard test, the minimum test, doesn't mean it's going to work for sure. You need to think about where you're putting it and make sure that somebody's done enough analysis or have been making it in that situation long enough to make sure that it works. And I'll end on that. Well, so many more of these. But I'll let you go for lunch. Thanks very much.
Thank you to all our speakers of session 2. We are now breaking for lunch. We will be back at 2:10 p.m. Please make the most of this time to visit our sponsor booths and continue discussions with speakers. Yes, thanks everyone for joining back in. Our third session today will start with Daniel Liddy, Partner and Project Design Director, Bureau Proberts. Dan will explore balancing facade and form, where bold gestures meet fine detail, using conventional materials in unexpected ways to create enduring, contextually responsive architecture. Over to you, Dan.
Thanks, guys. Can everyone hear me? Yes? Look, those 3 or 4 guys that I met out the front who said they'd clap louder for me, the $100 is outside. I'll give it to you at the very end. Thank you. Dan Liddy. Anyone join the queue? Dan Liddy, partner at Bureau Proberts. Look, we're a collective of many people, but we're very much a we, and I'm going to use that word a lot, so I'm giving you a forewarning now. We're a practice of 35 years. We refer to ourselves as makers of the new, and it's not lost on me that everyone in this room is a maker of the new, and that's our job. But for us, it's an ideology, and it's a way of representing and thinking. And personally, it really means reminding us that we're not a business that designs, but a design-led business, and that's really important to our ethos. We believe people come first, then spaces, and then buildings, and it shouldn't be in the opposite order. We're Brisbane architects, and we work globally, and we're very proud of that. And over our 35 years, we've fallen in love with our roots. We've fallen in love with the idea of being a small fish in a very big pond. And it's always a pleasure to reflect back on the journey and look at the complexity and the variation in our projects and how much they've changed over that time. But the reason we're here today is to look to the future. And there's no hiding from the fact that we operate in the development world and we thrive on the relationships that happen in that development world, and we critique ourselves against the value we create within that world, not just for our clients, but for the cities of the projects we do within them. So it's important to note that Australia in general, and particularly Brisbane, is at a point in time where design contribution is really crucial to its success. Design is a key factor in distinguishing exemplary outcomes and average ones, and it plays a fundamental role in developing cities, giving them character and turning them into places that people value and want to inhabit. We really like to work from the general to the particular, and we draw context from constraint and opportunity, and that informs our outcomes. No 2 sites are the same, and therefore no 2 projects should be either. The identity, the personality of the building, it comes from a macro to micro exploration, and that's really founded in a lot of our work. Inherently tied to this is the building facade. It's the first experience of the building. It's first experience visually and also a representation contextually. It has to set the tone for the ideology and the quality of the scheme, and inherently the quality of the place. But we believe the process is not place making, it's place keeping. Well-designed and well-considered buildings, forms and facades are sustainable in that they are long-lasting. They facilitate qualities of living that naturally cause people to gravitate towards them, and that vibrancy happens through osmosis. And then the legacy takes care of itself. So I'll start with a bit of context to that. The old tin and timber shack. It's humble, it's frugal, but it's bloody effective. It's a quintessential example of Queensland traditional living and the Queensland home, but it's a living style often characterised by its feathered edges. The spaces between the exterior and the interior are transitional, and they modulate a climate and provide casual living experience that engages you on this beautiful threshold between aspect, environment and climate. And those qualities are crucial to Queenslander living, but they're really transferable to subtropical multi-residential development. So the first project I'm going to talk to you today is an example of that. It's what we've called the Queenslander in the Sky. This is Wallan in Brisbane. It's situated on the western edge of the Kangaroo Point Peninsula. Wallan is a boutique multi-residential development. It's 14 apartments or homes, single floor, stacked on top of each other. It's perched right on the western edge, and let's see if I can get this thing working. Ooh. No, I can't. We'll then won't be doing that again. It's perched on the western edge of Main Street. It's got absolute river frontage to the CBD, but it's also got the Story Bridge and the hustle and bustle of that roadway in behind it. So it's really a site that's balanced between opportunity and constraint. The uninterrupted city views give this expansive access, but they really open the door for extensive solar gain. And coupled with that is a coveted existing density that's in the area. It's well held, and there's really a need for controlled privacy and shelter in between these developments. Historically, the peninsula was a source of Brisbane porphyry, which, for those who know, is one of the original foundational materials for a lot of Brisbane CBD and the architecture of Brisbane CBD, and has since moved into a point where a lot of our river edges are actually formed and banked by porphyry. As time and the needs of the growing city have developed, the riverfront land parcels that were once industrial have transitioned naturally into prime residential living outcomes. And in 1925, one of the early examples of those riverfront flats was built actually on our site. It was designed by Queensland's first registered female architect, Eleanor Mottram. And since then, the exuded cliffs are now part of the language and the DNA of Brisbane River as it meanders through the CBD and makes its way through these residential enclaves. Wallan grounds itself in its reference to that rich history of context, and it's formulated around three key qualities: its heritage as a prominence, its expression of place, and a modern interpretation of that Queenslander living I've spoken about. At its base, the building really gives pride to the heritage home, first and foremost. It deliberately elevates above and separates back from the river profile to give it space and breathability. As the tower raises, there's this conscious reference to cliff faces, and the fabric and the form and the design motif really draw directly from the iconic backdrop to the river frontage. The itemisation of each apartment helps embellish this angular form, and that one per plate really gives opportunity to do so. So there's a subtle movement that gives moments of shadow and relief and recess so that residents can still feel an identity and an individuality within a density of apartment dwelling. There's operable panels on three edges, and that adds to this personalisation. The building is always changing day to day, morning to afternoon. It's kinetic, it's sculptural. And the image on the left is actually taken from the Story Bridge. And in this instance, the building turns its back to that frontage, which normally, would be a key elevation, but there's acoustic, there's noise, there's cars. That doesn't mean it can't give amenity to the public realm, and that landscape spine is an offering as such. The subtropical climate was a key former, it has to be, of the plan and the facade. Each floor is conceived as a single home. It's got maximum external frontage to all areas that ensures cross-ventilation, natural light, access to breezes, but it reduces a reliance on mechanical cooling, and it takes those passive qualities of Queenslander home into a two-dimensional outcome. The planning recalls the deep shaded verandas of the Queenslander, and the apartments open pure and foremost out to the city, but then the other three aspects are wrapped by screening. And in keeping with that veranda motif, all the way that macro to micro terminology, the screens reinterpret the timber louvers of the Queensland veranda and our much-loved tin and timber homes. The benefit is a full perimeter of occupiable space beyond the glass line, and the modulating and undulating facade creates moments of habitat and respite in the building envelope, and they blur the line of internal and external. Landscaping really embellishes this, and the result is a natural light that penetrates into the plan and draws you to the outer edges. It sort of creates legibility in what is normally a typical floor plate. Beyond form making, material expression is just as important to sense of place, and much like the geography of the cliff informs the actual sculpture itself, its earthy tones were a huge inspiration for materiality. There was pattern making, exploration, and they were paramount to the process, and they went on for a while. I think if you'd ask my team, they say it was pretty laborious, but they would be adamant to say it was a labour of love, and the devil is in the detail. It's not lost on me saying that to a room full of facade enthusiasts, but detail was absolutely king. We had to balance striation of form, operability, structural rigidity, and it led to dozens of different connection conditions. Each one had to balance fixed, operable, and stacked systems, and expansion tolerance, deflection, and of course wind rigidity, which is quite important at that height, led us to actually favouring an express structural steel edge fixed to the facade, to the slab line. That gave us a little bit of tolerance, but also on-site adjustment capabilities. We didn't have to rely on a boarded works of concrete. We could meander and move on-site as needed. The shift gave opportunity for a beautiful fine edge projection, and it's galvanised steel that protrudes from the thickness and the outside of the slab line. That meandering component of slab edge and that individuality across every single floor plate meant that every floor plate had to be documented, every shop drawing had to be reviewed, every fixing detail had to be reviewed, and of course on top of that, every screen member had to be reviewed. So each level, every screen profile is individually orientated, located and spanned based on bedroom location, living space location, the adjacency of neighbours next door or not next door, views out, you get the picture. There's a lot of detail that went into that, but the outcome sort of speaks for itself, and this is the bedroom on the southeast corner of level 13. At this level, we've reached above the view corridors down to New Farm, and there's Mowbray Park in the distance. There is actually an apartment building to the right of screen, and on the left of screen, we've slammed with that early or sort of mid-afternoon eastern sun. And you'll see the way that the blades moderate and deviate and subtly capture the views, but block the building on the right and get a filtered, dappled light at the right profile. It's pretty rare as an architect to be asked to do a brother-sister scheme conceptually, and the success of Allan really provided this prevalence of the Queensland in the sky outcome. So we were really pleased when one of our existing long-term clients, JGL Property Group, approached us for a special site that needed a special outcome. We asked them where it was, and you wouldn't believe it, it's right next door. So this is Thornton, which is 20 metres southwest of Allan. They're very similar, but they're very different schemes. They're both subject to the same environmental and contextual considerations. They're both grounded in the ideas of subtropical living, and they both present consideration to the heritage built form at their base. But whilst one was focused on a shrouded facade, the other really seeks to do something more engineered. Thornton explores the ephemeral and thermal qualities of glass, and it looks to achieve a sculptural form that enables views, breeze, light, and make that the defining feature of the architecture. And unlike the louvered expression of Allan, its point of difference will register at close range at millimetre spacing ceramic frit that's actually embedded in the insulated glass panels themselves. In doing that, it makes a conscious shift away from a dual layered facade system to a singular envelope that still functions in the same way. The facade is achieved by a combination of bespoke curtain and proprietary window wall systems. So there's a layering stackable glass doors amongst fixed insulated panels. The insulated panels in yellow, the stackable doors in blue. As they deviate and move out and overlay from each other, the facade actually looks like a billowing curtain, glass curtain caught in the breeze. The operability creates, I guess, this fluid disparance between indoor and outdoor living qualities, and the plan in combination with that sort of creates an encouragement for residents to reside at the building edge. The actual fritted screens take reference from the iron lace filigree that's really prevalent in Brisbane. You can see we like context and reference. I think a key outcome of that was we've taken something that is a standard building system and consciously tried to turn it into an ornament, something that people can identify and be proud of. That filtered light experience then creates moments of respite and reflection and pause within the floor plan. The glass peels back and you're offered Juliet expressions, and normal, typical spaces like the master bed corridor taking you from entry to bed actually becomes a feature of the room, and the breathability and the availability of light that comes from that is something that's really unique. The process to develop the frit, much like the screens, was very detailed, testing. We eventually resolved on a system whereby we're at 55% opacity in the center of the plan or where the privacy was required, and that faded out to 15% opacity, so the dark blue to the light blue. The greater the opacity corresponds to the spatial nuance of each room, its privacy, its shelter is provided where it's needed, and as the view extends out to the horizon, the screen sort of dissipates. Layering of a frit is very important. The thermal qualities in Queensland are often resulted in quite dark glass, and having a white frit behind that wouldn't get the result that we needed. So low E was something that we certainly explored, and how that would actually be layered and sequenced within the glass was really important. We actually ended up with clear glass, the frit to the internal face of that, insulation, low E, and then clear glass again. And the result of that is that the white frit is heavily identifiable, and when the sun and the warmth hits it, it's almost opaque. It almost looks like a screen itself, but it's actually the singular envelope on the external. Prototyping, really important. Testing with Inhabit and Hutchies, who built the project, waterproofing, structural rigidity. That process was also a design experience for us, and those two images on the right are, funnily enough, one of my favourite of the scheme, because the right-hand image shows the frit externally and that profile and how prevalent and visually, I guess, out there it is. But as you come to the middle image, that same piece of glass, it's interesting to see how the frit dissipates into the sky above, and so that opacity outwards is still achieved. In doing that exploration too, rather than relying on deflection and structural tolerances, we found that using the planters as a precast mould gave us a lot more flexibility of installation and hanging systems. So something that was more typical actually became an opportunity in installation. I think it's pretty hard to tough to pick a top moment as an architect, but I think the install of these panels are right up there. Planning, testing, procurement, and then COVID means that from first line to this photo was 6 years. I mentioned a labour of love before, but I couldn't have been prouder when I was out there on site for this. Allan and Thornton, side by side, two very different schemes, two very different expressions, but similar ideologies. Hutchies built both of these projects, and their attention to detail was exceptional. They really brought us along the journey, or came on the journey with us, to push conventional materials in very unconventional ways. And that's an interesting point. Facade quality and detail is typically relative to building size. There's an economy of scale that comes with the nature of design and construct contracts that gives typically larger opportunity to larger projects and less opportunity to smaller. The next project I want to talk to was intentionally designed to challenge that misconception. Located on arguably one of Queensland's best sites, Glasshouse is a collection of 2 3-storey apartments stacked on top of each other at Burleigh Heads on the Gold Coast. At its core, the project abstracts and amplifies the qualities of its place. It forms a built envelope that is both shaped by and deeply connected to its context, and in this particular instance was the headland itself and the natural forms of it. It had a strict 15-metre height condition, and the architecture actually steps in unison with the natural topography to gain value out of every millimetre, essentially. It echoes the ascent of the headland behind it, and then it opens up graciously to the waterfront and beyond. The apartments were planned as a linear trilogy. It's open, invited, and private. The living spaces are positioned towards the shoreline to engage directly with the views, the breezes, but then the intimate private retreats are nestled into the foothills of the headland to the rear. What was important was the transition of facade to mirror this, indoor-outdoor qualities, and it was very purposeful. To the rear, and reflective of the headland's volcanic structure, precast is hung as a tooth pattern, and it controls views in and out. Very selective of locations and heights to ensure privacy to developments adjacent, but also catching beautiful aspects through. The choice of precast was definitely a considered one. We're trying to emulate rocks, but the softness and the ephemeral quality of it sort of reflected the idea of water forming, and that something that's been there for a long time feels like it's of its place. But as we got to the rooftop, the jaggedness is certainly looking to create that more rough expression. And the perimeter actually operates as a balustrade to the private penthouse pool, and I can tell you that I had a beer in it before we filled it. It's a cracker of a spot. Unfortunately, I don't think any of us will get to experience it. Central to the plan, landscape fissures create softness and they connect to nature, and it's much like planting that will take hold in nooks and crannies in riparian and coastal edges. Exclusive R&D was done with Cuss Landscape, with the landscape architects on the project, and we were able to achieve this extensive verdantness with only 250 mils of soil. So the green thumbs in the room, that's a pretty impressive feat. And then obviously the defining feature of the architecture, and so elegantly named, the swoops, self-supporting structural fluted glass that are circa 1.5 metres wide by 3.5 metres tall. Each panel is insulated, each panel was rolled in China and shipped individually quite carefully. The glass operates with dual function. The first experience is an emblematic representation of the ocean and the rhythmic pattern that comes from it, and the reflection of that light changes based on viewpoint, so there's an animation to it. But the reflective quality also operates as a privacy screen. So the image on the left, as viewed externally, the concave expression distorts views inwards, and the image on the right, the convex outcome, creates unimpeded vistas to the natural. So we're removing the need for dual facade and privacy. There's money that needs to go into this outcome, but that money savature was directed. Procurement and programming, as always, were really important, but G. James were engaged really from day dot to create proof of concept. And it is complicated and they are big panels, but at the end of the day, the joining details are almost proprietary. All we really needed to do was create width in the head and the sill to accommodate the curvature of the glass. It's a small project, so program was really important, and the ability to keep the scheme completely scaffolded through build was key. So unfortunately for the guys on site, these huge panels of glass had to come inwards and be installed from the slab out. They're structurally self-supporting though, so they were individually put in one by one, and all we needed was a butt joint silicon condition between the two, which really amplified the transparency between them. The interiors continue to reflect the grounding of place. There's these bespoke stone elements, organic striated forms, and they reference the darker tones and the permanence of local basalt. They contrasted with the really restrained white finishes behind them. There's micro gardens, there's filtered light, there's ventilation, and it blurs that indoor and outdoor threshold, macro to micro, exterior to interior. And they really create these rituals in daily life and this coastal living quality. We think that in the context of prime housing, Glasshouse really represents exceptional value for outcome. These two apartments sold at $25 million each, which in a Queensland market is very high. It's two high quality homes for the resource really required to do one, but fluted glass and hung precast aren't revolutionary. It's their use in a direct response to climate that creates the value for the project, and it's about clever thinking with simple things. So my last project that I'd like to discuss today sort of steps away from that commercial nature of development. It's more about civic offering and gestural urban realm positioning. It's a relatively small project with a very big job. This is the Eaves at West End. It's a 2 to 3 story commercial and retail offering in the centre of a huge urban renewal precinct. It's the 2 hectare mixed use West Village. It's 2 kilometres from the CBD and it's now finished and houses about 200 apartments. It was previously the location of the Peter's Ice Cream Factory and industrial lots, and those heritage buildings are dotted around in the pink there. And it had a well-held parcel by the local community of green space in front of it. The community were very nervous about the development. They were worried gentrification would turn its back on those qualities and charm. And so our brief was really to contribute to the public realm. But to do that, there were a number of contextual components we really needed to consider. The key was that the project needed to draw from the qualities of West End and its life and its rich and kind of quirky character. We talk about the project being distilled into roles, and above all else, the Eaves' 3 key roles is a civic connector, a meeting place, and a subtropical response. As a civic connector, it needs to draw people into the site. It's not just about a retail offering and a housing value. So we wanted to take cue from the heritage, and we borrowed the fabric of the arbour that reflects the timber superstructure of the factory building. This folly creates a really strong invitation which leads you right into the retail heart of the precinct. And as you enter from side streets, it's a landscaped journey that doesn't feel like a process, it feels like an experience, and terminates right at this key mature fig tree in the centre of the site. Prior to the intervention, the site really lacked a legibility and an identity. There was these parallel civic and retail uses, but they never really mingled in and amongst each other. So the building form intentionally meanders and shapes around that key fig tree, and it creates an emblematic beacon for people to meet and gather. I'll see you at the screen. So that's that civic contribution of a meeting place. But the facade is more than just a marker. It has a function. The site is completely due west and it was slammed by the sun. So we wanted to again draw from the Queensland qualities and create filtered light that came in but kept the heat out. It needed to perform a civic duty, and that drove us to look from inspiration from the civic history of the site. So specifically, we took cue from the existing brick heritage, but rather than a brick screen that was heavy, we looked to the negatives. So actually, the green there is our cueing of the mortar in between. We created a pattern that allowed us to evolve into a screen. It's a bespoke response that has substance and form, but it's also considerate and it's very frugal for budget, which is important on these small-scale developments. The result is a series of fixed pin terracotta bricks that are on a superstructure, and the negative of that space is the brick itself. Prototyping allowed for control of product, 3D printing, moved to manufacturing, allowed us to test weight, colour, density, sizing. And in doing that control, and having that control of weight in particular, the superstructure was actually able to cantilever out from the building and wrap that tree, as I spoke to before. We often talk about commercial value, and I've spoken about commercial value here this afternoon, but the process or the success of this project is its community value. There's really a sense of cultural capital that comes from respite, gathering, and human interaction. And good design can form that and be the foundation of it, and the rest will come. So I will finish today with a little bit of reflection. I'll ask, how do we balance facade and form? And my answer will annoy you, but you don't. The best solutions are when they're one and the same. And that doesn't come without difficulty. It doesn't come without love, but we have to challenge ourselves. We have to take influence from the urban fabric. We have to look for big gestures, but small details. And we have to use conventional materials in unconventional ways. They'll say build it and they'll come, but I think if you analyse, think, operate, implement, and build it bloody well, hopefully they come running. Thank you.
It was really exciting to see different representations, characteristics, and qualities of Queensland vernacular, as well, and even West End, in complex contemporary architecture and building cultural capital through that. Thanks a lot for that, Dan. Our next speaker is Scott Young, Senior Associate with Omnii. His topic is facade compliance with fire safety provisions of the National Construction Code and evolution. He will examine the evolution of facade compliance under the NCC, explore lessons from the combustible cladding crisis, and the growing role of fire engineering in achieving robust, performance-driven solutions. Over to Scott.
So I guess, look, in terms of facades and fire safety engineering, we really have to look at how it has changed over time. In fact, even how we've been involved in doing any fire engineering with facades. The best way to look at this is look through a timeline. Look at the events that have really shaped changes in response to fire engineering, building surveying or certifiers responses, and seeing how basically, like most building regulations, when there is a crisis or there is a disaster, people respond and attitudes and processes change. Now, I started doing fire safety engineering in 1997, and basically, if we go along a timeline here, I'll just see our, oh, oops, sorry. To make sure my circle, okay. So if we go from 2000 to 2014 of the crossfire, through that time, there was one single fire engineering report where we actually looked at fire spread via facade. After that, obviously with Lacrosse, suddenly we're thinking about combustibility. Grenfell disaster introduced other considerations, including combustibility. And now suddenly we've got a new NCC which starts to consider combustibility, facade tests and the like. So everything, unfortunately, with regulations and compliance approval, and ultimately our involvement in that process as fire safety engineers, has come as a consequence of basically disasters. Now, the compliance requirements for facades, and certainly for fire safety, are basically controlled by the building code. Now, basically the BCA 90 was introduced to get a uniform building code across all states in Australia, and then it's evolved through time to our now NCC 2022. Each of these have slowly changed the requirements for combustibility, for requirements to test facades for combustibility, and the processes you follow to approve them. Now, the key fire issues with with regards to facades from a fire viewpoint are really two important points. The first is the combustibility of the facades. That comes from the Lacrosse fire. We've had other fires in Melbourne, in the Neo 200 fire, and obviously you had the Grenfell, and there's been numerous fires overseas with high-rise buildings and facades. And the prime use of that was the ACP, aluminium composite panels. The ACPs were largely polyethylene core, would burn very well when exposed to large flaming fires. Other issues with combustibility of facades, which are a little bit more hidden, is actually how you build the wall. There are practical requirements when you build a facade. You're going to have sealant, you're going to have insulation, you might have packers and shims and all sorts of bits and pieces that actually make the facade so you can build it. A lot of that's ignored in the BCA, it always has been because they're very minor issues. The second important thing when you build a facade is essentially the continuity of the fire separations to the outside of the building. The building code assumes that when you have a concrete slab separating two levels, that concrete slab goes right to the outside of the building. Therefore, if there's a fire in that lower level, it's got to go out of the building and then break back in. And what happens when you have a curtain wall system, the fire can break. It doesn't necessarily break out, it will enter the facade. And the facade becomes like a little chimney. And it can spread through with actually going outside the building. And so these are the two key fire issues. And the events at Lacrosse and also the Grenfell fire brought both of those things into sharp focus for people. Now these are some of the buildings that I worked on where we had absolutely no fire engineering involvement. They're large buildings. That one I think is about 68 stories. Large, I think I worked on about 3 of these. Absolutely no involvement of the fire engineer. Curtain wall systems, they've got cavities, and the building surveyors, certifiers approved it. The other different process we had with a number of these buildings is the facade engineering was completely separated from almost the rest of the design team. You'd have your primary architects, they may set a specification for a facade, then a completely independent practice would come in, design a facade and almost bolt it on. It was very disconnected with the whole approval process of the building. So they sort of slipped through the cracks, a lot of facade designs in terms of regulatory compliance and looking at the issues of the fire spread. And the other processes in not having fire engineers were certifiers and building surveyors were accepting having your ACP's combustible cladding. There were provisions in the BCA that they were using, which probably weren't the right processes for approving it, but that were the tools they were given under the BCA. And these are some of the reasons of why they approved it. There was a concession for attachments that are combustible in the BCA. There was a concession for composite laminates, which people said that ACPs could fall under this one. And as I said before, when I'm talking about all these little minor elements of the facade, the little bits and pieces, there was a section in the building code that basically said you didn't need to look at them under a specification, but this actually wasn't related to combustibility. This was related to linings and performance of internal linings of materials, but that's how they were used. And the second thing with the continuity, the second primary issue and spread between the cavities is the building surveyors would approve a facade system, a curtain wall system. All they wanted to do was have a smoke separation between the edge of the slab, like it might just be some fire mastic, that would go to the back pan of a facade system, and they considered that acceptable for a sprinklered building. The only mention of curtain walls under the BCA, or National Construction Code as it's called now, was with a building that wasn't sprinkled. These are low-rise buildings, and this was a spandrel protection. There was absolutely no guidance for a sprinkler-protected building or mention of how you treat a curtain wall. And this sort of gives you an idea. This is the only part of it with the spandrel. So this is a fire-rated element. You need a 900mm high spandrel to separate the level, to stop the fire breaking out of here and coming up the top. And it's just saying non-combustible material. Somehow this is packed inside your curtain wall. So there's no real detail. But that was all that was mentioned in the building code about how you deal with curtain walls. Didn't do much for, a 50-storey building because it just isn't even called up under the NCC. So when did the combustibility of facades really come out? Well, this was in 2014. This was the Lacrosse fire. Before that, nobody really turned their mind to it. The proprietors of the aluminium composite panels had been, I guess, looking at this as being maybe an issue because code marks were issued in 2013 for ACP panels that were largely fire retardant. But the regulations in Australia at the time didn't really push it. So people would tend to use the more combustible panels. So once you had Lacrosse, then we had the regulators, VBA, Australian Building Codes Board, CSIRO, introduced industry alerts, drawing to attention. These materials are highly combustible. You shouldn't be using them on facades. The way the building code was being used as a combustible attachment using a small-scale test like AS 1530 Part 3, which would not tell you how a large fire would actually affect an ACP. They called that into question. You couldn't use it. There are also issues about what's a wall, what's an attachment to a wall. And certifiers and building surveyors would all argue about where does the wall stop, when does the facade start. And as I said before, the test they used, because the small-scale test that was referenced in the building code, it wasn't intense enough to melt through an aluminium panel to get into the combustible core. So you couldn't actually differentiate between that one that didn't burn well and one that burnt very well in a real fire. Because you couldn't get through the aluminium, it just reflected the heat back, wasn't big enough. And basically that meant, well, there was no appropriate facade test standard in the NCC, in the building code. And the second big issue, when did that come to the fore? Well, that came to the fore, as I said before, in the Grenfell fire. So, I mean, Grenfell was an absolute disaster. I mean, this had a multiple of issues that caused this to occur. It had no sprinklers. You can see the height of the building. You can see the little fire hoses there. Firefighters can't manage a building which is this tall. No sprinklers. You won't find many buildings in Australia of this height without sprinklers. They'd probably count them on one hand. They'd be very old high-rise buildings. Combustible materials on the facade and combustible insulation. And the third issue was they bolted the facade on and had a cavity between the old facade where they put insulation, and then they had their combustible aluminium composite panel with a 50mm gap. That made a chimney that ran right up the front in the face of the building. And an important point when we look at this, and I'm going to, we'll just have a look. So this is what happened with the Lacrosse building, the Grenfell building. As you can see, fire comes up. Now what happens, makes it even worse, is when you've got an ACP, which is highly combustible, and you've got an insulation foam on this face, the radiant heat feeds back on itself. So it actually makes the fire even more intense as it goes vertically. And obviously, when you're going up in this chimney, it allows the fire to enter the building. The heat's not going out and looping around. It's going very close to the facade, which means it very rapidly can enter the windows and spread fire through each level of the building. An important point to stop that is that you have to put a cavity barrier in there. So you have to block the chimney. So it can't continue to just go up through that gap in a curtain wall system. And all the tests that were done to approve our ACPs, the ones that actually don't burn very well, they all actually had cavity barriers in their tests. Unfortunately, the code marks that we got and the systems that were documented in those code marks didn't have cavity barriers put in them. So what happened as a consequence of all these events? With the certifier and building surveyors, they had to tighten up the processes they used to approve buildings. As I said before, there were industry alerts that were issued by the ABCB, Victorian Building Authority, and various other state legislative bodies that control building regulation. And the second thing that started to present itself was now the certifiers were asking fire engineers to consider the fact that the fire ratings did not go to the outside of the building. How was fire going to be stopped going up through the facade? Something that hadn't been asked for certainly the first 15 years of my career. And the other response was, there was a knee-jerk response when they brought out the NCC or BCA 2016 Amendment 1. They were very strict on what you could do for a combustible or non-combustibility for a wall. And this included impacts on things like sarking. We suddenly had to have sarking that had non-combustible, completely non-combustible sarking, which had certain impacts in terms of environmental issues in the wall cavities. And there are also all these minor construction issues, elements I talked about before, in terms of the things you use to build a wall. When the BCA or NCC 2016 Amendment 1 came out, it almost became impossible to build a wall system practically. And so by the time the NCC 22 came out, a whole lot of new things were introduced, and you know, there's a whole lot of things I've listed here, you can see here that's straight out of the NCC 2022 that basically allowed you to put the sealants in, gaskets, caulking, and it just meant that it was more practical. But it does take time. Regulations in Australia, unfortunately, are a response to a crisis. So now for current buildings, if we're using a current National Construction Code, the NCC has addressed in clause C2D10, it's allowing minor elements for practicality to be combustible. And the other element is that in general we don't use combustible elements on the outside of buildings for our cladding. So combustibility in a lot of ways I think has largely been addressed because it's being looked at very closely. There's a lot of scrutiny. If somebody wants to put some sort of combustible material, it's looked at with a lot of scrutiny by fire engineers, by certifiers, and also the fire brigades as part of the approval process. So a lot of those issues have been addressed, I think. And if they're not, they are looked at specifically. So things don't slip through as easily as they used to. And the other key issue is the continuity of the fire barriers. Now, continuity of fire barriers, well, I'm talking about slab edges, but if you do hospitals or apartments, you've got a fire-rated wall between each apartment. And again, that's got the same problem about not extending to the outside of the building. You're always going to have probably some sort of a curtain wall structure in front of it. So again, that's that lack of continuity. The way we have to look at that, there is really no deemed to comply solution. It has to be looked at through a performance solution with a fire engineer and a certifier, and then the fire brigade will get involved in the process in that approval. There is one alternative way you can satisfy the performance requirement for fire spread, and this is a verification method. This is one way you can do it, and this is where you can actually do a full-scale test of your facade. And if you satisfy the rating, the facade performs and doesn't spread temperature up it and measured in this test, you can satisfy the verification method, C1v3. Of course, this is not practical for most buildings because each facade element will be unique. You can't go and spend $50,000 and do a facade test for facades that are generally bespoke on buildings. However, some people have a standard system, a standard facade system, and in that instance, it may be appropriate that you can do a facade test and demonstrate that it complies with C1v3, and that's just basically would be approved almost straight away. So ultimately, each building ends up with a bespoke solution to address fire spread, because each facade system we see is unique, and we have to look at the way we deal with that issue of fire spread via the cavity spaces. You have metal flashings to restrict fire spread. A lot of the time there'll be a rock wall system incorporated into the facade element to restrict spread through the cavity. But of course, a lot of these cavities, they've got issues. You don't want to retain water, you want them and you want them ventilated. Once you start doing that, you're looking at things that need to swell up and seal up fire spread through that cavity. That's where you end up with things like intumescent strips and sealants. So when fire hits those, they swell up dramatically and they'll seal up a gap. You've obviously got to make sure that they're with the suppliers of those systems, that they meet the weatherproofing requirements. You don't want them to go off or deteriorate or not be able to stay in place for moisture and hot weather. There are a number of systems that have been developed by building suppliers. Bradford have a fire seal, Trafalgar have got their side rise product, and Trafalgar have got a number of different solutions. I think they came to our office yesterday and showed us some of their solutions for some of the ventilated facades where they've got the rock wool and an intumescent. But, you know, the space has now got products to deal with these issues of fire spread that maybe 10 years ago they didn't exist or nobody cared about them. I mean, these are some of the examples. This is the example of a party wall between two apartments. This solution, they stacked it full of plasterboard. And I've put some intumescent sealant in there between the glass. I haven't seen anybody pack a gap like that full of plaster ever. I don't know how that goes after a few years in the weather. The same building, they went for a more conventional approach where they've got flashing, they've got rock wool to restrict spread. You know, this is horizontally through that side of the apartment, going through the cavity and then coming out the other side. So, as I say, everything's fairly bespoke. A lot of the work is the facade engineer needs the facade to work properly, and then we've got to look at how we deal with the fire spread issue. It's almost secondary. And there's a typical one for a slab edge type facade protection, same sort of issue. There's your slab edge here, and the fire, you've got to really block it from coming around and leaping through the inside of the facade. So this will have metal flashing, it'll have rock wool cavity barriers to deal with that spread. So ultimately, with fire safety engineering, we're now getting involved on almost all projects. This is always an issue we have to look at. Generally there is no deemed to satisfy solution. So when you're designing facades, this issue will have to be looked at, and it's probably, there needs to be consideration of the practicality of the method of dealing with the fire separation, but obviously you need your facade to work properly as a facade for your intention. And that concludes my talk. Thanks for that.
Thank you, Scott, for that overview of combustibility in the facade system, in the code, and potential fire engineering solutions to it. Our next speaker is Allan Ramsay, Business Development Manager with Knotwood. His topic is the beauty and longevity of aluminium for facade designs. He will explore aluminium facades, highlighting applications, profiles, and the durability, installation, and maintenance benefits that make aluminium a lasting design choice.
Hi, good afternoon. Like Alexi said, that's what I'm here to talk about this afternoon. Allan Ramsay, I'm the training manager and BDM within Knotwood. Nice to see you all, thank you. We've been asked just to let you know who we are. Knotwood started our beginnings about nearly 17 years ago with a vision to bring timber look aluminium to the facade and building industry, which we've done extremely well. We've since evolved to fill this need, the whole essence being beauty, longevity, and hidden fixing, no welding, very low maintenance. And who we are now, well, we've grown to over 100 employees across Australia, New Zealand, UK, and USA. And the next chapter, well, we're still writing it. Now, here's my brief today, but before I do, I want to build an atmosphere of creativity and beauty in the room. Any creative minds here? Imaginative minds with design? Show of hands would suffice. I expect every architect's hand to go up. Okay, that's a good start. And today's all about beauty and longevity, okay? I want you to turn to the person to your right and tell them they look great. Okay, let's get a spirit going here today of everyone feels great, looks great, do it please. They look great. Hesitation here, there won't be a harassment suit, I assure you. Hesitation here about lying. Some of you on the right, but those of you who went to Sunday school when your dad went fishing, you would know Leviticus 19, 11 through 13 says, thou shalt not lie and stuff like that. But I'm sure there's cracks in scripture for some white lies. So you look great, we're feeling great, we're away we go. Without any further ado, my brief is the capability and methodologies of aluminium systems and what's out there, applications and profiles. God, I could spend an hour on that, but I won't. The benefits, we'll get to those. And the big kicker for today is environment and recycling. We'll get to that. And of course, standards and codes compliance. That's another 1 hour lecture on its own. Capabilities and profiles, essentially across the range, it's wool cladding, I've got them outside, battens, slats, and to a degree decking, which we will get to. Although decking's not a facade, it does tie in, and I'll bring you into that story. Benefits of aluminium. The number one is everything is recyclable, 100% recyclable. You can reuse it, reinstall it, repurpose it, recycle it. It is forever. We use no volatile organic compounds. Very, very strong on environment. Nice to follow Scott. Everything we make is non-combustible. AS 150 part 1 and 3. So we'll get to that as well. Very low maintenance. Very low maintenance. Hello, Knotwood. Oh, your cladding's dirty. Hose it off. We're done. Very, very simple stuff. Okay. It's lightweight and it's insect proof. Termites hate us. All the nasties out there hate us. They hate me. It's lightweight. I can attest to this. I have unloaded copious utes in my time, and it is lightweight. An old mentor of mine once said to me, taking life-changing advice, if the guy doesn't have a grey hair in his head, get advice from elsewhere. You're in good hands, okay? He also said to me, go to functions like this, take away one thing. Make sure, take at least one thing away with you to make it worthwhile. And this is the thing I want you to take away. There's 9 up there. Gonna wrap them up. Timber look aluminium, some of that aluminium that we make is all Australian made, Queensland made for that matter. Everything about it is Australian. Our head office, our manufacturing plant is here in Stapleton. We export to the world from here. It won't warp. It's lighter, stronger and straighter than timber. My father's a builder. Did not agree with my joining knotwood, so I hit him over the head with a length of knotwood aluminium, timber look, and now he loves it. Colour stability is extremely high, we'll get to that. And thank you, Scott, it's non-combustible. Achieves every code of 1531 and 3, high bell ratings, very low maintenance, as I said. Weather resistant, won't grow mould or crack or split. Scratch resistant. I started to an architect one day, a panelling, and she got her nails out and said, oh, does it scratch? I said, sweetheart, you'll destroy your nails. No, it won't scratch. What if I get a chisel and gouge it? I said, that'll do it, I'm out of here. We're not stupid. As a very lightweight, insect-proof, sustainable. I'm going to use this thing. Where is it? We hang our hat on sustainability. You want to partner with a sustainable partner? Look no further. We've got, as everything is recyclable, we've got 150 kilowatts on the roof, about 200,000 kilowatts a year. We recycle 7.2 million litres of water a year, and our footprint's reduced by about 140 tonnes. So we're doing okay. So you want a sustainable partner with good product? Come with us. So what is wood grain aluminium? Plenty on the table outside. 6060 T5 alloy, commonly used in windows, doors and trims, etc. Architectural grade. Meets with the AAA standards for continuance of colour, maintenance of colour. And as I said, very, very eco-friendly. The one thing that's not Australian made is the film. How we achieve that timber look on our product. That comes from Italy. No one in Australia can do it. So it's the one component that's not Australian made. They do great pizzas, great coffee and great gelato. We didn't need that, we needed the film. And the film is brilliant. So I've been asked to let you know how it's made. Full process is extrusion, Queensland aluminium, bauxite extruded by the likes of G. James or Caporal. We pre-treat it, powder coat it, and sublimate it. The extrusion is just simply taken through a billet to get the shapes that we want. And then when it gets to us, we clean it right down to fingerprints off the product itself. Then goes into a powder coating stage where once again conforms to WMA 2604 global standards. We'll get to that. Now, the beauty behind this product is the powder is electrostatically charged. It's drawn to aluminium reducing waste, and any overspray is caught and reused. It's then cured by heating the profiles. We have both vertical and horizontal ovens, and this base coat is the rudimentary foundation of the quality and longevity of the product. Okay. protects us from all external factors, abrasion, corrosion, weather, humidity and UV, and the coatings are all lead-free and Green Star certified. Then we go into the beauty part, where we get that timber look that you want. There's over 50 finishes of different timber look that you'd like, and it's essentially the aluminium that's in powder coated is wrapped in the film, the air is taken out to a vacuum sealed product, it's then heated and baked in the oven, and that sublimation effect, the timber effect, is actually ingrained down into 95% of the powder coated finish. So it's pretty permanent, heat and pressure transfer, lots of different colours out there. But there are alternatives. We're not the only ones. Okay, we're the best, okay. But there are others out there with alternatives. The timber grain wrap, polyethylene film, generally derived from petrochemicals. Oh, look, flexible, durable, resistant, great optical clarity. No good for durability, but let's talk AS 150 Part 1 and 3. It'll burn. It'll spread. Big drawback on that one. Composite cladding, which Scott discussed, all the benefits of its predecessor, the last screen, but once again fails AS 1530 Part 1 and 3. Don't like the Façade. And my favourite, the wood plastic composite, looks fantastic, great hybrid, combination of wood and plastic, extruded, very low maintenance, can't argue with that. It's resistant, something that we're resistant to, except Façade. Coating standards, generally through the AAMA, we have test fields in Florida, worst place in the world. The environment, the toxicity of the environment, the heat, the humidity. I wouldn't live there if you gave me a mansion, but it's great for testing, longevity of powder-coated finishes, and we do plaster with flying colours. Some of the applications we're going to discuss, we can do whatever your imagination is limited to. Gates, fences, feeds, pergolas, trellises, decking we'll get to, right through anything facade effect you want to achieve, we can achieve with you. There's a few shots of what we do, what we've done. And those all made to go externally, it lasts forever out there, 25-year structural, 15-year performance, guarantees on the product. You can also go indoors. Indoors, it'll last even longer. There's some shots there. The product suites, I guess the most important thing on this product, and anyone who makes it with us in the marketplace, all joints are concealed. You don't see any screws, you don't see any fixing, there's no welding. So we can achieve your architectural designs. Very versatile for those ranges I discussed, and there's 100 different profiles. We'll talk about on that. Snapshot of the suites, as I said, battens, cladding frames, geometric hollow sections, all range of accessories. There's a great shot of a use of battens on gates and fences and facades. There's some more. Picture tells 1,000 words. Cladding, we don't just clad facades, we clad soffites as well, ceiling soffites. Very much made for harsh Australian conditions. The Millionaires Road down the Gold Coast, that's right on the beach. Cladding is certified impervious to moisture and water ingress. As we said, we do soffites. There's a range of options there and certifications to burn, wind ratings, combustibility. It's all there. Just on the wind ratings, everything's engineered, certified. We have all the tickets there for you. In wind zone region A, it'll blow the baseball cap off your head, right down to C and D that'll blow your ute off the road with you in it. Finishing up, just a thing on, although decking's not a facade, okay, it does tie into the total effect, in so much you can put the decking down, you can stand on it, and up and close to your facade, admire its beauty by standing on the deck. The decking product is marine grade aluminium, finished in the P5 non-slip effect, becoming very popular. There are lots of applications, meets all the standards. Busy slide, one of the last slides. It's overwhelming, it's daunting, and that's the whole reason. we want you to be daunted by. We want you to be overwhelmed by. These are the standards and certifications and standards and codes that we meet with all of our products. Code mark is but a week or so away. So, yeah, be impressed. I was. So in summary essence, ladies and gentlemen, powder coating and sublimation delivers a beautiful typical product across 50 different finishes, and beautiful forever is our slogan. Plenty of applications, limited by just the imagination of those hands that went up. Okay. Benefits, oh look, it's durable, it's so easy to install, it's very low maintenance. The whole environmental advantage behind it, to reuse, repurpose, remodel, and that's a big thing today. I have teenage kids and my daughter says to me, Padre, she's learning Spanish or Italian I think, and the ill-conceived idea she'll travel to these places one day. She said, is Knotwood an environmentally friendly company? I said, well, yeah, we are. And I made her sit through this presentation last night, by the way. So an inappropriate conversation for dinner time, really. I'd rather talk about football or volleyball or your brother's ex-girlfriend, but let's talk environment. And I told her all about what we've achieved, and I think she was quite impressed. So, as I said, the standards are all there, code compliance is there, certifications to burn, product or not. And that pretty much wraps up my 14 minutes. Okay, we're done.
Thank you, Allan, for that entertaining look at aluminium facades, cladding, and decking systems. We have our final speaker before the panel, which is Colin Niland, the National Sales and Technical Manager for Aluminium Facade Systems. His topic is One Facade Supplier, One Solution. He will present a streamlined approach to delivery, one facade supplier, one integrated solution, backed by in-house engineering and decades of proven systems expertise.
Thanks, everyone, and thanks for staying with us for the whole of the afternoon so that you've managed to catch the last few of us speakers. So really appreciate your time, and we'll spend a brief moment going through one facade solution, one facade supplier, Elspec. So Elspec, as an overarching company, we are going to go through the full solutions that we can offer on your projects and on your facades. We can assist at all stages. So a lot of people will just sell you a product, that's it, we're done and finished. We can sell you and help you at all stages of your project, through conception, through to completion of the project, and beyond with continued investment and interest on the facade. And that would include things like warranties and follow-ups on site with inspections to make sure that what has been done is met with what you started with, is what you got on the job at the end, and is all been signed off and finished. So under our umbrella business, Elspec, we are part of a multifaceted group in our approach to the market. From our aluminium systems brands offering cladding and facade solutions, we've got Elspec Glass, providing supply of glass direct to the market, along with opportunities for fully fabricated facades. We also have Elspec with an X extrusion plant, offering bespoke die and extrusion opportunities. So if you have something that you have created, designed up, whether it be bespoke cladding, bespoke sections for windows or curtain walls or fins, we're the guys to talk to assist with making that die work and actually then providing and delivering those extrusions. Along with the extrusions, we also have our home brands like Elspec Securities with our InvisiGuard and security screens, and Carinya. We can offer the whole package even in the residential market. So why Elspecs? And sadly, I'll read from some of these slides. We have been operating for over 50 years. Started as a small company and have expanded and expanded and expanded, and now close to, if not exceeding, $500 million a year in turnover and revenue. We're fully integrated as supply chain, so that also includes full quality assurance and full quality control. So all stages of your design, all the way through to the fabricator or the builder purchasing the product, we have ensured that it's ticked all the boxes from a quality point of view. We have a one-stop shop for aluminium products. As we noted before, it covers all of our sub-brands, but also everything from hardware to security screens, everything that you want in aluminium. Elspec has that to offer. And as you will see on our stand outside, we've also diversified now into the supply of glass as well. We've got 14 branches across Australia, so that gives us coverage in every state. Being one of the largest there, we've got over 900 capable and committed employees. From us as the technical side of the business, to the sales teams, to internal administration, we're continuing to develop and expand and grow our business. But our people are important to us, so we always make sure they're fully trained and capable of providing you guys with the support that you need. We also have a NATA-accredited test facility, Omnii Test, that combines with an engineer. We can do that as standalone, or we can also do it with our own product. So if you have another product that you're looking to test, Omnii Test is completely independent as well, and has got the ability to have complete confidentiality with your product for whatever project that you're looking at, whether it be an Elspec product or something else that you're delving into. So there's our branches across the country. And as we said, all of our BDMs and area managers are fully trained. They have the full backing of our technical support team, myself included, the R&D teams nationally. We have our specification team. So I'd say, hey, go and meet the spec guys. We've got Bernie and we've got Hillary here today, but I think we've already seen you today. So in the future, reach out to those guys. They can assist locally here in Queensland, but also we have those teams nationally throughout the states to help support architects, engineers, and builders at all stages. So how do we approach this? So as Elspec, and particularly aluminium facade systems, which I'm primarily part of, we'll always start with the project conception at the beginning. Go and speak to the engineers, go and speak to the architects. We then call in our in-house engineers, we call in our BDMs, we call in all of our standard systems. Then we proceed past that point to going through with the engineer to sign it off. And then if we have to, we'll do the testing to get product compliance through to National Construction Code. That then gets taken and put into a specification that goes out to tender, along with, if there's the engineers in the room, you'll have written probably a facade solution that is tagged into the architect's specification as well. That support then goes through to our installers, that then finally ends up with a project that's actually completed, and we then support the completion by looking on site and making sure that it's been installed correctly, etc. So just briefly, our in-house engineering, Subi has been on the stand today. We can help through all those stages. We can provide wind load calcs, mullion calculations, FP 1.4 or F3P1 testing, 4284 testing at Omnii Test, span charts, anything else that you guys might throw at us. We can assist you as well with our in-house engineering. So there's our testing and compliance, just a couple of examples there. Cyclonic impact testing carried out there. We've got our AS4284 test rig. We've got Acoustic Labs AS2047. But we also have the ability to go outside and source testing at other laboratories. So our AS1530.1 test there just for some of our cladding. And we're always striving to comply with BCA NCC compliance at all stages. So a couple of projects just very quickly to run through. So this is one of our ProClad Solid. This is our 3 mil offering to the market. This project was done, the panels were curved, they were completed on site. To satisfaction, we went on site and actually checked the project at the end and signed it off, as well as providing quality control documents at the beginning of the project. The job at Glen Hunley Station, this was internal and external linear cladding. This cladding was part of our ProClad linear range, which is a robust product. If you've seen any of the samples that are floating around, it can be a little bit thicker than some of the products, but we've deliberately designed it that way to be more robust, and we've actually had it fully engineered to span further so that the on-site installation time is reduced the amount of fixings that are required are reduced, which also minimises the cost of those materials on the project. Particularly one of mine, when I first started, we got involved with this one at Waterloo Metro Station in Sydney. This was provided as a fully manufactured, perforated and folded cassette system, fully engineered prior to reaching site, fully quality checked both at supplier and at our factory in Interchange in Sydney before it went out on site and got installed. Fantastic job. This is part of our by design process, so one of our sub-brands under Aluminium Facade Systems. Whatever you want us to look at, we can design it and help you work with it. Basic projects. This was an LSPEC project with 150mm Hunter Evo, but on this project we utilised, with the glass, provided WERS calculations and also mullion calculations and spans, so that we could provide a nice full facade whilst meeting Section J, and helped with the fabricator and the architects and engineers on this one. Final couple of slides. This is Lumiere in Queensland. Again, Section J requirements, wind load calculations done by our engineers, full height slab to slab, and then the battens were tested and also engineered to span double height fixings. I'm mindful of the time because on the last one, I probably can run over a minute, maybe. Our innovations, so you guys might have seen on the stand, our embossed cassette panel system. So this is part of our by design system. We've incorporated that in a project in Perth. We'll be fully powder coated, 4 different designs. That was worked with an engineer over in Perth that we've now got sign off on. We're also looking at, as one of our innovations, unitized cassette panels. So offer a 4-edge support system, which one of the biggest issues that we have with cladding can be oil canning. So we've looked at that, come up with a couple of solutions. We're also looking and working with Technoform to look at how we can actually make that a thermally broken system as well. So these are some of the innovations that we get involved in to help promote and innovate the market to take the next step. So in brief, LSPEC, our innovation is our brand. So moving forward, LSPEC are expanding into lots of different markets, but our brand being as it is, you always know that you get the best quality, the best engineered, and the best service before, during, and after your design and your installation. Thank you very much.
Thanks, Colin, for that overview of LSPEC's work. We are now moving to the final segment of the day, the panel discussion, which is titled Establishing Facade Engineering, a Necessity, Not an Option. This session will be moderated by Balesh Balishan, Senior Associate, Facade and Sustainability in Habit. Over to you, Balesh.
Thanks, Kavita. Good evening, everyone. So I know you have been going to be thirsty for the drinks and networking session, so probably this session is going to be your bites for them, so definitely. So before we begin, I would like to acknowledge the traditional custodian of the country throughout Australia and recognize their continuing connections to lands, water, and community. We pay our respect to their elders, past, present, and emerging. Today we have an exceptional panel representing architect, sustainability, and facade engineering. Please join welcoming Anne Kovacevic, Technical Director at McDonald's, leading sustainable buildings and presents with a deep expertise in building physics, well-being, and future-focused facade performance. Alex Ward, Principal at Fender Castellist, bringing in global design perspective and strong commitment to sustainable, performance-driven architect that responds meaningfully to place and context. Our next panel member, Taryn McQueen, Principal at Populous, delivers inclusive world-class stadium and civic projects, championing women's sports through the master planning and complex delivery from Australia to 2034 FIFA World Cup. Wow. And our last panel member, Richard Fairhead, Director at Building Envelope Group, Facade and Building Envelope Specialist with over the 27 years experience across the new builds and expert advisory. Please give our panelists a warm welcome. Let me start with a simple question. If something represented 15 to 20% of building total construction cost, controls safety, energy performance, durability, occupant comfort, and increasingly embodied carbon, would you consider the discipline as optional? Facades today are no longer architectural or aesthetic thoughts. They are complex, high-risk, high-value engineering systems. So you've already gone through a lot of presentation in here. You can value how that happened. And yet in Australia, unlike other engineering disciplines, facade engineering still lack clearly defined, nationally recognized competency and accountability framework. So we have the disconnected, high technical complexity, high financial exposure, high public safety implications, but often unclear responsibility. That's why today our conversation is meta. This panel explored the one central idea, that means facade engineering is not a niche capability, it is a necessity. Before we dive in, a quick show of hands I am asking from the audience. How many of you believe that establishing facade engineering as a formally recognized discipline is necessity, not an option? Say like around 80% or 90% of the hands I can see there. So most of them I agree. So pretty much I'm back to the panel members now. So this is your turn. As I mentioned before, facade represents 15 to 20% of the project cost. So you can clearly see this is we took it from the exact project and work out the numbers of how much is the cost and it's going on there. So why are they still often treated as a secondary? And what does that really cost us and risk, revoke, and long-term performance? It's a long question. But I would ask, starting from where's the schematic and concept start? So maybe I want to get from Taryn or Alex. So what is your opinion? Because you are the one not in the facade engineering background, as the architect. So we want to get something from you guys first. So what do you believe in this one?
I think the facade is the architecture. So there's a lot of requirements that we need to meet, but it's the element that is the most noticeable part of the building. So it really informs the form, what we're trying to portray. We've heard before that there's elements that we introduce into the facade that relate to its context. So it's not just an architectural element anymore, it's a technical element. So there's a lot more that we need to consider in how we're designing than what we want to introduce. And I think as we understand our environment more, there's far more consideration of how we design these facades. So it's not just a part of a building anymore, it is the building.
Yeah,
Alex?
I would completely agree. We've had the benefit of designing the second tallest building in the world, which has an extensive facade, whereas we also do smaller retrofits, what we're doing at 450 Queen Street, where majority of the cost is the facade because we're retaining a lot of the structure. So we've taken that into consideration quite a lot, and it also keeps us understanding our context, where we want to put the money and put the time and the effort, where you're able to interact with the facade at the lower levels and the podium structures. And then put a lot of the thinking, obviously, into the upper to be efficient and affordable so that we can also try and build a lot more square footage.
Yeah, great. So the point you're pointing of the time and the money, where do you want to put? So we could see that couple of examples before, they're talking about the similar thing. So where we do want to put the time and the money. So probably the question from sustainability point of view, what is your thinking on that question?
Well, I guess the facade, it really is, it's what's obviously separates the outside from the inside, and so it's giving us a lot of our performance. In fact, you know, most of our performance is to do with like how well our facade is performing. But I suppose we also want to be able to connect with the outside as well. So it's that balance between providing something that's really isolating us from facade and control it, making the inside of our buildings controllable, but also being able to work with our facade. So in different climates, we can open and shut and connect with the outside. So absolutely a really key fundamental part of sustainability. And I actually thought facades was a subset of sustainability. No, I'm just kidding.
Yep. Now back to Richard. So engineering point of view, what is the moment your career when you realized the facade engineering is not an optional?
It's always been an option. It can't be an option. It has to be part of the design. Since when I started fresh out of uni too many years ago, to the points that were raised where if a facade engineer or a consultant is on board, even when you go to GA, if you don't have the benefits of a facade engineer on your team, some of the language that the architectural practices are trying to portray might not be achievable. So getting that in early so that you're not having to go back into your DAs and making amendments and actually getting the visual and contextual look of the building early on, it makes a big difference.
Yeah, that makes sense. So because your background work is as a facade engineer, but there's a similar question I want to really get the opinion from Taryn. When do you think, so because you come from the architecture, when do you think in reality the facade is a really, we need it as in your career, do you need it, the facade engineering is essential? So you, from the beginning as a graduate, you thought about straight away, or whether you thought about in later part?
I definitely didn't think about it straight away when I was a graduate. I think that was exemplified. I grew up in Queensland. I studied here. The outdoors and the indoors is the same thing for us in a subtropical climate. Anne made a good point just before that the facade is the element that separates the outside from the inside. And when you start working outside of Queensland in climates where the weather is far more extreme, you have to have that separation between outside and inside. So one of the first jobs where I started to realise that the facade has to perform in a far more important way in buildings is when I started doing projects in Victoria. So I've done quite a few down there where we have elite training facilities and it is cold most of the year. You're wanting to keep the inside warm, so you have to have that separation between the two spaces. Whereas it's not necessarily the paramount thinking up here, because we don't need it as much. There's hot months, sure, but when I was working on the home of the Matildas, it was one of those ones that was a Green Star accredited building, and it was in a southern state that had more extreme weather, so there was a lot more emphasis put into the facade design because we had to consider it. So I think the requirements that are coming into the code documentation, the performance requirements that have to be certified, it's pushing everyone into a better direction. And then those additional certification processes on top of that is making us do more. So I think that's where we're starting to see a lot of improvement across facade design. So we're not experts. We know what it wants to look like, but there's a lot more performance requirements that we need to consider, so we need input from yourselves.
Yeah, that's a good point. So probably you're thinking about in the concept design or schematic design, a facade is a really important thing, which facade engineering is really needed. So where do the facade failures most commonly originated today? Say like concept design or procurement, value engineering, or the construction. So Alex, maybe what is your opinion on the concept design and other things? Maybe I can more elaborate for the procurement or value engineering, Richard and others. So first I start with the path in the way usually the architect is thoughts, great design is come from you guys to great thoughts. So then value the engineering in the next step. So probably I want to get starting from you. What's your point?
We like to think the great design starts with architecture, right? But you need a client initially to have that vision to take the project on board. And you also need them to come on board with you when you are designing every component of the building. When it comes to the facade, easy failures are unaware of its climate and its context. You see a lot of the K-Rudd sporting halls dilapidating with mold because the facades weren't designed appropriately for their climate. They all brought in systems that were easily just being able to put up quickly due to the cost and the affordability, but then being able to translate that with someone who's informed of its local area, set a performance specification so a builder or a contractor can get on board and set something that is local will get us a lot more fundamentally long-term value than what we're having to do now in a lot of these places and replace these facades. I've been fortunate enough to work in practices where having a facade engineer or a facade specialist on board to curate and assist in the designing of these external skins is fundamental in my opinion, and I'll always probably go down that pathway to get that advice, especially when you get to procurement and engaging with industry. It's a lot easier having someone take along that journey.
What is your opinion, Richard? The question is, where's the failures most commonly? Do you reckon whether it's going to be the concept or procurement or value engineering? So what is your experience?
All of the above.
Okay, yeah.
No, it comes down to so many different factors. We've somebody from sustainability, we've got architectural, we've got facade consultants, and then somebody else earlier today was showing all the other disciplines. And facade is somewhat architectural, but it's that whole left brain, right brain fight that we have to have with ourselves. We have a lot of different disciplines that influence our design and our packages. So one of those missing steps creates a void or potential for failures to occur. Probably being somewhat cynical would be in the contractual side, on the D&C side. Architectural practices will do a nice design, it'll be thought through, and then it goes through to a D&C contractor to finalize. And an uneducated client doesn't understand the material substitutions or product substitutions. Is it the same as what the original design was? So there's a myriad of failure mechanisms across the entire project, let alone trades for one where we don't have the same number of trades that we used to and we rely upon, where we are now a workforce to install and laborers versus qualified individuals.
Yeah, that's the other point nowadays is the ECI through the bring into the early contractor involvement, so that how it's really to working. I know that architect point of view, so you need to have some sort of leverage to work on your thoughts, but at the same time, sometimes the knowledge-wise, if you bring into the early contractor involvement, so how that's going to in reality, we can reduce the risk and other things. So what is your opinion on that one?
I think from a buildability perspective, having early contractor engagement is good. The balance comes into maintaining the design of the building and the design intent so that it can be carried through and looking at things as a whole rather than a finite cost and always, we can do this cheaper this way. What is the maintenance aspect? Todd talked about it. Brian showed some slides too. There's a lot of issues that happen in there where you can really lose that value and those good solid design principles.
Yeah, exactly. You pointed out. So I also want to point out the Todd's and Brian's presentation. So that's where we need to spend the time and the money. So as Alex mentioned before, yeah, that's the other important things we say. Like we are sitting in the norm land zone as a facade engineer. So we need the architect background, so structural engineering or mechanical engineering and sustainability and other things. And so facade fit is the intersection of the lot of strength, energy, carbon, durability, safety. How do we stop sustainably being bolted onto and start the engineering it from day one? Because a lot of times I can see everyone talking about the embodied carbon, reduce the carbon. But in reality, we want to see how much is the design life and how long it going to be stay there, and the structural point of view, one of them. So condensation point of view, we need the installations and other thing. Say like a waterproofing from the different approach. So how we going to really balance this stuff and giving to the sustainable is the real outcome from that. So some things you can elaborate from your experience.
Yeah, well, I mean, we've got this picture up, which is a project that we're working on at the moment, and I think the reason why I sort of suggested talking about it is it's obviously something that we're really trying to push at the moment is reusing existing buildings, and particularly in this case, sort of reusing something as closely as we possibly can. And it's interesting from a facade point of view that we're, you know, there's little being done to it, and you know, you have different challenges. And as Taryn said before, you know, in Queensland we have very different climate than other projects that we're working on. So you know, these traditional buildings were built to breathe and to, you know, to have open courtyards and draw air through. Yet you know, we then want to use them in our rising climates, but our also changing expectations of what's going to be inside. And so we have to think about how we use these facades and still achieve. I mean, certainly we're not going to achieve the thermal, we're not going to achieve the airtightness that we quite like to achieve on other projects, but you know, it's still working with this facade, and by using this facade, we think we'll save up to about 70% of the embodied carbon, and also just have a wonderful place and be, you know, reinvigorating our existing buildings. But it does mean that we need to change our expectations a little bit about how we work within that facade. So again, working really closely to understand how we optimize that.
Yep. The other important things, we need to facades, as you mentioned, it's need to be the climate and geography related design. So how we have moved from the generic detail to truly location specific envelope designs. For example, the Queensland really high wind loads in here, and also the cyclone debris impact resistance you have to consider into the northern Queensland. So in that type of, definitely the facade standardizing or the practices has to be geographic focused as well. That's the obvious thing. So Taryn, so what is your opinion on, especially on that question?
Well, geography is essential, and I think I was joking with a couple of people earlier that in Australia we're probably a little bit behind because you could live outdoors for the most part all year round. We don't have weather that's trying to attack you. So this is a great example that you have to keep the weather out. So we're trying to provide something that you can have a comfortable space inside. The technology is obviously changing, so there's a lot of opportunities for us to change these environments and have those views outdoors that we were talking about. But yeah, I think that every building has to relate to its place. So whether that be aesthetic or thermal or physical. So.
Yeah, exactly. So this is the projects in, I think it's the Antarctica and so you probably, you can, so how the geography related, so the facades has to be.
Yes, so this is a project we're working on in Antarctica. I can't go into too many details or anything like that, but the facade engineer has been doing a fantastic job and is obviously one of the key people in this project. I mean, achieving the airtightness and dealing with all the conditions that we deal with in Antarctica, and thinking about the shape of the building and everything like that. I think from the previous slide that we had up, where you know, we're in a Queensland climate where, you know, we use a facade to breathe through, and for thermal mass we've then got this completely opposite facade where it's really firmly, it really needs to perform. It has a very tight, very stringent air tightness. And as we were saying before, you know, when do we achieve this? Well, and I think particularly Green Star, as Taryn alluded to before, we're really trying to bring the assessment and the thinking about things right to the front. So say with air tightness, you've done your full envelope and thought about where it's going to leak and what your strategy is to achieve that air tightness, working really closely with all the facade engineers, but then taking that through so that you've got a procedure to work through with your contractor. And then, you know, for something like this, we say, well, how do we really make sure that it works like we want it to? Because these are pretty much the main pieces of sustainability. How do we make this function? Well, it's airtight.
Yeah, well, no, that's a great point, and in reality, but in the practice and performance, couple of topics everyone's talk about now. But how we are going to say, in reality, Australia has a world-class standard for the other engineering, for the structural engineering or any other disciplines. Why facade engineering lagged behind in having clear national competency framework? What international model should we learn from? So that's something I want to ask Richards, because you dive into the more than 25 years in our industry. So what is your thinking about on here?
Yeah, so what's up on the screen there is the model that New Zealand uses, where you have design, peer review of design, installation, and then you have review of the installation by a third party, usually the design reviewer. This is one aspect of it, but the start of your question there saying, where should we be looking? If you look to New Zealand, we've got government support in the likes of brands. Canada, where I'm originally from, we've got the National Research Council of Canada. Those large institutions really help focus and work directly for the environments in which we have to design for, but more importantly, that information is disseminated amongst the different parties. So it's taught in North America, it's taught in parts of Europe. Unfortunately, a local university used to have a Jim Stringfellow teach it. It was great, and there was an influx of young engineers coming through with some knowledge of that. We don't teach it here. But the easiest way for us to look at it is to look across in New Zealand with what you've got. Obviously, everything is centralized with councils there, so everyone reports to the council. So if you're a producer statement author, you have to be deemed competent by, starts with the Auckland City Council. If you're in with them, you essentially can work in any other council jurisdiction in the country. You're evaluated, you are monitored, and every 2 years you have to then reapply. You have to show competency, you've got to show that you're doing your CPDs and everything like that. So it's a really good model to follow from, but the missing link in Australia is we have independent certification. That's the one piece that's missing. I like the process. Some people might not agree with, they might think it's too onerous in New Zealand, but it's a checks and balances along the way. And this is similar to what was introduced in the early 2000s in Canada to try and get a similar type thing for a designation for people who practice building sciences or envelope works as well.
Yeah, that's a really good input you put in the tables and for the audience in reality for the international, how the practice is happening. So one good thing is in here, Vicky, you can see that where is the accountability is there for even concept, or where's the design, or where it's coming from, so failures happen. So you can see that track down, so where is exactly happened from now, we are missing on that one. So example.
All of those people, because I do a lot of expert witness work, and in New Zealand, if you sign a producer statement and a building fails, you're accountable.
Yeah. And Alex, what do you would look like for the facade standard, more perspective or performance based? So the question I asked, because you guys always cover the which is the perspective or performance based, which one is the good. So probably it's the good thing I can get it from architecture background, what you are thinking about that question.
Sure. I mean, we rely on a lot of our consultants and teams that we work with to provide us with the best way to go forward. We rely on industry to provide input into our design to get to a point where we can go to market. But we also like to provide that innovation piece, so when we go out to tender, it's more of a performance-based specification, so they can come back to us and innovate and innovate. Like, we can only push our consultants so far with the ideas and the strategies and what we want to achieve for the buildings that we produce. But it is up to the industry and the people willing to build it that actually get it done and come with that additional innovation that they may have been testing that we're not privy to. And we usually try to do that through prototyping initially in the early tendering, after tendering phases, and to get them on board. Similar to, I think, what Dan had presented earlier, looking at many different options about how we can actually get that a little bit further, a little bit of a better outcome, and really push it for each project that we do. So I think, yeah, to answer your question, I would go performance-based each time. But sometimes, you know, you do get a contractor who hasn't come across that before, and that, you know, initially happened probably around in 2023 when it started becoming more of a way to go forward with the procurement. But I think you'll find a lot more sophistication now in the tendering process with the facade contractors and their subbies.
Yeah, that's exactly the horses to horses. That's probably the we have to depends on the project situation. So and other things. Move on to the other chapter a little bit. So this is the more important things we need to talk about. So should be facade engineering be formally recognized and registered discipline similar to other discipline? So what's your thought on why this has to happen, say like a Design and Building Practitioner Act in professional expectation for facade engineering in New South Wales? That's the only area we can see the facade engineer definition now. So, and to the more responsibilities on there. So what is your opinion?
Well, we've had very similar issues with sustainability, and I guess, you know, with sustainability, we see a lot of people come in through a mechanical background, and then we see a lot of architects as well, and similarly there's limited sort of a correct direct career path that ends up being a sustainability consultant. And we did work through with Engineers Australia some time ago to create some career paths, and because currently sustainability sits in the engineering college, but most people coming through a mechanical background, so we did put some competencies together, but it hasn't really materialized. And I think in some ways we see more of the being able to check competency based on some of the industry bodies like Green Building Council and Neighbours and things like that. So I guess that's sort of how it's evolved. I'm not sure if it's necessarily correct, and it is difficult if you want to maintain your engineering accreditation and go down that pathway. But there are ways to work that through with Engineers Australia and get sort of some competency. But I guess, you know, with a lot of these more specialist disciplines, it is something that maybe there just needs to be sort of some pathways that you can put in place.
Yeah, that's a good point, because currently a couple of different ways that Society of Facade Engineers, and they are supporting and to thinking about all the facade engineers putting to the facade engineering is the area of practice in the Engineers Australia too, as a one like a structural engineering or any other electrical engineer or something like that, facade engineering as an area of practice. Definitely that the way every people, the facade industry, if you meet, so they are talking about that's really the important things. So need to vision, because that is the lot of other things, so the accountability and for competency of the facade and a couple of things in really working on that. Richards, when the facade fails today, so is accountability clear or does it fall through the cracks?
Accountability here is not, definitely I think it falls through the cracks. In some of the litigation that myself and others have done, it's very difficult to actually get those that are making the final decisions and the sign-offs. Structural engineering, let's say the column fails, much like what happened down in Sydney, structural engineer and the builder were held accountable. Because a lot of the way we've been doing business traditionally here, where it goes through, and maybe it goes to the subcontractor and he signs off on it, we're seeing, and others today have talked about it, where those people phoenix and or go bankrupt or they're not around anymore, so it goes on to the next person, which is typically the builder, and everyone starts pointing the fingers. I think with about 3 years ago, September, the Building Code Board got rid of, for weather tightness, they said they got rid of certifier discretion and thou shalt have a performance solution for weather tightness. That, I think, is the starting point for actually having accountability, somebody who's willing to look at the designs, make sure that the processes along the way are meeting the environmental conditions, structural expectations, so on and so forth in design, and seeing that from the beginning of the project through to the end of the project. I think that's the first time that I'm starting to see that accountability come into Australia.
That's good to know, actually. It's other thing is one is the accountability and the other one is competency. We need to think about the say, like example, there's the facade is nowadays is more complex because of the early days is the drawings boards and other things. Nowadays is the software is playing the role, and we can lot of different geometries and complex. Say, like example, the facade every time taking through this slide. So to design these type of stuff, so what are the minimum competency needed before someone should design or review the high-risk facade? So is that actually standardized anywhere, or whether we can find it on the competency, Richard?
The competency for the design?
Yeah, competency for the facade engineer.
Yeah, for the facade engineer. Not in Australia. Obviously, the structural aspects. So what I'm going to say was the traditional facade engineer, which was a structural engineer that made his way into facade and aluminum and glass design. But when you step back and you have a look at it, I kind of giggled at Simon's presentation earlier on the stadiums. It didn't say facade discipline lead anymore, it said building envelope. When I moved here 18 years ago, I said, they said, well, what do you do? I said, I'm an envelope consultant, building envelope consultant. And they looked at me funny, and it's great to see things actually come full circle again. But the competency of a facade engineer is not just the nuts and bolts in structural engineering. It's the envelope of the building. And that's where having that in there, people that have that knowledge and materiality that was spoken about earlier today, horizontal surfaces, vertical surfaces, the interface between them. I thought that presentation, or the slide with the multiple projection balconies in and out. A lot of people can design the glass, but they don't understand all the interactions.
Yeah. Example, even see the panel of, say, the picture on here, it's like a different skirting shapes on there, so complex, and this is another one. entire building in front of there. So taking on for the design of this stuff, it's really the important. So another things I want to say, because we study concrete as a structural engineer or civil engineer, so we study the concrete, traditional members, timber or brickwork. But if one graduate says, I want to become a facade engineer, what is the defined pathway without the learning through the failure? So, and so probably it's sustainability point I asked, and then I come back to and ask about Richard. So, so what is your opinion on that?
So what are the number one things to fail?
No, if a graduate says, I want to become a facade engineer, what is the defined pathway? Do we have anything?
I mean, personally, I think as Richard sort of alluded to, probably the most direct path is structural engineering. But I think what we find is that a lot of the specialist disciplines come out of interest in different areas, so you could end up with sort of anyone moving across, and I guess that's the way we see careers kind of evolve these days. So I think as long as it's sort of defined what those minimum levels of competency you need to have, and that you can learn with someone and have the correct people reviewing things, I think there's a lot of opportunity to move through different ways, and that's how I feel with sustainability as well. There's lots of opportunity to pivot careers so that you get to a certain space.
Yeah, as Richard, you already mentioned about the universities, the professional bodies, or any other facade engineering degree. So that's really the things. Yeah.
If you want to be a facade engineer, find a multinational company that has offices in Europe and North America, or find companies that have a lot of expats who have studied it. So.
Yeah, even Taryn mentions is that even for the architecture, to feed up the facade, so you need the CPD vents and other things. So what's something you've been pointing out?
I know in Queensland we don't have it, but New South Wales have introduced CPD for architects. You sort of choose your own journey. You can pick anything to get your points. I think there's merit in what New South Wales are introducing of key focus areas. Like we always talk about architects, so the jack of all trades, we need to know a little bit about everything and then engage with our consultants to make sure that we're doing the right thing. But there are definitely CPD sessions that need to be focused on facade design because, again, it's getting more complex. We're pushing into parametric design, which is really advancing the way we're detailing these things. So there's a lot of continued education that we need to do to make sure that we're designing designing facades that are aligning with what we need to meet.
Yeah. So, turning to the time constraint. So I want to ask only the one sentence answers from everyone. So maybe I'll start from Anne. So what must changes in the next 5 years to ensure the facade engineering is treated as a necessity, not an option?
Start with someone else. Start with Richard.
Yeah, that's all right. We need to understand and educate. We need government to actually recognize what it is that they have mandated us to provide to industry.
Yeah. Taryn?
I think the code documents probably need to be more proactive than reactive. We need to start looking at what are the right things to be doing rather than fixing the problems that we've created in the past.
Alex?
I think it's all about the pathways that they can offer, and if they can set that up. I mean, I've been fortunate enough to work in large practices that have it as a specialty, and a lot of people use that at the start of their career and decide they want to focus on just facades. It's very much the case in New York, very much the case in London, so I don't see why not it shouldn't be here as well.
Okay, I've thought of a good one.
It's time to wrap it up now. Facade engineering is not an optional extra.
Anne's got one. She's ready.
Oh, sorry, you want to?
Okay, sorry. At the last minute, that's all right. A free letter. So I think the main thing is around understanding sustainability and performance and really respecting that. And so clients wanting to achieve that for their buildings as well.
Yep. No, I think pretty much is this is a good discussion. So facade engineering is not an optional extra, it's a fundamental to safety, performance, long-term value. We have heard from the strong perspective from our panel. Now we love to hear from everyone in here, so the panel members. Thank you to each panelist for your valuable contribution. So hopefully a lot of questions would happen after this. So thank you very much, and Alex, Taryn, Richards. Let's give them a round of applause. A special thanks to organizers of Zak World of Façades and sponsors who made this event possible. Yep. Thank you everyone for your joined us today for the Zak World of Façades 2026 in Brisbane. So I think after we do have a networking session and the drinks. So yep, hopefully you can join us after this. Thank you everyone.